Look up at the night sky, away from the city lights, and you might just catch a faint, fuzzy patch of light among the stars. To the unaided eye, it's a smudge, a cosmic afterthought. But that tiny, blurry spot is one of the universe's most magnificent and ancient structures, a globular cluster, a glittering, spherical city of stars bound together by gravity, orbiting our Milky Way like a distant, silent sentinel. For centuries, astronomers saw them as simple curiosities, but we now know they are anything but simple. They are time capsules, holding within their dense cores the oldest stars we can observe, stellar fossils that have witnessed nearly the entire history of the cosmos. They are cosmic paradoxes, places where the rules of physics seem to be bent and rewritten, where mysteries lurk in the very fabric of their existence. Today, we are embarking on a journey to the heart of these celestial enigmas. We will uncover 50 of their strangest, most mind-bending discoveries, revelations that don't just add to our knowledge, but actively challenge the foundations of what we thought we knew about the universe. This isn't just a list of facts, it's a voyage into the unknown, a deep dive into the secrets these ancient star clusters have guarded for billions of years. Think you understand how stars live and die, or how galaxies form? The truths waiting inside globular clusters will make you question everything. They contain stars that shouldn't exist, dark matter that may be missing, and dynamics so bizarre they defy our best simulations. Each discovery is a piece of a grander puzzle, a clue to understanding not only these clusters themselves, but the very story of our cosmos. So prepare to have your perspective shifted. We are about to pull back the curtain on a realm of cosmic wonder that is both beautiful and profoundly strange, a place where every glittering point of light has a story to tell, and those stories are more incredible than we ever imagined. Our very first strange discovery is perhaps the most baffling of all, a paradox that strikes at the very heart of cosmology. We find stars in globular clusters that, according to our most reliable methods of measurement, appear to be older than the universe. Let's unpack how this is even possible. Astronomers determine the age of a star primarily by looking at its composition and its position on what's called the Hertzsprung-Russell diagram, which is essentially a map of stellar life cycles. The oldest stars are those that formed when the universe was in its infancy, composed almost entirely of hydrogen and helium, the primordial elements forged in the Big Bang. They burn their fuel slowly and methodically, and by studying their brightness and color, we can estimate their age with remarkable precision. When we apply these techniques to the most ancient suns in the cores of globular clusters like M92 or NGC 6397, we get ages that are staggeringly high. Estimates often land between 13.5 and 14 billion years. The problem: the current best estimate for the age of the universe itself, derived from the Planck satellite's observations of the cosmic microwave background, is 13.8 billion years. This creates a glaring inconsistency. It would mean these stars ignited and began shining before the cosmos itself even existed. This is the ultimate chronological impossibility. So, what's really going on? Scientists are probing several fascinating possibilities. One is that our stellar evolution models, while incredibly sophisticated, might be subtly incomplete. Perhaps we're misunderstanding how stars burn their fuel in these incredibly dense environments, or maybe the initial chemical composition of these clusters was different than we assume, throwing off our age calculations. Another, more profound possibility involves our understanding of the universe's expansion. If the Hubble constant, which measures the rate of this expansion, is slightly different than we've calculated, it would directly change the calculated age of the universe. Current debates about the Hubble tension, the discrepancy between expansion rates measured locally versus from the early universe, could be the key to resolving this star age paradox. A slightly younger universe would make the ancient stars fit more comfortably within the cosmic timeline. This isn't just a minor accounting error, it's a fundamental challenge. It tells us that either our clocks for measuring stellar lives are broken, or our clock for the entire cosmos needs recalibration. The very fact that we can observe this paradox means our models are brushing up against a deeper truth we have yet to fully grasp, making these ancient star clusters the ultimate tests for our most foundational theories of physics. Moving from the profound age paradox that challenges our cosmic timeline, we encounter a discovery that completely rewrote the story of how these clusters are born. For generations, astronomers held a beautifully simple view. A globular cluster was a single, pristine entity. The theory was that each one formed in one swift, glorious burst of star formation from a single giant cloud of primordial gas. Every star within it, therefore, should have been a twin, born at the same time from the exact same material, a uniform population of ancient suns with identical chemical fingerprints. This elegant idea was a cornerstone of astrophysics for decades, but then our telescopes, particularly the powerful Hubble Space Telescope, looked closer, and this simple picture shattered into 1,000 pieces. We discovered that globular clusters are not simple at all. They are cosmic melting pots hosting not one, but multiple distinct generations of stars. This revelation of multiple stellar populations is arguably the most transformative discovery in globular cluster research in the last half-century. The evidence for this lies in the starlight itself. By dissecting the spectrum of light from individual stars within a cluster, astronomers can determine their precise chemical makeup. What they found was astonishing. While all the stars are indeed ancient, they are not chemically identical. A first generation of stars, the true primordial population, shows a chemical signature pure and simple, mostly hydrogen and helium, with only the faintest traces of heavier elements which astronomers call metals. But then, woven throughout the cluster is a second, and sometimes even a third or fourth generation of stars. These later-born stars show a clear and unmistakable chemical pollution. Their atmospheres are enriched with specific heavier elements like nitrogen, sodium, and aluminum, while curiously being depleted in others like carbon and oxygen. This particular pattern of enrichment is the crucial clue. It doesn't point to just any old source of material. It points to the nuclear furnaces of the first generation of massive stars. The only place these specific elements are forged in abundance is in the intense proton-capturing fusion cycles that occur inside massive stars, and they are then scattered into the cluster's gas when those stars end their lives in spectacular supernova explosions or through powerful stellar winds. This means the formation story of a globular cluster is far more dramatic and prolonged than we ever conceived. The narrative is no longer a single burst, but a cosmic cycle of life, death, and rebirth. It begins with that initial, rapid burst of star formation, creating the first generation. Then, the most massive of those first stars, living fast and dying young, exploded and flooded the cluster's interior with their newly forged, enriched material. This ejected gas, now mixed with the pristine gas still lingering, created a second reservoir of raw material. Gravity then pulled this enriched gas together, triggering a second wave of star formation millions of years after the first. This second generation of stars was therefore born from ashes of the first, carrying the chemical fingerprint of their ancestors. In some of the most massive clusters, this process might have even repeated again, leading to a third generation. This completely overturns the idea of a globular cluster as a simple, one-and-done event. Instead, we see them as dynamic stellar ecosystems capable of sustaining complex, internal processes of chemical enrichment and multiple rounds of birth. The very existence of these multiple populations suggests these clusters were able to retain their gas against the powerful forces that would normally blow it away, perhaps because of their immense gravity, allowing for this incredible cycle of stellar life to unfold within their dense hearts. This discovery forces us to see these glittering spheres not as static fossils, but as places with a rich and complex history of their own. This leads us to a third, deeply puzzling mystery, one that involves a cosmic crime scene where the expected evidence has somehow vanished. Given their immense age and the sheer density of stars packed into their cores, globular clusters should be the sites of frequent and spectacular stellar deaths. We're talking about ancient stellar cities where stars are constantly brushing past one another, a perfect environment for the kind of dramatic events that end stellar lives. And when the most massive stars die, they don't fade quietly. They explode as supernova, blasting their outer layers into space at incredible speeds and leaving behind an expanding cloud of superheated gas and dust, a supernova remnant. These remnants can persist for tens of thousands of years, glowing faintly as they expand and slowly mix with the interstellar medium. Logic would suggest that in these ancient clusters, we should be able to point our radio and X-ray telescopes and find a graveyard full of these glowing ghosts, the telltale signs of countless past explosions. But when we look, we find almost nothing. The expected supernova remnants are mysteriously missing. It's as if a cosmic cleanup crew has swept through and erased all the evidence. The depth of this mystery becomes clear when we consider the numbers. A typical large globular cluster contains hundreds of thousands, even millions of stars. Based on our understanding of stellar populations, a significant number of those stars would have been massive enough to end their lives as core collapse supernova early in the cluster's history. Furthermore, the dense environment should also promote the formation of white dwarfs that accrete enough material from binary companions to exceed the Chandrasekhar limit and explode as Type Ia supernova. Over billions of years, a single cluster should have produced hundreds, if not thousands, of supernova. Even if each remnant only glows for a short cosmic time, the law of averages suggests we should still be able to detect at least a few of the youngest, most recent ones. Yet, surveys across the electromagnetic spectrum from radio waves that can reveal the synchrotron radiation from high-energy electrons to X-rays that detect the million-degree gas have come up nearly empty-handed. There are a tiny handful of candidate remnants in a few clusters, but the numbers are staggeringly low compared to what the models predict. This is the missing supernova problem, and it forces us to question what is so fundamentally different about the life and death of stars inside these crowded systems. Astronomers have developed several compelling theories to explain this strange absence, and each one points to a more dynamic and violent life inside a cluster than we ever imagined. One leading idea focuses on the incredible speed at which things happen in the cluster core. In the sparse environment of our galactic neighborhood, a supernova remnant can expand relatively undisturbed for millennia. But in the core of a globular cluster, the remnant is expanding into an environment that is already filled with an intense wind from thousands of other stars, and it's constantly slamming into the dense interstellar material that might still be present. This would cause the remnant to lose its energy much faster, cooling down and fading from view in only a few thousand years instead of tens of thousands. The evidence is essentially scrubbed away on a much shorter timescale, making the remnants incredibly difficult for us to spot. Another, more radical theory involves the very nature of the stars that explode. Perhaps the initial generations of stars in these clusters weren't like the stars we see today. In the early, chemically pure universe, stars could have formed with much higher masses, monsters hundreds of times the mass of our Sun. These behemoths might have met a different fate altogether. Instead of exploding as a traditional supernova, they could have collapsed directly into a black hole, swallowing much of their outer layers and leaving behind little to no expanding remnant. If this direct collapse scenario was common, it would mean the clusters had a very different kind of fireworks show in their youth, one that left far less debris behind for us to find. A third possibility involves the ultimate fate of the remnants themselves. The incredible density of stars in a cluster core means that gravitational interactions are constant and fierce. A newly formed supernova remnant, a cloud of expanding gas, would be highly vulnerable to these forces. The gravitational tug from a passing massive star could literally rip the remnant apart, scattering its material so widely and so quickly that it simply dissipates into the general background of the cluster before it has a chance to develop the structure we recognize. It's a bit like trying to see the outline of a smoke ring in a hurricane. The organized structure is destroyed almost instantly by the chaotic environment. This missing evidence isn't just a trivial oversight. It's a profound clue that the final moments of a star's life are dramatically altered by the company it keeps, suggesting that in the crowded downtown of a globular cluster, even death is a communal affair. And just when you thought the surprises were over, we come to a discovery that reshapes our understanding of cosmic monsters and their hiding places. Deep within the seemingly serene hearts of some globular clusters, astronomers have found compelling evidence for a class of black hole that was, for a long time, almost mythical: the intermediate mass black hole. We're familiar with stellar mass black holes, the remnants of collapsed massive stars, and we know about the supermassive behemoths that lurk in the centers of galaxies. But the intermediate mass black hole, weighing in at anywhere from a few hundred to a few 100,000 times the mass of our Sun, was a missing link. Finding one is difficult because they don't emit the bright X-ray flares that often betray their smaller stellar mass cousins, which are actively feeding on gas from a companion star. So how do you find an invisible object that isn't making a lot of noise? You look for its gravitational signature. You watch the stars themselves. In clusters like Omega Centauri and Messier 15, the Hubble Space Telescope and other observatories have done exactly that, meticulously tracking the motions of individual stars near the cluster's core over many years. What they've recorded is a telltale celestial dance. These stars are whipping around the center at velocities so incredibly high, thousands of kilometers per second, that the only thing that could possibly be holding them in such a tight, fast orbit is the immense gravitational pull of a single, incredibly massive object. It's an object that emits no light, a dark anchor around which these suns are furiously swinging. By applying the same laws of gravity that keep our own planets in orbit around the Sun, astronomers can calculate the mass required to produce those observed stellar speeds. The numbers they get point unequivocally to an intermediate mass black hole, a gravitational titan sitting squarely in the mass gap between stellar and supermassive varieties. This finding is monumental because it challenges our ideas about how black holes form and grow. One leading theory suggests these intermediate black holes could be primordial, forming directly from the collapse of enormous clouds of gas in the early universe, making them truly ancient relics. Another, perhaps more dynamic, possibility is that they are the result of a runaway chain reaction of collisions and mergers inside the densely packed cluster core. In such a crowded stellar environment, black holes could sink to the center through dynamical friction, meet one another, and merge, building up mass over billions of years. The presence of these objects transforms our view of a globular cluster from a simple collection of stars into a potential nursery for building blocks of the supermassive black holes we see in galaxies today. It suggests that these clusters are not just fossils, they are active, evolving gravitational engines where the most exotic objects in the universe can coalesce and grow, hidden in plain sight. But nestled among these ancient, fading suns, we find a stellar contradiction that defies all expectation: stars that look impossibly young. These are the blue stragglers, and their very existence in a globular cluster is like finding a group of vibrant, energetic teenagers living in a retirement home for billionaires. They stand out starkly against their surroundings. While the vast majority of stars in a cluster have aged into cool, red giants or settled down as faint white dwarfs, blue stragglers are hot, brilliant, and blue, burning with a fierce intensity that belongs to a star in the prime of its life. According to everything we know about stellar evolution, these stars should have exhausted their fuel and moved on to the next phase eons ago. They are living on borrowed time, and the source of their extended youth is a tale of cosmic violence and intimate partnership. The mystery of these stars boils down to a simple question of fuel. A star's lifespan is determined almost entirely by its mass. The more massive a star is, the more fiercely it burns through its hydrogen fuel, leading a short but spectacular life. In a globular cluster, all the stars were born around the same time, so the most massive one should have been the first to die out. That's why we expect to see only lower mass, longer-lived stars remaining after billions of years. A blue straggler, by its very blue and hot nature, must be more massive than the normal, aged stars around it. It simply couldn't still be shining that brightly unless it had found a way to gain a fresh supply of hydrogen fuel, effectively hitting the cosmic reset button on its life cycle. Astronomers have converged on two primary, dramatic mechanisms that can create these stellar anomalies, and both involve a star getting a little too close for comfort. The first scenario is a story of cosmic cannibalism, a direct collision. In the incredibly dense downtown of a globular cluster core, stars are not the distant, solitary beings we know in our own galactic neighborhood. They are packed so tightly that close encounters and even direct impacts, while still rare, become statistically possible over billions of years. Imagine two older, sun-like stars, each calmly going about their lives on a gradual drift towards one another. A gravitational nudge from a passing star can alter their paths just enough to send them on a fateful course. They don't simply bounce off each other. Their immense gravity pulls them together in a cataclysmic merger. When two stars collide, their cores and gaseous envelopes violently mix, creating a single, new, more massive star. This newly formed star is now composed of fresh hydrogen from the outer layers of both its progenitors, fuel that was previously untapped. It ignites this new reservoir with the vigor of a much younger star, blazing hotter and brighter than either of its parents ever did. This stellar phoenix, born from a violent union, appears as a brilliant blue straggler, its youth stolen from the wreckage of a cosmic crash. The second path to rejuvenation is slower, more methodical, and reveals the complex dynamics of binary star systems. Many stars in the universe are born in pairs, and globular clusters are no exception. In this scenario, two stars are locked in a gravitational embrace, orbiting one another. One of the stars, slightly more massive, will age faster. As it exhausts its hydrogen core, it begins to swell into a red giant. If the two stars are close enough, the expanding giant can literally spill its outer layers onto its smaller companion. This process, called mass transfer, is a gravitational siphon on a cosmic scale. The smaller star greedily accretes this fresh hydrogen, its mass steadily increasing. With this new fuel, it is effectively reborn, its fusion reignited to that of a younger, hotter blue star. The original donor star, having lost its outer envelope, is left as a tiny, fading ember, a white dwarf. We are left with a bizarre pairing, a hot, massive blue straggler and the tiny, dense remnant of the star that gave it new life. This process is so efficient that it can completely alter the appearance and fate of a star, allowing it to masquerade as a youthful interloper in a city of ancient suns. The presence of blue stragglers is therefore a direct testament to the dynamic and often violent interactions that shape life inside these crowded star clusters. They are not a puzzle to be solved, but rather a clear signal that in the cosmos there is more than one way to grow old. While we have been exploring the visible and the ultra-dense, our next discovery comes from a completely different, invisible spectrum of light, revealing that globular clusters are not just visually stunning, but are also cosmic powerhouses of the most energetic radiation in the universe. For decades, we studied these clusters in optical light, radio waves, and X-rays, building a picture of ancient stars and dynamic interactions. But then NASA's Fermi Gamma Ray Space Telescope turned its gaze toward them, and it detected something entirely unexpected. A faint but distinct glow of high-energy gamma rays emanating from several globular clusters. This was a profound surprise. Gamma rays are the most energetic form of light, typically produced by the most violent and extreme processes in the cosmos, like supernova explosions, jets from active black holes, or the annihilation of subatomic particles. To find this signal coming from these supposedly serene, ancient stellar cities was like discovering a hidden nuclear reactor inside a historic monument. It immediately presented a high-energy puzzle. What on Earth, or rather, what in the heavens, could be producing this immense power within these clusters? The search for the source of these gamma rays has led astronomers to two primary and equally fascinating suspects. The first, and the current leading candidate, is a dense population of rapidly spinning neutron stars known as millisecond pulsars. A pulsar is the ultra-dense, magnetized core of a star that went supernova, spinning rapidly and beaming out radiation like a cosmic lighthouse. A millisecond pulsar is a special kind that has been spun up to incredible speeds, completing hundreds of rotations every single second. How does a pulsar get spun up so dramatically? The answer lies in the very binary interactions we discussed with blue stragglers. In a globular cluster, a neutron star can often have a companion star. As the companion evolves and expands, it can transfer mass onto the neutron star. This infalling material doesn't just fall, it carries with it a tremendous amount of angular momentum, effectively stoking the neutron star and causing it to spin faster and faster until it reaches those mind-boggling millisecond periods. These pulsars are capable of accelerating charged particles to near the speed of light, and when these particles interact with magnetic fields or ambient light, they can produce the precise type of gamma ray emission that Fermi detects. Given that a single globular cluster could be home to hundreds or even thousands of these millisecond pulsars, their combined faint emission could easily add up to the diffuse gamma ray glow we observe. They are the invisible high-energy engine of the cluster, a buzzing hive of spun-up stellar corpses. However, there is a second, more exotic possibility that adds a layer of profound mystery to this signal: dark matter annihilation. We've discussed the missing dark matter problem in globular clusters, the fact that they don't seem to contain the vast halos of this invisible material that galaxies do. But what if, in the incredibly dense cores of these clusters, dark matter particles are crowded together so tightly that they are constantly colliding with one another? According to some theories, when two particles of dark matter meet, they could annihilate each other, converting their mass directly into pure energy in the form of gamma rays. If this is true, then the gamma ray signal from a globular cluster isn't just a byproduct of stellar remnants. It is a direct glimpse into the invisible universe, the first potential evidence of dark matter particles revealing themselves through their own self-destruction. This makes the gamma ray glow a double-edged sword. It could be a confirmation of our understanding of stellar evolution and the prevalence of millisecond pulsars, or it could be one of the most significant discoveries in modern physics, a direct detection of the universe's dominant yet most elusive component. The ongoing investigation is a masterclass in astronomical detective work. Scientists are trying to distinguish between these two scenarios by looking at the specific details of the gamma ray signal. For instance, if the emission is coming from a collection of many point sources like pulsars, then with extremely high-resolution observations, we might eventually be able to resolve individual blinking pulsars within the glow. Some recent studies have indeed managed to identify a few specific millisecond pulsars contributing to the signal in certain clusters, bolstering that case. On the other hand, if the emission is smooth, diffuse, and centered perfectly on the cluster's core in a way that can't be explained by known pulsar populations, the dark matter hypothesis gains traction. The truth may well be a mixture of both, with pulsars responsible for a large portion of the emission, but a tantalizing excess pointing toward something more. This unexpected gamma-ray signature has fundamentally transformed globular clusters from being merely astronomical objects into natural laboratories for particle physics. They provide a unique environment to test theories about the most extreme states of matter in the form of pulsars, and simultaneously probe the fundamental nature of the dark matter that shapes the entire cosmos. Yet another discovery shows us that globular clusters are not the isolated, unchanging islands they appear to be. They are actively being dismantled by the immense gravitational pull of our galaxy, a slow-motion demolition that paints the sky with traces of their orbital history. These are the tidal tails and stellar streams, vast, river-like structures of stars that stretch for thousands of light years across the galactic halo, often far beyond the visible boundary of the cluster itself. Imagine a comet's tail, but made not of ice and dust, but of countless suns stripped away over billions of years. These streams are incredibly faint and difficult to detect, a ghostly signature against the black of space. It's only with the advent of massive digital sky surveys like the Sloan Digital Sky Survey and the Gaia Space Observatory that we've been able to map these structures in their full, breathtaking extent. The process that creates them is a relentless gravitational tug of war. As a globular cluster orbits the Milky Way, it doesn't follow a perfectly smooth path. It plunges in and out of the galactic plane and swings around the dense central bulge. During these close passages, the difference in the galaxy's gravitational pull on the near side of the cluster versus the far side becomes significant. This difference, known as a tidal force, acts to stretch the cluster. It's the same force that the Moon exerts on Earth's oceans to create the tides, but on a vastly larger and more destructive scale. With each galactic orbit, this tidal tug pulls a few more stars loose, primarily from the outer, more weakly bound regions of the cluster. These ejected stars don't just fly off randomly, they continue to orbit the galaxy on paths very similar to the parent cluster's own orbit. Over countless orbits, these escaping stars accumulate, forming two long, trailing streams, one ahead of the cluster and one behind it, tracing its path through space like cosmic breadcrumbs. The properties of these streams tell a detailed story. The length and density of a tail reveal the age of the process and the original mass of the cluster. A long, well-populated stream suggests an ancient cluster that has been losing stars for a very long time, while a short, faint tail might indicate a more recent or less dramatic stripping event. Furthermore, the specific shape and width of the stream are exquisitely sensitive to the distribution of dark matter in the Milky Way's halo. As the stream of stars orbits the galaxy, the gravitational field of the dark matter halo subtly sculpts its path. By mapping the precise contours of a stellar stream, astronomers can effectively reverse engineer the gravitational forces that shaped it, allowing them to chart the invisible dark matter landscape of our galaxy. This turns globular cluster streams into powerful forensic tools. They are not just evidence of destruction, they are dynamic maps that record the history of the cluster's interactions with the galaxy. By studying the Palomar 5 stream, for instance, we can reconstruct its orbital history and predict its future demise. The cluster itself is now a pale, wispy remnant, having lost a vast majority of its stars to its spectacular tails. In a few more orbits, the cluster core may dissolve completely, leaving only the stream behind as a monument to its former existence. This process shows us that globular clusters are not permanent fixtures. They have a life cycle, and their gradual dissolution is an integral part of the galactic ecosystem, seeding the galactic halo with stars and providing us with an unparalleled tool for understanding the hidden structure of our cosmic home. Just when we thought we understood the limits of where planets could form, globular clusters presented us with another stunning contradiction. For a long time, the prevailing wisdom was straightforward and seemingly unassailable. Planets could not exist in these dense stellar cities. The reasoning was sound. Planet formation is a delicate and precarious process. It requires a stable, quiet protoplanetary disk of gas and dust to swirl around a young star for millions of years, allowing dust grains to gently clump together, eventually building up into planetesimals and finally full-fledged planets. Now, imagine trying to perform this delicate assembly in the middle of a chaotic, densely packed metropolis. In the core of a globular cluster, stars are not light years apart. They can be as close as our solar system is wide. A neighboring star wandering too close would have a catastrophic gravitational effect on that fragile disk. It could strip away the raw material before planets even begin to form, or gravitationally fling any nascent protoplanets out into the cold darkness of interstellar space. The environment was considered so hostile, so disruptive, that the very idea of a stable, long-lived planetary system like our own surviving for billions of years in such a place was dismissed as sheer fantasy. It was the ultimate real estate nightmare, too crowded, too unstable, and far too dangerous for something as fragile as a world to take root. This is why the discovery of PSRB 1620-26 in the globular cluster Messier 4 was nothing short of revolutionary. Astronomers weren't even looking for planets. They were studying a pulsar, the rapidly spinning corpse of a massive star. By meticulously timing the precise flashes of its lighthouse-like beam, they detected tiny, regular anomalies, a slight wobble in the pulsar's rhythm. The only plausible explanation was the gravitational tug of not one, but at least two planetary mass objects orbiting it. Here was definitive proof. Planets could and did exist in one of the oldest, most chaotic environments in the galaxy. This discovery shattered the old paradigm completely. It forced a radical rethinking of planetary resilience and the processes of formation itself. If planets could survive here, then they might be even more ubiquitous in the universe than we ever dared to hope. The existence of these planets opens up a fascinating detective story about their origins, because the path to their creation is likely as violent as their surroundings. We can envision two primary dramatic scenarios. The first is a story of second-generation birth, a true phoenix rising from the ashes. The pulsar they orbit is the clue. A pulsar is formed in the supernova explosion of a massive star. That catastrophic event should have vaporized any pre-existing planets that might have been orbiting the original star. So how did new planets form? The leading theory suggests that the supernova explosion, while destroying the original system, also provided the raw material for a new one. The explosion would have created a new disk of material around the young pulsar, formed from the debris of the shattered companion star or from material falling back after the blast. From this disk of stellar remains, a new second generation of planets could have coalesced. These would not be rocky worlds like Earth, born from the gentle coalescence of primordial dust. They are likely exotic, diamond-rich worlds forged in the furnace of a stellar explosion, orbiting a dead star. The second possibility is even more dynamic and highlights the strange social dynamics of a globular cluster. It's a tale of planetary theft or adoption. In the crowded core, a star with its own planetary system could have a close encounter with a solitary pulsar. The complex gravitational dance during this flyby could have ripped a planet right out of its original orbit around its parent star and sent it careening into a new, bound orbit around the pulsar. Alternatively, a free-floating planet, a rogue world already ejected from some other system, could have been captured by the pulsar's gravity during a close pass. This means the planets we see might not be native to their current star. They could be cosmic orphans adopted by the pulsar after a chaotic gravitational exchange. The very fact that we have to consider such extraordinary origins shows just how different the rules are inside a globular cluster. Planet formation isn't always a quiet, solitary affair. In these dense environments, it can be a communal, violent, and recycled process. The survival of these worlds against all odds suggests that planets are not just delicate flowers, but can be tenacious weeds capable of taking root in even the most unforgiving cosmic soil. And this brings us to a truly dense population of cosmic power plants hidden within these clusters, the astonishing overabundance of millisecond pulsars. To appreciate just how strange this is, we first need to understand what a pulsar is in its natural state. When a massive star explodes in a supernova, its core can collapse into a neutron star, an object so incredibly dense that a single teaspoon of its material would weigh billions of tons. This newborn neutron star is often born spinning wildly, sometimes dozens of times per second, and with an immense magnetic field. As it rotates, it beams out radiation from its magnetic poles, and if that beam sweeps across Earth, we detect it as a precise, repeating pulse, a pulsar. Left to its own devices, a pulsar is a cosmic whirring top that slowly loses energy, its spin gradually winding down over millions of years until its pulses become feeble and slow. But in the social chaos of a globular cluster, a pulsar doesn't have to face a lonely, slow decline. It can get a second lease on life, a cosmic reboot that transforms it into something far more extreme. This process is called recycling, and it hinges on the pulsar having a binary companion. In the crowded core, stellar encounters often pair stars together, and a pulsar is no exception. Imagine a pulsar with a normal, sun-like star as its partner. As that companion star ages, it swells into a red giant. If the two are close enough, the pulsar's fierce gravity begins to pull material from the outer layers of the giant star onto itself. This isn't a gentle flow, it's a torrent of gas spiraling onto the pulsar's surface. Crucially, this incoming material carries a huge amount of angular momentum. It's like throwing a rope around a spinning top and pulling it, forcing it to spin faster and faster. Over hundreds of millions of years, this process can accelerate the pulsar's rotation from a few dozen times per second to an almost incomprehensible several hundred times per second. We call these reborn objects millisecond pulsars, and they are the most perfectly accurate clocks in the universe. Their pulses so regular they can rival atomic clocks. Now, here's the truly baffling part. The number of these hyper-spinning relics we find in globular clusters is wildly out of proportion with the rest of the galaxy. A single, massive cluster like Terzan 5 or 47 Tucani can contain hundreds of these millisecond pulsars. To put that in perspective, the entire sprawling disk of our Milky Way galaxy, with its hundreds of billions of stars, has only confirmed a few hundred millisecond pulsars in total. Globular clusters, which make up a tiny, tiny fraction of the galaxy's stellar population, somehow host a massively disproportionate share of them. This isn't a slight overabundance, it's a glaring statistical anomaly that points directly to the unique, dynamic environment of the cluster itself. The reason for this pulsar bonanza boils down to two key factors: opportunity and longevity. First, the opportunity for stellar encounters and binary formation is immensely higher in the densely packed core of a cluster. Stars are constantly interacting, exchanging partners, and creating the very binary systems necessary for the recycling process to occur. A pulsar born in the galactic field might never find a companion to provide it with the needed mass transfer, doomed to spin down alone. But in a globular cluster, finding a partner is almost a certainty. Second, these millisecond pulsars, once formed, are incredibly stable and long-lived. They spin so efficiently that they can keep pulsing for billions of years with very little slowdown. Since globular clusters are themselves ancient, they have had ample time to accumulate these recycled pulsars over many cosmic epochs. They are like a cosmic museum that not only preserves ancient stars but also collects and maintains these hyper-spun relics, creating a dense population that exists nowhere else. This overabundance is more than just a curiosity. It provides a direct window into the dynamic interaction history of the cluster and helps explain other mysteries like the faint gamma-ray glow we discussed earlier, as the combined emission from hundreds of these invisible cosmic lighthouses, all spinning in the dark heart of a stellar city. Building on the idea of complex stellar life cycles within these clusters, we come to a discovery that is written not in the light of the stars, but in their very atomic makeup. If you could take a core sample from a star in a globular cluster, you would find a bizarre and specific chemical fingerprint that defies the simple composition of a typical ancient star. This signature is a strange and imbalanced recipe, a noticeable enhancement of elements like helium, nitrogen, and sodium, curiously paired with a depletion of others, particularly carbon and oxygen. It's as if someone took the primordial stellar gas and ran it through a specialized cosmic filter, removing some ingredients and concentrating others. This isn't a random pattern. It's the direct and unmistakable evidence of a sophisticated nuclear processing chain that can only occur inside stars, and it provides the final, conclusive proof of the multiple generation story we touched on earlier. These unusual abundances are the forensic evidence of cosmic pollution on a grand scale, showing that the later generations of stars were literally built from the ashes of their ancestors. To understand how this works, we need to step inside the heart of a massive first-generation star. These pioneering stars, known as population 3 stars, were behemoths many times more massive than our Sun and composed of almost pure hydrogen and helium. Deep in their searingly hot cores, where temperatures reach millions of degrees, nuclear fusion is the engine of their life. The first step in this chain is the proton-proton chain, which fuses hydrogen into helium. This is the same process that powers our Sun, but in these much more massive and hotter stars, a more efficient cycle called the CNO cycle takes over as the dominant way to burn hydrogen. The CNO cycle, which stands for carbon, nitrogen, oxygen, uses these heavier elements as nuclear catalysts. A nucleus of carbon-12, for instance, will sequentially capture 4 protons, turning into nitrogen-14, then oxygen-15, and finally, after a decay, back into carbon-12, having effectively converted 4 hydrogen nuclei into 1 helium nucleus in the process. The key point is that the catalysts are recycled. However, in the real, imperfect conditions of a stellar interior, the cycle doesn't run with 100% efficiency. Some of the intermediate products get siphoned off. In particular, nitrogen-14 tends to accumulate, as it is a relatively stable isotope. Meanwhile, at even higher temperatures in a shell surrounding the core, a process called helium capture begins. Here, helium nuclei are fused onto existing heavier elements. When a carbon nucleus captures a helium nucleus, it becomes oxygen. But if the conditions are just right specifically at very high temperatures, a different chain can dominate. In this hot helium-burning shell, a neon-sodium cycle can occur, where neon captures a proton to become sodium. Simultaneously, oxygen can be depleted as it captures helium to create other elements. This complex suite of nuclear reactions operating in different layers of the star creates a very specific chemical output, a gas that is enriched in helium from the core hydrogen burning, enriched in nitrogen from the CNO cycle, and enriched in sodium from the hot helium burning, while being depleted in carbon and oxygen as those elements are used up in the various cycles. The crucial next step is getting this processed material out of the star and into the cluster's reservoir of gas. This doesn't necessarily require a cataclysmic supernova, though that is one way. For the intermediate mass stars that are responsible for this specific chemical pattern, the primary delivery mechanism is through powerful, steady stellar winds. As these stars evolve into red giants, they blow off their outer layers into space. These winds are essentially the star gently shedding its own atmosphere, carrying this nuclearly processed material, now enriched with extra helium, nitrogen, and sodium, and depleted in carbon and oxygen, and polluting the shared interstellar environment of the entire globular cluster. This ejected gas then mixes with whatever pristine hydrogen and helium remains from the cluster's initial formation. When gravity eventually triggers a second wave of star formation, this new generation of stars condenses from this already polluted gas cloud. They are therefore born with this strange chemical signature already imprinted in their DNA. They don't have to create these elements themselves, they inherit them. This is why we see stars that are chronologically ancient, but chemically look like they've been contaminated by the life and death of other stars that came before them. The pattern is so consistent and distinct from the chemical makeup of stars in the general galactic field that it serves as the definitive marker of a globular cluster's unique and complex history, a chemical fossil record of the dramatic lives and deaths of the very first stars to call that cluster home. This brings us to a quieter, more subtle mystery, one that involves a population of missing residents. When astronomers calculate the kinds of stars that should be present in a globular cluster, they rely on a fundamental principle known as the initial mass function. This is essentially a cosmic census that predicts how many stars of each mass will form from a given cloud of gas. Think of it like a bell curve for stellar birth. The universe has a strong preference for making vast numbers of low-mass, small, dim stars, the red dwarfs, and far fewer of the brilliant, high-mass giants. This ratio is remarkably consistent across the Milky Way, from our own galactic neighborhood to distant star-forming regions. So, when we look at an ancient globular cluster, we naturally expect to see this same distribution, only skewed toward the lower masses because all the high-mass stars have long since died off. The clusters should be absolutely teeming with these faint red dwarf stars, vastly outnumbering every other type. But when we point our most sensitive telescopes to take a precise stellar head count, the numbers don't add up. In many clusters, there is a clear and puzzling deficit of these low-mass stars. A significant portion of the cluster's smallest, faintest members are simply gone, vanished without a trace. It's as if someone went through a vast forest and systematically removed a specific type of sapling, leaving the older trees behind. This missing population forces us to confront a brutal truth about life in a dense stellar city. It's a dangerous place to be small and weak. The explanation for this stellar evaporation lies in the relentless and impersonal mechanics of gravitational dynamics. Over billions of years, a globular cluster acts like a vast, self-stirring gravitational system, constantly seeking a state of equilibrium. Stars are perpetually jostling and interacting, and in this cosmic game of pool, energy is constantly being exchanged. The primary mechanism at work is a process called two-body relaxation. As stars swing past one another, their gravitational pulls alter each other's orbits. In these exchanges, there's a tendency for kinetic energy to be shared around the system in a specific way. More massive stars tend to lose speed and sink towards the center of the cluster, a process known as mass segregation. Meanwhile, the lighter, low-mass stars often get a gravitational boost, gaining energy and velocity. Imagine a crowded dance floor where the larger, more powerful dancers gradually work their way to the center, while the lighter, more nimble dancers get bumped and nudged toward the edges, sometimes with so much force that they're flung right out of the room entirely. That's precisely what happens in a globular cluster. Over countless millions of years, these gravitational interactions steadily heat up the low-mass stellar population, pumping energy into their orbits until they reach the escape velocity of the entire cluster. Once a star reaches that critical speed, it breaks free from the cluster's gravitational grip entirely, sailing off into the lonely expanse of the galactic halo to become a rogue star. This is a slow, inexorable process of evaporation where the cluster is constantly shedding its lowest mass members. There is, however, another powerful force contributing to this stellar loss, acting from outside the cluster. This is the galactic tide we discussed earlier, As the cluster orbits the Milky Way, the differential gravitational pull from our galaxy doesn't just create tidal tails, it also makes it dramatically easier for stars to be stripped away. The cluster's gravitational hold is weakest at its outer edges, and the galactic tide effectively lowers the energy required for a star to escape. The stars that are already on the verge of being ejected through internal dynamics, those low-mass stars that have been gravitationally heated up, find it almost effortless to drift away when they reach these vulnerable outer regions. The combination of internal kinetic heating and external tidal stripping creates a highly efficient stellar removal service, one that disproportionately targets the smallest and lightest stars. They are the ones with the least gravitational anchoring, making them the easiest to eject in any dynamical encounter. This process fundamentally alters the cluster's demographic makeup. What we see today is not the initial population, but a filtered and evolved one, a community that has been shaped by billions of years of gravitational selection, where only the more resilient, or at least the more massive, stars have managed to remain. This missing starlight is therefore a direct record of the cluster's dynamical age and its past orbital history, a silent testament to the countless faint suns that have been cast adrift over the eons. Now we arrive at a discovery that seems to defy one of the most fundamental concepts in modern cosmology, creating a stark divide between globular clusters and the galaxies they orbit. When we observe the universe at large, from the smallest dwarf galaxies to the largest spiral behemoths, we find overwhelming evidence for dark matter. This invisible substance, which does not emit or absorb light, reveals its presence through its immense gravitational pull. We see its effects in the way stars orbit the centers of galaxies far too quickly for the visible mass to hold them in, and in the way galaxy clusters bend light with a strength that their luminous material alone could never provide. Dark matter appears to be the cosmic scaffolding upon which galaxies are built, an essential ingredient in their formation and stability. So, when we turn our attention to globular clusters, these massive, gravitationally bound spheres of up to 1 million stars, the logical assumption would be that they, too, must be embedded within their own hefty halos of dark matter. Their sheer mass and stability over billions of years seem to demand it. Yet, when astronomers meticulously measure the motions of stars within these clusters to weigh them, they are met with a profound and consistent surprise. The numbers add up. The observed gravitational pull, the force that keeps these stars whirling in their tight orbits, is almost entirely accounted for by the collective mass of the stars we can see. There is no significant gravitational surplus, no missing mass. Globular clusters, it appears, contain little to no dark matter whatsoever. This isn't just a minor discrepancy. It's a cosmic identity crisis that forces a complete re-evaluation of what these objects are and how they came to be. This conclusion is drawn from a classical technique in astronomy known as dynamical mass measurement. By carefully studying the velocities of stars as they orbit within the cluster, specifically how their speeds change with distance from the center, scientists can construct a model of the cluster's gravitational potential. This model tells them the total mass required to produce the observed stellar motions. They can then independently estimate the mass in visible stars by measuring the cluster's brightness and applying well-understood relationships between a star's light and its mass. In every well-studied globular cluster, these two numbers, the dynamical mass and the luminous mass, are in near-perfect agreement. The stars are moving precisely as fast as they should be if they were only being pulled by the gravity of other stars. There is no room in the budget for a dominant, unseen component. This stands in breathtaking contrast to a typical dwarf galaxy of similar stellar mass, where the dynamical mass can be 10, 100, or even 1,000 times greater than the mass in visible stars, compelling evidence for a massive, enveloping dark matter halo. This stark difference is a vital clue pointing towards two radically different formation histories. The prevailing theory for galaxy formation, known as the bottom-up or hierarchical model, posits that dark matter halos formed first in the early universe. These halos acted as gravitational traps, pulling in ordinary gas which then cooled and fragmented to form stars, giving birth to galaxies. In this picture, a galaxy and its dark matter halo are inextricably linked from birth. Globular clusters, however, seem to have followed a different path. The leading explanation is that they formed not within their own private dark matter halos, but as compact, dense pockets of gas within the much larger, turbulent disks of the primordial galaxies that would become the Milky Way and others. Imagine the early universe as a vast, chaotic sea of gas and dark matter, where the first giant galaxies are beginning to take shape. Within these colossal structures, immense pressures from colliding gas flows, shock waves from early supernova, or gravitational instabilities could have triggered the collapse of particularly dense knots of pristine gas. These knots, collapsing under their own gravity and free from the need for a dark matter anchor, would have undergone an incredibly efficient and rapid burst of star formation, creating a tightly bound spherical stellar system from the very beginning. Because they formed from the ordinary, baryonic matter already within the galactic disk, they would have inherited the orbital dynamics of that gas with no private dark matter halo of their own. They are, in essence, purely stellar entities born from the luminous material of their parent galaxy. This distinction solves one mystery but inadvertently creates another, even more tantalizing one. If globular clusters are truly devoid of dark matter, then they become the ideal natural laboratories in our quest to understand what dark matter actually is. Many leading candidates for dark matter, such as weakly interacting massive particles or WIMP, predict that these particles can occasionally interact with each other, annihilating and producing a shower of gamma rays. Astronomers often look for this signal in places where dark matter is thought to be densely concentrated, like the centers of dwarf galaxies. However, there's a complicating factor. Other astrophysical processes, like the collective emission from millisecond pulsars we discussed earlier, can also produce gamma rays. This creates a problematic background, making it difficult to definitively attribute any observed signal to dark matter. But a globular cluster, with its high density of stars and apparent lack of dark matter, provides the perfect control experiment. If we see a gamma-ray signal from a dwarf galaxy, we can't be sure of its origin. But if we see a similar signal from a globular cluster where dark matter is absent, then we can be much more confident that the source is astrophysical, like those pulsars, and not particle annihilation. By comparing the two, we can isolate and constrain the properties of dark matter with far greater precision. The absence of dark matter in these clusters, therefore, isn't a void in our understanding. It's a powerful, clean slate that allows us to test the limits of physics in a way that few other cosmic objects can. But just as we've settled into the idea of globular clusters as exclusively ancient fossils, the universe presents us with a brilliant contradiction. In a handful of nearby galaxies, astronomers have found clusters that possess all the classic hallmarks of a globular. They are massive, densely packed and spherical, but they are not old. They are stellar teenagers, some barely a few 100 million years old, shining with a vibrant bluish light that speaks of recent, ferocious star formation. This discovery of so-called young globular clusters completely shatters the monolithic view that all these objects are relics from a single, primordial era. It tells us that the recipe for building a globular cluster is not a secret locked away in the early universe. It is a process that can and does happen repeatedly across cosmic time whenever the conditions are just right. The most famous and stunning examples of this phenomenon are found in the Antennae galaxies, a spectacular pair of spiral galaxies currently in the throes of a violent collision. When the Hubble Space Telescope focused on this cosmic wreck, it didn't just see chaos, it witnessed a fireworks display of star birth on an almost unimaginable scale. Dotting the tangled spiral arms and the bridge of material between the two galaxies are thousands of brilliant blue star clusters. Many of these are so massive and compact that they meet every definition of a globular cluster, except for one crucial factor: their age. Spectroscopic analysis reveals they are composed of hot, massive young stars, their light telling a story of formation that coincided almost directly with the galactic collision itself. This provides the critical clue to their origin. The immense pressures and shockwaves generated as the two galaxies tear into each other are compressing vast clouds of gas to extraordinary densities, triggering starbursts so intense that they can forge these massive, bound clusters in a single, rapid burst. These are not the quiet, gentle nurseries where stars are born one by one. These are stellar factories operating at maximum capacity, creating hundreds of thousands of stars at once in a region of space that gravity then ties together into a permanent spherical family. This revelation forces a dramatic expansion of the globular cluster family tree. We now understand that there are at least two distinct populations. The classic ancient globulars that orbit our Milky Way belong to what astronomers call the Old Halo population. They are the first-generation pioneers, forming during the universe's most fecund period for cluster creation, a time when the cosmos was smaller, gas was more plentiful, and the conditions for such intense star formation were ubiquitous. The young globulars, on the other hand, represent a later generation population. They are proof that the universe can still muster the extreme conditions necessary to build these objects, but it requires a truly catastrophic trigger. The primary engine for this modern-era cluster formation appears to be major galactic mergers and intense, localized starbursts. The violence of such events replicates the high-pressure, high-density environment of the early universe, providing a temporary window for the formation of new globulars long after the main epoch of their creation has passed. This discovery does more than just add a new category to our astronomical catalogues. It provides a powerful and direct link between the distant past and the present-day universe. It suggests that the majestic globular clusters we so revere in our own galaxy were likely born in similar environments of utter chaos and violence during the Milky Way's own tumultuous assembly period billions of years ago. We are essentially witnessing, in real time in other galaxies, the very processes that built our own cosmic neighborhood. The young globular clusters in the antennae galaxies are a living fossil, not of the stars themselves, but of the formation mechanism. By studying them, we can watch the entire life cycle of a globular cluster from its fiery birth, giving us unprecedented insight into the initial conditions, the rapidity of star formation, and the early dynamical processes that were, until now, only theoretical for the ancient clusters we see nearby. This bridges a critical gap in our understanding, transforming globular clusters from static snapshots of a bygone era into dynamic players in the ongoing, evolving story of galaxy growth and interaction throughout cosmic history. This brings us to a discovery that fundamentally challenges the very definitions we use to categorize cosmic objects, blurring the line between a star cluster and a galaxy in a way that forces us to rethink our entire classification system. For generations, astronomers operated with a seemingly clear distinction. A globular cluster was a dense, spherical collection of stars orbiting a galaxy as a satellite. A dwarf galaxy was a much larger, gravitationally bound system that could contain its own dark matter halo, gas, dust, and complex structures. The separation appeared clean, based on size, mass, and composition. But then, in the late 1990s, as surveys of the nearby Virgo and Fornax galaxy clusters became more detailed, astronomers stumbled upon a class of objects that didn't fit neatly into either box. These were the ultra-compact dwarf galaxies, or UCT, and their discovery created an identity crisis in the cosmos. At first glance, they look exactly like very massive globular clusters, tiny, round, and intensely bright points of light. But when astronomers measured their properties, they found something entirely new. These objects are typically only about 200 light-years across, which is minuscule for a galaxy, but they pack an astonishing number of stars into that volume, often reaching masses of tens of millions of suns. This makes them far more massive than even the largest globular clusters, yet far more compact than any known dwarf galaxy. They occupy a strange middle ground, a cosmic no-man's land between two established classes, forcing us to ask, what exactly are they? The mystery deepens when we look at their internal composition and dynamics. The key piece of evidence comes once again from weighing them. When scientists measured the velocities of stars within these ultra-compact dwarfs, they found something that set them apart from every known globular cluster. Many of them contain a significant amount of dark matter. The stars are moving so quickly that the mass in visible stars alone cannot explain their motions. This is the classic signature of a galaxy, not a star cluster. We now recall our previous discussion where classic globular clusters show no evidence for dark matter. Their gravity is accounted for by their stars. The fact that many ultra-compact dwarfs do have this dark matter component is a game changer. It suggests that they are not merely overgrown star clusters, but rather the dense, stripped-down corpses of what were once much larger dwarf galaxies. This leads to the compelling and dramatic theory of their origin, a tale of cosmic violence and gravitational stripping. The most widely accepted explanation paints a vivid picture of galactic evolution. Imagine a small but normal dwarf spheroidal galaxy, perhaps 1,000 times less massive than the Milky Way, orbiting a much larger galaxy in a dense cluster like Virgo. As this dwarf galaxy makes repeated close passes near the giant galaxy at the cluster's heart, it experiences immensely powerful tidal forces. These forces act like a cosmic cheese grater, relentlessly pulling and tearing at the dwarf galaxy. The process is brutally efficient but selective. The stars and dark matter in the galaxy's outer, loosely bound halo are the first to be stripped away, stretching into long, faint streams that eventually dissolve into the intracluster medium. What remains after this gravitational assault is only the galaxy's very heart, its dense, compact nucleus, which was far too tightly bound for the tides to disrupt. This surviving core, having lost its fluffy outer envelope, is what we now observe as an ultra-compact dwarf. It retains the original dark matter halo of its progenitor, but now concentrated into an incredibly small volume, which explains the high measured masses and stellar velocities. In this scenario, ultra-compact dwarfs are the galactic equivalents of a shipwreck's black box, the indestructible core that survives a catastrophic event, holding within it clues to a much larger structure that has since been destroyed. However, the story may not be so simple, and this is where the classification becomes even more intriguing. There is another compelling pathway for their formation, one that links back to the globular cluster family. Some astronomers propose that the very largest ultra-compact dwarfs could be the product of a different kind of violence, the merger of multiple massive globular clusters. In the dense central regions of galaxy clusters, where thousands of globular clusters swarm, it is possible for them to dynamically interact and merge into a single, more massive object. This globular cluster merger model suggests that some UCDs could be built from the bottom up through the amalgamation of smaller, dark matter-free star clusters. If this is true, then the ultra-compact dwarf population might actually be a mixed bag, containing both the stripped nuclei of true galaxies and the superclusters formed from mergers. This dual origin hypothesis perfectly encapsulates why these objects are so revolutionary. They demonstrate that the universe can produce objects of similar appearance through completely different evolutionary pathways that converge on this strange middle ground. Their very existence forces us to abandon our rigid categories and accept a more fluid, continuous spectrum of cosmic structures, where the difference between a giant cluster and a tiny galaxy is not a bright line, but a blurred and fascinating frontier. Buried within the seemingly random distribution of starlight in a globular cluster is a subtle but incredibly powerful feature, a bend in the curve of stellar brightness that astronomers call the luminosity function Ni. To understand its significance, you first have to picture what the luminosity function is. If you were to count all the stars in a cluster and sort them by their intrinsic brightness, from the brilliant giants to the faintest dwarfs, you'd create a graph. On one axis, you have the number of stars, and on the other, their magnitude or brightness. For most of its range, this graph follows a smooth, predictable slope. There are always far more faint, low-mass stars than bright, massive ones, but at a very specific, faint level of brightness, this smooth slope abruptly bends. It forms a distinct Ni, a point where the number of stars at that brightness is noticeably different from the simple, straight-line prediction. This isn't a random statistical fluke. It's a fundamental signpost in the life cycle of stars, and it has become one of astronomy's most reliable cosmic yardsticks. The reason this Ni exists is tied directly to the physics of how stars burn their fuel. A star's brightness and color are determined by its mass. For the vast majority of a star's life, it fuses hydrogen into helium in its core, residing on what's known as the main sequence. The lower a star's mass, the longer it takes to use up its hydrogen, and the fainter and redder it glows. The luminosity function Ni marks the precise point on the main sequence where a star has just enough mass to have been burning hydrogen for the entire age of the cluster. Stars more massive than this Ni point have already exhausted their core hydrogen and have moved off the main sequence, evolving into the giant branch. Stars less massive than this point are still faithfully burning hydrogen in their cores. Therefore, the location of the Ni in terms of brightness is a direct clock. It tells us the age of the cluster with remarkable precision. An older cluster will have a Ni at a fainter brightness because only the very lowest mass, slow-burning stars are left on the main sequence. A younger cluster will have a Ni at a brighter level because stars of a higher mass are still in their long, stable hydrogen-burning phase. By finding this bend in the curve and measuring its brightness, astronomers can effectively read the cluster's birth date. This makes the luminosity function Ni an excellent standard candle for measuring distances to globular clusters themselves, and by extension to the galaxies they orbit. Here's how this cosmic geometry works. We know from stellar evolution theory exactly how bright a star at the Ni should be for a cluster of a given age and chemical composition. It has a known, predictable intrinsic luminosity, but when we observe the cluster, that star appears much dimmer to us here on Earth. By comparing how bright the Ni star should be to how faint it actually appears, we can calculate precisely how much the light has dimmed on its journey through space. The amount of dimming follows a simple, well-understood mathematical law related to distance. This allows us to derive a highly accurate distance to the cluster. It's a more robust method than relying on a single, variable type of star like a Cepheid variable, because the Ni is a feature of the entire stellar population, a statistical average that smooths out individual peculiarities. By using the Ni to measure the distances to globular clusters scattered throughout the Milky Way's halo, we've been able to map the three-dimensional structure of our own galaxy and gauge the vast scale of our galactic neighborhood. But the story of the Ni doesn't end with age and distance. Its very shape and position within the cluster also hold vital clues about the internal dynamic life we've been exploring. Remember the process of mass segregation, where heavier stars sink to the core and lighter stars get gravitationally heated and pushed to the outskirts. This has a direct and measurable effect on the luminosity function. In the dense core of the cluster, where dynamical interactions have been most vigorous over billions of years, the population of low-mass stars has been systematically depleted. Many of those faint, lightweight red dwarfs have been ejected entirely. This means that if you were to measure the luminosity function Ni specifically in the cluster's core, you would find that the bend is less pronounced or even absent. The smooth distribution of faint stars has been truncated. Conversely, out in the cluster's halo, where the ejected low-mass stars tend to migrate, the knee and the faint end of the luminosity function would appear much richer and more populated than in the core. By carefully mapping how the luminosity function changes from the crowded center to the diffuse outer regions, astronomers can literally chart the history of mass segregation within the cluster. The knee becomes a fossil record of gravitational interactions, revealing not just how old the cluster is, but how dynamically evolved it has become, painting a picture of a system that has been constantly rearranging its stellar population through an endless, slow-motion gravitational dance. And if you thought single stars in these clusters had strange lives, wait until you see what happens when stars pair up. The intense social environment of a globular cluster doesn't just encourage stellar partnerships, it forges them into some of the most extreme and exotic binary systems in the entire cosmos. Far from the simple, well-behaved binaries we might find in the galactic field, clusters become factories for bizarre stellar relationships, producing cataclysmic variables, luminous X-ray binaries, and contact binaries that are so close they literally touch. These systems are not just curiosities, they are cosmic pressure cookers where the high stellar density and constant gravitational nudges create conditions for phenomenal stellar drama and incredible energy output. Let's start with the cataclysmic variables. The name itself is a perfect description. These systems are composed of two stars locked in a dangerously intimate dance. One is a normal, sun-like star, and the other is a white dwarf, the Earth-sized, super-dense core of a dead star. They orbit each other so closely that their orbital period can be as short as a few hours. At this range, the white dwarf's immense gravity begins to violently strip material away from its living companion. This stolen hydrogen doesn't just fall onto the white dwarf's surface. It forms a whirling, flat disk of superheated gas called an accretion disk, spiraling inward at tremendous speeds. The gas in this disk, heated by friction and gravitational compression, can glow brilliantly even before it reaches the white dwarf, but the real cataclysm happens periodically. When a critical mass of hydrogen accumulates on the surface of the white dwarf, it can ignite in a runaway thermonuclear explosion. This isn't a supernova that destroys the star, but a surface blast that causes the entire system to brighten by a factor of 100 or even 10,000 in a matter of hours, making it look from a great distance like a new cataclysmic star has appeared in the sky. These eruptions can repeat every few weeks or months as fresh material builds up and detonates again. In the calm between these outbursts, the system still sizzles with the energy of the constantly accreting disk, a persistent, simmering threat of the next explosion. The sheer number of these systems in globular clusters is a direct result of the environment. Close encounters between stars can dynamically create these tight pairs, or they can harden existing wide binaries, pushing them closer together until the white dwarf can begin its feast. Taking this concept of stellar vampirism to an even more extreme level are the low-mass X-ray binaries. These are the true powerhouses of the cluster. In these systems, the dead star is not a white dwarf, but something even denser, a neutron star or, in some cases, a stellar mass black hole. The companion is still a low-mass, sun-like star. The process is similar to a cataclysmic variable, but the energy scales are almost incomprehensibly higher. As material is pulled from the normal star and accelerated toward the neutron star or black hole, it doesn't just heat up, it is accelerated to nearly the speed of light. The gravitational potential energy released as this material plummets onto the surface of the neutron star or into the accretion disk around the black hole is so immense that it is converted into X-rays, the most energetic form of light after gamma rays. A single low-mass X-ray binary can outshine the entire cluster in X-ray light, appearing as a brilliant, flickering beacon. These systems are the primary way we identify stellar mass black holes in clusters, as the intense X-ray emission betrays their presence. The process of mass transfer can also spin the neutron star up to become a millisecond pulsar, creating a direct evolutionary link between these violent X-ray binaries and the quiet, precise clocks we find in abundance. The high density of globular clusters makes the formation of these exotic pairs much more probable than in the galactic field, as stellar interactions readily provide the neutron stars and black holes with the stellar partners they need to begin their luminous, destructive feast. Then there are the contact binaries, systems that take stellar intimacy to its absolute limit. Imagine two stars so close together that their mutual gravity has distorted them from perfect spheres into teardrop shapes. They are orbiting so rapidly that their period can be less than a single Earth day, and they are physically touching, sharing a common envelope of gas. These are the W Ursae Majoris type stars, and they are incredibly common in globular clusters. In this bizarre configuration, the two stellar cores orbit within a single shared atmosphere. Material can flow directly from one star to the other, creating a single peanut-shaped thermodynamic system. They are effectively Siamese twin stars, forced into this embrace by the dynamical processes of the cluster. Over time, the friction of this contact causes their orbits to decay even further, and they will eventually spiral completely into each other, likely merging into a single, rapidly spinning star, a potential precursor to a blue straggler. The prevalence of these contact binaries in clusters is another direct signature of the dynamical squeezing that occurs. Wide binaries get hardened through gravitational interactions with passing stars, their orbits shrinking until the stars are literally pressed against one another. Every one of these systems is a testament to the relentless gravitational processing that occurs in these dense environments, where stars are not allowed to live in peaceful isolation, but are constantly being pushed, pulled, and paired into ever more extreme configurations. Buried deep within the most densely packed globular clusters is a process of gravitational runaway, a phenomenon so dramatic it reshapes the very heart of the stellar city. This is the core collapse, and it represents the ultimate fate for many of these ancient systems, a future where the center cannot hold. To understand how this happens, we need to think of a globular cluster not as a static sculpture, but as a dynamic, breathing entity. The stars within it are in constant motion, orbiting the shared center of gravity, and as they do, they are perpetually exchanging energy through their mutual gravitational tugs. This process, called two-body relaxation, acts like a slow-motion thermal engine for the entire cluster. Just as air molecules in a room share kinetic energy until they reach a uniform temperature, stars in a cluster gravitationally interact until the system reaches a state of what's known as thermal equilibrium. But in gravity's unique version of thermodynamics, this equilibrium has a bizarre and counterintuitive outcome. The most massive stars, through these countless gentle encounters, tend to lose kinetic energy and slow down. As they slow, they sink inward, journeying toward the cluster's core in a process termed mass segregation. It's as if the heaviest dancers on a dance floor gradually, over eons, migrate to the very center of the room. Meanwhile, the lighter, low-mass stars often receive gravitational kicks that boost their speed, effectively heating them up. These energized, lightweight stars then migrate outward, some gaining so much velocity that they achieve escape speed and are permanently ejected from the cluster, contributing to the evaporation we discussed earlier. This creates a profound and unsustainable imbalance. The core of the cluster is becoming steadily more crowded with massive stars, while the outer halo is being stripped of its lighter members. The central density begins to skyrocket. As the core contracts under the weight of all these sinking heavy stars, its gravitational pull becomes even stronger, which in turn pulls in yet more stars, accelerating the process in a runaway positive feedback loop. This is the onset of core collapse. The central region, which might have originally been a few light years across, can shrink down to a volume so incredibly small that you could fit it within the distance from our Sun to its nearest stellar neighbors. In this ultra-dense state, the core is no longer a place of orderly orbits. It becomes a seething, chaotic environment where stars are whipping past each other at phenomenal speeds, their paths constantly and violently perturbed. The observational signature of a core-collapsed cluster is unmistakable. When you look at an image of a cluster like Messier 15 or Messier 30, the center isn't just bright, it is a blazing, almost solid-looking spike of light. The stellar density there is so extreme that our best telescopes, even Hubble, cannot resolve it into individual stars. It appears as a single, brilliant gem of fused starlight. This is the direct visual evidence of a gravitational catastrophe that has already occurred. The core has collapsed in on itself, achieving a density that can be thousands or even millions of times greater than the density in the cluster's outer regions. But what happens next in this stellar pressure cooker? The laws of physics demand a release of this incredible tension, and they provide it through spectacular stellar violence. In this chaotic environment, the probability of close encounters skyrockets. The most dramatic outcome is direct stellar collisions, when two stars, each moving at hundreds of kilometers per second, have their paths altered just enough to bring them into contact. They don't simply bounce. Their immense gravity pulls them together in a cataclysmic merger. The resulting object is a new, more massive star forged in a fireball of unimaginable proportions. These collision-born stars are often the blue stragglers we've already met, their fresh hydrogen fuel and reignited fusion making them appear bizarrely youthful amidst their ancient neighbors. The core collapse process, therefore, isn't an end. It's a crucible of stellar rebirth, a factory for creating new and exotic stellar objects through sheer gravitational forcing. Yet, the story doesn't necessarily end with a single terminal collapse. The universe has a way of finding balance even in extremis. The same process that creates the ultra-dense core can also lead to its own salvation through a mechanism known as gravitational heating. The most likely agents of this salvation are binary star systems. In the insane density of the collapsed core, the formation of binary stars through three-body encounters becomes highly probable. When a single star interacts with a tight binary system, the complex gravitational dance can result in the single star being flung out of the core at high speed, carrying away a tremendous amount of kinetic energy. According to Newton's laws, for every action there is an equal and opposite reaction. So, as this star is ejected, the binary system that flung it out receives a kick that hardens its own orbit, but also injects energy back into the core. It's as if the core's own gravitational interactions are building a pressure release valve. This injection of energy can, over time, halt the collapse and even cause the core to re-expand slightly, a phase known as core bounce. This sets up a potential cycle of collapse and rebound, where the cluster's heart pulses over billion-year timescales, periodically creating bursts of stellar collisions and then settling back into a temporary state of calm. This dynamic seesaw illustrates that a globular cluster is a far more active and evolving system than its serene appearance suggests, a place where gravitational physics plays out on a grand and relentless scale, constantly reshaping its internal landscape. And deep within this swirling stellar metropolis, we find individual suns that have been catapulted to blistering speeds, becoming cosmic cannonballs racing through the cluster's heart. These are the unusually fast-moving stars, and they are the direct, visible evidence of the intense gravitational game of pool that is constantly being played out in these dense environments. While most stars in a cluster move at a stately, shared pace dictated by the overall gravitational field, these stellar speedsters are outliers, clocking velocities that can be thousands of kilometers per second faster than their neighbors. They aren't just drifting, they've been shot from a gravitational slingshot, and their trajectories tell a story of a recent, violent encounter that forever altered their path through the cosmos. The primary mechanism for creating these stellar projectiles is a gravitational dance known as the three-body interaction. Imagine a stable, long-married binary star system, two stars peacefully orbiting their common center of mass. Now introduce a third star, a massive interloper that passes a little too close to the pair. The gravitational chaos that ensues is both complex and predictable in its outcome. The three stars exchange energy in a furious gravitational tug-of-war. Very often, the lightest star in the system becomes the victim of this cosmic mugging. The two more massive stars can effectively act as a team, gravitationally slinging the lighter one away at an incredible velocity, while they themselves, now bound more tightly together, receive a kick in the opposite direction. It's a perfect demonstration of Newton's third law in action on a stellar scale. The ejected star carries away the excess energy from the encounter, racing off on a new high-speed trajectory, while the remaining binary hardens, its orbit shrinking as a result of the interaction. This process is so efficient that a single close encounter can accelerate a star from a relative stroll to a significant fraction of the cluster's escape velocity. In some extreme cases, these stars are flung out with so much energy that they don't just race through the cluster. They break free entirely, becoming hypervelocity stars that escape the cluster's grip to wander the galactic halo alone. The very presence of these fast-moving stars within a cluster is therefore a direct measurement of the frequency of these dynamical encounters. By counting them and measuring their speeds, astronomers can effectively take the temperature of the cluster's core, gauging how dynamically active and violent its recent history has been. But there is another, even more dramatic pathway to stellar acceleration, one that involves the most extreme objects in the cluster, binary systems containing black holes or neutron stars. When a binary comprised of two such compact objects has its orbit tightened through dynamical interactions, it becomes a potent gravitational engine. As these ultra-dense partners spiral ever closer, they lose energy through the emission of gravitational waves, a process predicted by Einstein's theory of general relativity. This in-spiral continues until, eventually, they merge in a cataclysmic event that ripples the fabric of spacetime itself. If the merger is not perfectly symmetric, for instance, if the black holes have different masses or are spinning, the final, single black hole can receive a massive kick from the anisotropic emission of gravitational waves. This recoil can be so powerful that it launches the newly formed black hole out of the cluster at speeds of thousands of kilometers per second. Before this final merger, however, the binary can also act as a powerful slingshot for other stars. A normal star passing too close to a tight black hole binary can be given a gravitational kick of such ferocity that it is ejected at hypervelocity, a clear and unmistakable sign that an invisible, massive binary is lurking in the core, acting as a gravitational factory for stellar shrapnel. The detection of these fast-moving stars thus serves as an indirect way to probe the population of these dark, central engines, revealing the presence of black holes we might not be able to detect through other means. Studying the motions of these stars provides a natural laboratory for the fundamental laws of gravity and dynamics. By meticulously tracking their positions over years, even decades, with telescopes like Hubble and Gaia, astronomers can map their precise trajectories. These paths are not random. They are dictated by the sum of all the gravitational forces within the cluster, from the collective pull of hundreds of thousands of stars to the sharp, localized tugs from dense substructures or hidden black holes. Each high-velocity star is a test particle, and its motion allows scientists to reverse engineer the gravitational landscape of the cluster. This is how we can weigh the cluster, search for missing mass, and confirm the presence of intermediate mass black holes. The way these stars are distributed in velocity space, how many are moving at a certain speed, and in what direction acts as a fossil record of the cluster's dynamical past. A cluster with a large population of high-velocity stars is one that has experienced recent, significant dynamical activity, either because it is very dense and its core is undergoing collapse, or because it recently passed close to the galactic center, stirring up its stellar population. In this way, these stellar speedsters are more than just celestial curiosities. They are the dynamic tracers that illuminate the invisible forces sculpting these ancient cities of stars from within. This brings us to a subtle but deeply consequential puzzle in stellar demographics, one that forces us to look beyond the most obvious explanation to understand the final chapters in the lives of these ancient stars. It's known as the second parameter problem, and it centers on the horizontal branch, a specific stage of stellar evolution that becomes a powerful diagnostic tool. Near the end of its life, a mid-sized star exhausts the hydrogen fuel in its core and swells into a red giant. After a period of instability, it then makes a dramatic move on the Hertzsprung-Russell diagram, settling onto the horizontal branch. Here, the star is now burning helium in its core and hydrogen in a surrounding shell. What's crucial is that the exact position of a star on this horizontal branch, specifically its color and temperature, is primarily determined by the mass of its remaining hydrogen-rich envelope. A star with a thick envelope stays cooler and redder, residing on the red side of the horizontal branch. A star that has lost a significant amount of its outer layers, leaving only a thin blanket of hydrogen, will be much hotter and blaze with a blue-white light, sitting on the blue side. For a long time, astronomers had a beautifully simple one-factor explanation for this. They found that the primary driver, the first parameter, was a star's metallicity, its abundance of elements heavier than helium. Metal-poor stars, like those in most globular clusters, tend to have more powerful stellar winds during their red giant phase. These winds blow away more of the star's outer envelope, leaving a lower mass hydrogen shell when it arrives on the horizontal branch, which naturally leads to a hotter, bluer star. So, logic would dictate that all globular clusters with the same low metallicity should have horizontal branches that look identical, dominated by these hot blue stars. But the cosmos, as always, delights in complexity. When astronomers began comparing different clusters with nearly identical metallicities, they found stark and inexplicable differences in their horizontal branch morphologies. Some clusters, like the magnificent M53, display a horizontal branch that is almost entirely blue, a long, sweeping arc of hot stars, just as the first parameter rule predicts. Yet, other clusters with virtually the same ion content, such as the striking M3, show a horizontal branch richly populated with redder, cooler stars alongside the blue ones, creating a much more balanced and extended distribution. This is the heart of the second parameter problem. If metallicity alone cannot explain why M53 and M3 look so different, then there must be another factor, a second parameter, that is varying between them and influencing how much envelope mass a star retains before it ignites helium. Identifying this second parameter has become a major focus of stellar astrophysics because it holds the key to understanding the subtle differences in the life stories of these seemingly identical stellar populations. The search for this elusive factor has led scientists down several fascinating paths, each with profound implications. One of the strongest candidates is age. While all globular clusters are ancient, they are not all precisely the same age. Differences of even 1 or 2 billion years could be critical. A slightly younger cluster, while still immensely old, would have stars that formed when the universe had a tiny but non-zero amount of heavier elements. This minute difference in initial composition might affect the nuclear reaction rates in the star's core, changing its structure and how it loses mass. Furthermore, a younger star of the same initial mass as an older counterpart might have a slightly different internal structure, potentially leading to a less efficient mass loss during its red giant phase. This would leave it with a thicker hydrogen envelope when it arrives on the horizontal branch, explaining a redder, cooler presence. It's a subtle distinction, but over billions of years, these slight variations in initial conditions can manifest as dramatically different final appearances. Another compelling and more radical candidate is helium abundance. We've already discussed how multiple stellar generations have polluted clusters with extra helium. Imagine two clusters with the exact same iron content, but one of them experienced a much more efficient second wave of star formation, meaning a higher proportion of its stars are from a generation enriched with extra helium. Helium is a lighter element than hydrogen, and it alters the fundamental physics inside a star. A star born with a higher initial helium fraction has a different internal structure. It has a smaller, denser core and burns its fuel more rapidly. This can lead to a more dramatic mass loss process before the star ever reaches the horizontal branch. The result is that by the time helium fusion begins, the star has been stripped down even further, making it more likely to land on the hot, blue end of the horizontal branch. Therefore, a cluster with a higher overall helium abundance could have a much bluer horizontal branch than a cluster with the same metallicity but less helium, providing an elegant solution to the puzzle. This directly links the second parameter problem to the complex formation history of the clusters themselves. A third possibility involves the dynamics of the cluster environment itself, specifically the rotation of the stars. In the calm of the galactic field, stars generally rotate at a modest pace, but in the crowded core of a globular cluster, close gravitational encounters can literally spin stars up, transferring angular momentum and causing them to rotate much faster. A rapidly rotating star is a different beast altogether. The centrifugal force from fast rotation can make the star oblate, bulging at its equator, and this can affect how it loses mass. Stellar winds might be enhanced at the poles or the equator, changing the overall mass loss budget. Furthermore, rotation induces internal mixing, bringing fresh hydrogen from the outer layers down into the core and prolonging the star's life. This altered evolutionary path could easily result in a different envelope mass when the star finally settles onto the horizontal branch, pushing it toward a redder or bluer location. In this scenario, the second parameter isn't a chemical or age difference, but a dynamical one. A cluster with a higher density and more frequent stellar interactions could produce systematically faster rotating stars, which in turn imprint a specific signature on the horizontal branch morphology. The truth is that the second parameter is likely not a single, unifying solution, but a combination of these factors, with one dominating in certain clusters and another in different ones. This makes the horizontal branch a far richer and more nuanced cosmic laboratory than we first imagined. It's not just a simple endpoint of stellar evolution. It's a sensitive screen onto which a star's entire history is projected, its birth composition, its age, and even the dynamic social environment it has experienced for billions of years. Cracking this code doesn't just solve a technical problem in stellar astrophysics. It refines our ability to use these ancient stars as precise chronometers and chemical tracers, allowing us to read the finer print in the epic story of our galaxy's formation. Now we turn to a phenomenon that lets us literally see into the past, a cosmic replay made possible by the slow, patient journey of light itself. Imagine witnessing a stellar explosion that occurred centuries ago, not from some indirect evidence, but by seeing its light arrive at your telescope for a second time. This is the magic of light echoes, and their detection within the dusty confines of globular clusters has opened an entirely new window through which we can observe history. The principle is elegantly simple, yet its implications are profound. When a star erupts in a cataclysmic event, whether a nova, a supernova, or a titanic flare, it unleashes an immense, instantaneous pulse of light in all directions. The light that travels directly from the event to Earth is what we would see as the initial flash, a brief, brilliant signal that fades in days or weeks. But in an environment like a globular cluster, which often contains clouds of interstellar dust, that initial flash doesn't just vanish. It keeps traveling outward at the speed of light until it slams into a distant wall of dust grains. These microscopic particles absorb the light and then re-emit it, scattering it in new directions. Some of this re-emitted or echoed light is sent on a longer, more scenic route toward us. It arrives at our telescopes years, decades, or even centuries after the direct light from the original event. What we see is not the event itself, but its reflection, a ghostly, expanding ring of light that appears to move outward from the long, quiet source. It's as if the universe has provided us with a cosmic DVR, allowing us to rewind and re-watch some of its most dramatic moments. This technique transforms a single, fleeting observation into a multi-year, sometimes multi-century scientific study. Consider a classical nova that was observed to flare in a globular cluster 200 years ago. An astronomer of that era would have recorded a new star appearing where none was before, watching it brighten and then fade over a few months. Their data would be limited to the brightness and color they could measure with the instruments of the day. Fast forward to the present. Using the Hubble Space Telescope, we might detect a delicate, shell-like structure of visible light slowly expanding outward from the location of that long-dead nova. This is the light echo. By monitoring this expanding shell year after year, we can perform a kind of astrophysical tomography. We are not just seeing one image, we are seeing the original flash of light as it illuminates successive shells of dust at different distances from the explosion. This allows us to conduct a forensic investigation of the original event with modern tools that the 18th century astronomer could never have dreamed of. We can take a spectrum of the echoed light, dissecting its rainbow to determine the precise chemical composition of the material ejected in the blast 2 centuries prior. We can measure the velocity and geometry of the outflow in 3 dimensions, seeing if it was a symmetrical blast or a lopsided one. We can even search for signatures of the underlying binary system that powered the nova, clues that were completely invisible in the initial, direct glare of the eruption. A light echo turns a historical footnote into a living, breathing laboratory. The most breathtaking application of this is the potential to study supernova light echoes within clusters. As we discussed earlier, the supernova remnants themselves are mysteriously absent, having faded or been disrupted. But their light echoes could still be propagating through the cluster's halo, a faint, shimmering memory of a stellar death that occurred millennia ago. Finding such an echo would be a monumental discovery. It would allow us to directly classify a supernova that no human ever saw, to determine if it was the core collapse of a massive star or the thermonuclear detonation of a white dwarf. We could analyze the spectrum of the echo to see the specific elemental fingerprints forged in that incredible explosion, providing a direct measurement of how these clusters contributed to the chemical enrichment of the early galaxy. We could precisely locate the site of the explosion and see what resides there today, perhaps a neutron star or a black hole that is the direct descendant of that cataclysmic event. In this way, light echoes act as a form of cosmic archaeology, letting us dig through layers of time to uncover the violent history that shaped these ancient stellar cities, giving us a second chance to observe the most ephemeral and transformative events in the universe. But the surprises hidden within these clusters aren't limited to our own galactic backyard. Far beyond the halo of the Milky Way, within a small, cannibalized galaxy known as the Sagittarius dwarf spheroidal, lies the globular cluster M54. For a long time, it was thought to be just another one of our galaxy's many satellite clusters, but we now know its different M54 is actually the nuclear star cluster of the Sagittarius dwarf galaxy, the very heart of that system, which the Milky Way is currently in the process of tearing apart and absorbing. And at the center of that cluster, astronomers have found a gravitational monster that defies all expectations. A black hole of such immense proportions that it challenges our fundamental understanding of how these objects can form in dense stellar environments. The standard methods for detecting black holes in clusters involve watching the movements of stars near the core. As stars whip around an invisible central mass, their speeds reveal the gravitational pull of whatever is there. When these measurements were applied to M54, the results were staggering. The stellar motions indicated a central black hole with a mass of around several thousand times that of our Sun. This by itself would place it firmly in the category of an intermediate mass black hole, which we've discussed, and while surprising, that wouldn't be unprecedented. However, the true shock came when astronomers compared the mass of this black hole to the total mass of the globular cluster itself. The ratio was astronomically high, completely out of line with the scaling relations we see anywhere else in the universe. In larger galaxies, there is a known correlation between the mass of the central supermassive black hole and the mass of the galaxy's central bulge. The black hole typically makes up about 0.1% of the bulge's mass. For the intermediate mass black holes found in some other globular clusters, this fraction is even smaller, a mere speck compared to the cluster's total stellar mass. But in M54, the black hole is so disproportionately massive that it completely breaks this scaling relation. It's an overmassive black hole, a true heavyweight champion residing in a relatively lightweight stellar system. This presents a profound challenge to theorists. How could such a behemoth come to reside in a cluster of this size? One leading hypothesis reaches back to the unique identity of M54. Because it isn't just a globular cluster, it's the stripped nucleus of a dwarf galaxy. It may have inherited its black hole through an entirely different cosmic pathway. In the standard model of galaxy formation, every sizable galaxy is thought to harbor a supermassive black hole at its center. The Sagittarius dwarf galaxy was, before its disruption, a proper galaxy in its own right. Therefore, it would have possessed its own central supermassive black hole. As the Milky Way's tidal forces shredded the outer layers of the dwarf galaxy, the dense nuclear star cluster M54 and its pre-existing supermassive black hole were left as the surviving core. In this scenario, the black hole in M54 wasn't formed within a globular cluster. It was born as the central engine of a galaxy, and we are simply seeing it now in its final captured state. This would neatly explain its excessive mass, as it follows the galactic, not the cluster, black hole scaling relation. However, this discovery forces us to reconsider the very nature of some of the most massive globular clusters we see. It raises the tantalizing possibility that other extremely massive clusters, like Omega Centauri in the Milky Way, might not be genuine globular clusters at all. They, too, could be the leftover cores of ancient dwarf galaxies that were completely devoured by our Milky Way in the distant past. If that were true, then they too might harbor similarly overmassive black holes in their centers, a possibility that astronomers are actively investigating. The existence of this single, overmassive black hole in M54 does more than just add another strange object to our list. It blurs the line between the largest star clusters and the smallest galaxies, suggesting that the distinction may be more about their formation history than their present-day appearance. It tells us that the gravitational anchors of these systems hold secrets not just about stellar dynamics, but about the hierarchical construction of galaxies themselves, a process of cosmic cannibalism where the devoured leave behind their dark hearts as the only evidence of their former existence. Nestled within the radio silence of these ancient clusters, astronomers have pinpointed another class of enigmatic objects that defy straightforward classification. These are the anomalous X-ray sources, luminous spots of high-energy emission that outshine typical stellar binaries but fall short of the awesome power of active galactic nuclei. They occupy a strange middle ground in the cosmic power hierarchy, too bright to be explained by a simple neutron star accreting from a companion, yet not nearly brilliant enough to qualify as a miniature quasar. Their very existence suggests we are witnessing either a new, unidentified class of celestial object or a familiar process operating under such extreme and unusual conditions that it produces a radically different outcome. To grasp why these sources are so baffling, we need to understand the standard X-ray players in a cluster. The most common bright X-ray emitters are low-mass X-ray binaries, where a neutron star or stellar mass black hole pulls material from a sun-like companion. This accretion process generates X-rays, but there's a theoretical upper limit to their brightness, known as the Eddington limit. This is the point at which the outward pressure from the intense radiation being produced actually overcomes the inward pull of gravity, effectively shutting off the accretion flow and limiting how luminous the object can become. The anomalous X-ray sources, however, consistently blow past this limit for a system powered by a stellar mass black hole. They can be 10, 100, or even 1,000 times more luminous than a typical binary system should be, producing a persistent, powerful X-ray glow that demands a more massive engine. This luminosity problem has led scientists to propose several compelling and sometimes controversial explanations. The leading hypothesis points directly to the intermediate mass black holes we've discussed. If a black hole weighing a few thousand solar masses resides at the cluster's center, it could easily power these luminous X-ray sources without breaking a sweat. The higher mass means a deeper gravitational well, which allows for a much higher Eddington limit. In this scenario, the anomalous source might be a normal stellar mass object, like a neutron star, that has wandered too close to the intermediate mass black hole. The black hole's immense gravity could strip material from the smaller object at a ferocious rate, or it could be actively accreting from a dense disk of gas created by earlier tidal disruptions of stars. The observed X-rays would then be the signature of this violent feast, scaled up to a level that only a more massive central predator could provide. However, there's another, more exotic possibility that doesn't require an intermediate mass black hole at all. What if we are seeing a standard stellar mass black hole, but it is accreting material in a fundamentally different way? Most models assume spherical accretion, but if matter is funneled onto the black hole in a narrow, dense stream or through a warped disk, it might be possible to temporarily exceed the classical Eddington limit. In this super-Eddington accretion state, the physics changes. The radiation is trapped within the inflowing material, creating a thick, opaque flow that allows more fuel to reach the black hole's event horizon before the radiation can push it away. This would make the system appear far more luminous than our standard models would predict for its mass, creating the illusion of a more powerful object. Alternatively, the source could be an ultraluminous X-ray pulsar, a neutron star with an incredibly strong magnetic field. This field can funnel the accreting material directly onto the magnetic poles, creating intensely hot, localized spots that emit X-rays with a brightness that, from certain viewing angles, appears to violate the Eddington limit for a neutron star. The key to distinguishing between these models often lies in the X-ray light itself. Many of these anomalous sources exhibit a characteristic flickering, a rapid variability in their output. This flickering timescale is a clue to the size of the emitting region. The faster the flicker, the smaller the region must be. The incredibly rapid variations seen in some of these sources point to an emission region smaller than our Sun, which strongly favors a compact object like a stellar mass black hole or neutron star as the power source, rather than a much larger intermediate mass black hole. This brings us back to the super-Eddington accretion idea, suggesting that under the right conditions, even modest-sized black holes can put on a surprisingly brilliant show. The dense environment of a globular cluster is likely the key ingredient that makes these extreme phenomena possible. The constant gravitational interactions can provide a steady supply of fuel. A black hole could be surrounded by a cloud of debris from tidally disrupted stars, or it could be part of a complex hierarchical triple system where two stars feed material to it in a chaotic gravitational dance. The very processes that create blue stragglers and millisecond pulsars collisions and mass transfer could also be forging these peculiar X-ray powerhouses. Each anomalous source is therefore a unique cosmic experiment, a testbed for accretion physics under conditions we cannot replicate anywhere else. Their persistent but puzzling glow challenges us to refine our theories of how matter behaves in the most intense gravitational fields, reminding us that even in the oldest neighborhoods of the universe, there are still new and surprising ways for matter to shine. Yet another layer of complexity emerges when we peer at the very moment stars begin their final transformation, a discovery that reveals these ancient clusters are not the simple, single-aged families we once presumed. This mystery is found in the extended main sequence turnoff, and it begins with a fundamental concept in stellar astronomy, the main sequence turnoff point itself. On a Hertzsprung-Russell diagram which plots stars by their color and brightness, most stars spend the majority of their lives on a well-defined band called the main sequence. This is their stable, hydrogen-burning adulthood, the exact point on this band where stars are leaving the main sequence to become red giants is the turnoff point. It's a critical cosmic clock, since more massive stars burn their fuel faster and leave the main sequence sooner. The location of this turnoff point directly tells you the age of the stellar population. For a simple, single-aged cluster, all stars of the same mass should exhaust their core hydrogen at the same time, creating a sharp, well-defined turnoff point where the main sequence abruptly bends into the giant branch. It should look like a distinct corner in the diagram. However, when astronomers trained the Hubble Space Telescope on many globular clusters, they found something completely different. Instead of a sharp corner, they saw a broadened, smeared out, or even split turnoff region. It was as if the stars were not all clocking out from their main sequence jobs at the same time, but were instead leaving in a staggered fashion over hundreds of millions of years. This blurring of the cosmic clock is the extended main sequence turnoff, and it forces us to abandon the idea that every star in a cluster is an exact contemporary. The immediate and most intuitive explanation for this spread is an age difference. Perhaps what we call a single globular cluster is not the product of one single, rapid burst of star formation, but rather several bursts stretched out over a significant period. In this scenario, the cluster didn't form all its stars in one furious million-year period, but might have experienced waves of star formation spanning 200 or 300 million years. While this is a cosmic blink of an eye compared to the cluster's 13 billion-year life, it is more than enough time to leave a distinct imprint on the turnoff point. The stars from the very first wave would be the oldest, and their turnoff point would be at a fainter, redder part of the diagram. The stars from a subsequent wave, born 100 million years later, would be slightly younger. Their turnoff point would be at a brighter, bluer location because stars of the same mass would still be happily burning hydrogen in their cores, not yet ready to evolve. When you plot all these stars from different generations together, their individual sharp turnoff points blend into a broad, extended swath. This fits beautifully with the earlier discovery of multiple stellar populations, providing a consistent picture of a cluster with a more prolonged and complex formation history than the simple, single-burst model allowed. It suggests that the conditions for star formation persisted within the cluster for much longer than we thought, perhaps because the cluster managed to retain gas reservoirs far longer against the powerful stellar winds from its most massive members. However, age spread is not the only actor in this play. A second, equally compelling explanation has gained significant traction, one that involves the spin of the stars themselves. Stellar rotation can profoundly alter a star's life story, and in the dense environment of a globular cluster, stars can be spun up to incredible speeds through close gravitational encounters with their neighbors. A rapidly rotating star is not the same as a stationary one. The centrifugal force makes the star bulge at its equator, which changes its internal structure and temperature gradient. More importantly, rotation induces mixing. It churns the star's interior like a giant spoon stirring a pot. This mixing brings fresh hydrogen from the outer layers down into the core, effectively refueling the nuclear furnace. At the same time, it carries helium-rich ash from the core out into the envelope. This extended fuel supply allows a rotating star to remain on the main sequence significantly longer than a non-rotating star of the same mass and initial composition. Now, imagine a cluster where some stars are rapid rotators and others are slow. The rapid rotators will have a delayed evolution. They will linger on the main sequence, their turn-off point appearing fainter and redder. The slow rotators will evolve on schedule, turning off at a brighter, bluer point. When you observe the cluster as a whole, the coexistence of these fast and slow rotators will create a spread in the turn-off region that looks remarkably similar to an age spread. It's a case of stellar nature versus nurture. The innate properties of the star are being modified by the dynamic environment it has lived in for billions of years. Distinguishing between the age spread hypothesis and the rotation hypothesis is one of the most active areas of research in stellar astrophysics today, and the answer is likely a complex combination of both. Astronomers are using sophisticated computer models to simulate stellar evolution with rotation included, and then comparing the predicted extended main sequence turnoffs to the exquisite data from Hubble. They are looking for subtle clues in the precise shape of the smeared-out region. Some clusters show a turnoff that is not just broadened, but actually split into two distinct branches, a feature that is very difficult to explain with a smooth age spread alone, but which could be explained by two distinct populations of stars with very different rotation histories. This makes the extended main sequence turnoff more than just a complication for age dating. It is a powerful diagnostic tool. By analyzing its precise morphology, we can start to unravel the specific dynamical history of a cluster. A cluster with a broad turnoff might have had a prolonged period of gas retention and star formation, while a cluster with a split turnoff might have experienced a major dynamical event like a core collapse that violently spun up a large fraction of its stars. This single, blurry line on a graph therefore encapsulates billions of years of a cluster's secret history, from its earliest days of formation to the gravitational interactions that have shaped its stellar population ever since. The incredibly dense cores of globular clusters, where stellar encounters are a constant fact of life, are now believed to be among the most productive factories for gravitational waves in the entire universe. Gravitational waves are ripples in the very fabric of spacetime itself, first predicted by Einstein's theory of general relativity. They are generated when massive objects are accelerated in particularly violent ways, such as during the merger of two ultra-dense remnants like neutron stars or black holes. Detecting these waves is extraordinarily difficult because they are incredibly faint. By the time they reach us, the distortion they cause is thousands of times smaller than the nucleus of an atom. That's why it took a century and an instrument of almost unimaginable sensitivity, LIGO, to finally confirm their existence. But while LIGO has detected mergers from black holes and neutron stars in the broader galactic field, the unique environment inside a globular cluster makes it a specially tuned engine for producing these cosmic tremors at a potentially staggering rate. The secret lies in the cluster's ability to orchestrate the mergers of its most exotic and massive inhabitants through a relentless process of gravitational matchmaking. In the sparse environment of the galactic disk, two black holes or neutron stars must be born in a tight binary system from the very beginning to have any chance of merging within the age of the universe. Left alone, their orbit will only decay slowly through the emission of gravitational waves, a process that can take billions upon billions of years. But inside the bustling core of a globular cluster, these compact objects don't have to wait. They are given a massive gravitational push. The process begins with mass segregation, the same phenomenon that drives the core to collapse. Black holes, being the most massive objects in the cluster, rapidly sink to the very center, forming a dense subcluster of their own kind. In this chaotic downtown of dark objects, close encounters are not just likely, they are inevitable. When two black holes pass near each other, they can become gravitationally bound, forming a new binary system on the spot. Even more effectively, a single black hole can interact with a pre-existing binary system in a dramatic three-body encounter. The complex gravitational dance that follows often results in the original binary being hardened, its orbit shrunk and tightened, while the single black hole is ejected from the core at high speed. This hardening is the critical step. A tighter orbit means a faster orbital period and a much shorter lifetime until merger due to gravitational wave emission. What might have been a multi-billion-year process in isolation can be accelerated to just a few million years or even less within the cluster's dynamic core. This means that over the long history of a globular cluster, the central population of black holes and neutron stars can churn out merger after merger, each one sending a powerful burst of gravitational waves out across the cosmos. The implications of this are profound for our ongoing surveys of the gravitational universe. Instruments like LIGO and Virgo are listening to the cosmos, and a significant fraction of the black hole mergers they detect could very well have originated in globular clusters. There are even telltale signatures that might point to a globular cluster origin. For instance, the black holes that form and merge in these dense environments can have a different mass distribution than those that form in isolated binary systems. Dynamically formed binaries can pair up black holes that are more massive, and they can also create pairs with randomly aligned spins, unlike the typically aligned spins of binaries born together from a single stellar nursery. As we collect more gravitational wave events, statistical patterns in the masses and spins of the merging black holes could reveal the distinctive fingerprint of these dense stellar factories. Furthermore, the sheer rate of mergers in clusters helps solve a puzzle. If black hole mergers were only possible from isolated binary evolution, the predicted rate might be too low to match what LIGO is already observing. Globular clusters provide a necessary and prolific additional channel, ensuring that the cosmic symphony of gravitational waves is as rich and varied as it is. These clusters are not just silent, glittering ornaments, they are active, rumbling engines of spacetime distortion, constantly broadcasting their internal dramas through a language of invisible ripples that we are only just beginning to understand. But just as we think we have a handle on the chemical history of these clusters, a specific and perplexing elemental deficit emerges, one that challenges our understanding of the universe's very first moments. This is the lithium problem, and it centers on an element so simple and fundamental that its unexpected behavior has become a major cosmological headache. Lithium is the third element on the periodic table, and according to our most robust models of Big Bang nucleosynthesis, the process that forged the first atomic nuclei in the initial minutes of the cosmos, a specific, predictable amount of lithium-7 should have been created. This primordial lithium, along with hydrogen and helium, became the raw material for the first stars. The theory is exquisitely precise. Based on the measured density of ordinary matter in the universe, we can calculate exactly how much lithium should have been present when the first stellar generations formed. When astronomers then look at the oldest stars we can find, the ones that should preserve this pristine, primordial chemical mix, they expect to see this predicted level of lithium in their atmospheres. And this is where the mystery begins. In the atmospheres of the most ancient stars within globular clusters, the measured abundance of lithium is consistently and significantly lower than the Big Bang model predicts. It's as if someone has been secretly destroying lithium for billions of years, and the most ancient stellar fossils are the evidence of this long-running cosmic crime. To grasp why this is so troubling, we need to understand that these particular cluster stars are our cleanest laboratories. They belong to that first generation, formed from gas that had not yet been polluted by the supernova of earlier stars. Their outer atmospheres are like time capsules, preserving the chemical composition of the early universe. Finding less lithium there than expected means one of two things. Either our understanding of the nuclear physics in the universe's first 3 minutes is incomplete, or some process inside these ancient stars has been systematically consuming lithium after the stars formed. Both possibilities are profound. The first strikes at the heart of our most successful model of the early universe, while the second implies there is a fundamental stellar process we have not yet accounted for, one that can destroy this fragile element deep within stellar interiors. So how could a star destroy its own lithium? Stars are not passive observers, they are dynamic furnaces. The most promising explanation involves a process called diffusion, coupled with slow internal mixing. A star like our Sun has a layered structure. Nuclear fusion, which powers the star, occurs only in the incredibly hot and dense core. The outer atmosphere, or photosphere, is much cooler, and it is the light from this layer that we analyze to determine the star's chemical composition. For most elements, this atmosphere is a reliable record, but lithium is an incredibly fragile atom. It has a low nuclear binding energy, which means it is easily destroyed in nuclear reactions at temperatures as low as 2.5 million Kelvin, a temperature that is reached not in the star's core, but in a layer just beneath the visible surface. The theory suggests that over billions of years, lithium atoms in the atmosphere can slowly sink downward through a process of gravitational settling. Once they drift deep enough to reach this hot layer, they are rapidly fused into heavier elements like 2 helium nuclei. This process would slowly but surely deplete the lithium in the atmosphere, creating the discrepancy we observe. Furthermore, if there is any slow, large-scale circulation of material, a gentle stellar mixing it would constantly bring fresh lithium from the atmosphere down into the destruction zone, acting like a conveyor belt feeding a furnace. The older the star, the more time this process has had to operate, and the less lithium we should see. This fits the observational data perfectly, as the stars with the very lowest lithium abundances are consistently the oldest ones. However, the plot thickens when we consider the environment of a globular cluster. Could the dense social life of the cluster be accelerating this lithium destruction? It's a compelling possibility. The same dynamical interactions that spin up stars to create blue stragglers and alter horizontal branches could also be stirring a star's interior. A close gravitational encounter with another star, or the tidal forces in a tight binary system, might trigger internal waves or disrupt the star's stable layering, enhancing the mixing process and driving lithium from the surface down to its doom more efficiently than in an isolated star. This would mean that the lithium depletion we see isn't just a function of age, but also of a star's social history within the cluster. A star that has lived a quiet, solitary life in the cluster's outskirts might retain more of its primordial lithium than a star of the same age that has resided in the chaotic core, constantly buffeted by gravitational interactions. This turns the lithium abundance into a potential new diagnostic tool, a chemical marker that could reveal the dynamic past of individual stars within the ancient stellar city. The lithium problem, therefore, is more than a cosmological puzzle. It is a window into the subtle, internal workings of stars and how their long-term evolution is shaped by the company they keep. Most of us picture a globular cluster as a perfectly spherical, static swarm of stars, a place where every star is buzzing around in a purely random, chaotic dance with no overall direction or purpose. It's a beautiful image, but for many of these clusters, it's fundamentally wrong. We now know that a significant number of these ancient systems are not the unordered beehives we imagined. They are slowly spinning with a distinct sense of cosmic choreography. This overall rotation, or the discovery that the orbits of many stars are aligned in a preferred direction, is a subtle but profoundly important clue. It tells us that the chaos of their formation was not complete, that a whisper of order from their birth has managed to persist for billions of years, and it provides a direct link to the specific conditions under which they were born. The evidence for this rotation isn't something you can see in a single photograph. It's hidden in the starlight, revealed through the painstaking measurement of stellar motions. Using powerful observatories like the Hubble Space Telescope and the Gaia mission, astronomers have been able to track the precise movements of thousands of individual stars within a cluster. They don't just measure if a star is moving towards or away from us, they can map its motion across the sky. When they do this for a rotating cluster, a clear pattern emerges. The stars on one side of the cluster's center are systematically moving toward us, while the stars on the opposite side are moving away. It's the same principle we use to see that a spiral galaxy is spinning, but applied to a much smaller and denser stellar system. This isn't a fast, violent whirl. It's a stately, slow roll, a collective drift that has been ongoing since the cluster first condensed from its primordial gas cloud. The very fact that this rotation has survived for over 13 billion years is a testament to the cluster's incredible stability. In a less bound system, gravitational interactions between stars would have long since randomized these orderly motions, erasing the rotation through a process called two-body relaxation. The fact that we can still detect it means the cluster's gravity is so dominant that it has preserved this primordial fingerprint against the constant, eroding force of internal stellar encounters. So, what does this preserved spin actually tell us? It points directly to the cluster's origin story. The leading theory is that this rotation is a fossil relic, a leftover from the specific way the cluster collapsed. The prevailing model for star formation, even on these immense scales, involves the gravitational collapse of a giant molecular cloud. As this vast cloud of gas begins to fall in on itself, any tiny initial amount of random motion or turbulence can become amplified, just like how a figure skater spins faster as they pull their arms in. This conservation of angular momentum would have caused the entire collapsing cloud to begin rotating. The resulting globular cluster, having formed from this spinning cloud, would have inherited that overall spin. The stars that condensed within it would have largely retained the motion of the gas from which they were born, resulting in the large-scale rotation we detect today. The presence of rotation, therefore, strongly supports the idea that these clusters formed from the monolithic collapse of a single, massive cloud, and it allows us to rule out other, more chaotic formation scenarios that would not have produced such a coherent spin. But the story doesn't end with a simple spin. Some clusters show an even more intricate kind of order, where the elongated orbits of many stars are not just part of a general rotation, but are actually aligned with each other like a flock of birds all flying in formation. This phenomenon, known as radial orbit anisotropy, is a deeper and more subtle level of organization. It means that a significant fraction of the stars are following paths that are not circular but elliptical, and crucially, the long axes of these ellipses are all pointing in roughly the same direction within the cluster. This isn't the smooth, wheel-like rotation of the entire cluster, but a coordinated dance of individual stellar trajectories. This kind of organized motion is a much more fragile fossil. It is easily destroyed by the gravitational jostling of stars over time. Finding it preserved in an ancient cluster is like finding a perfectly preserved fossil in a turbulent riverbed. It suggests that the cluster has lived a relatively quiet life, avoiding major disruptive events that would have scrambled this delicate orbital architecture. The implications of these aligned orbits are profound, and they point toward a dramatic past interaction with our galaxy. One of the most compelling explanations for this phenomenon is that the cluster experienced a strong, specific tidal shock. Imagine the cluster making a close pass by the Milky Way's dense central bulge. The galaxy's tidal gravitational field doesn't just pull evenly, it stretches the cluster, and it does so in a specific direction. This tidal force can act as a powerful sculptor, selectively stripping away stars that are on random, misaligned orbits, while leaving behind those stars whose orbits are already aligned with the direction of the tidal pull. It's a gravitational filtering process. After the flyby, the cluster that emerges is leaner and has a stellar population whose orbits have been neatly organized by the galaxy's immense gravitational hand. Alternatively, this orbital alignment could be the signature of the cluster's own formation within the disk of the young Milky Way. If it was born from a giant molecular cloud that was itself part of the galaxy's rotating disk, the initial conditions could have imprinted this specific orbital structure from the very beginning. In either case, whether it's the scar of a past galactic encounter or a birthmark from its formation in the galactic disk, the aligned orbits provide a powerful diagnostic tool. By measuring the precise degree and direction of this orbital alignment, astronomers can effectively work backwards, reconstructing the cluster's orbital history and its relationship with the galaxy over billions of years, turning the subtle motions of ancient suns into a historical record of cosmic interactions. We now arrive at a celestial census discrepancy that centers on one of the most dramatic and brilliant phases of a star's life. According to our well-tested models of stellar evolution, a predictable percentage of the stars in an ancient globular cluster should at any given time be in the red giant phase. This is the final, glorious blaze of a star's life after it exhausts the hydrogen fuel in its core, causing it to swell to an immense size and glow with a characteristic red hue. These stars are the beacons of a cluster among its brightest and most easily observed members. Yet, when astronomers take a head count in certain clusters, the numbers consistently come up short. There is a clear and puzzling deficit of these red giant stars. It's as if a specific demographic within the stellar population has quietly gone missing, and the explanation points directly to the intense social pressures of life in a dense star city, where the very process of aging can be accelerated or altered. The standard stellar life cycle for a sun-like star is a graceful and predictable dance. After billions of years steadily burning hydrogen, the core becomes a dense ball of inert helium. With a central fusion engine shut down, the core begins to contract under its own weight, releasing a tremendous amount of gravitational energy. This energy heats the shell of hydrogen surrounding the core to the point of ignition, causing it to fuse violently. The outpouring of energy from this shell fusion is so immense that the star's outer layers are forced to expand to hundreds of times their original size, transforming the star into a brilliant red giant. Our models tell us precisely how long a star of a given mass should spend in this phase, and how many red giants we should expect to see in a cluster of a known age and size. The fact that we observe fewer than predicted means something is interrupting this process. The stars are somehow skipping the full red giant phase or passing through it so quickly that they become statistically elusive. The prime suspect in this mystery is enhanced mass loss. All red giant stars lose mass through powerful stellar winds, where the star's own radiation pressure pushes its outer atmosphere out into space. This is a normal part of the aging process. However, in the crowded core of a globular cluster, this natural shedding may be dramatically accelerated. One compelling theory involves the relentless gravitational nudges from passing stars. In a dense environment, a red giant with its vast distended atmosphere presents a huge target. A close encounter with another star could gravitationally shake the giant, destabilizing its outer layers and effectively stripping away a significant portion of its hydrogen envelope in a single dramatic event. Even without direct collisions, the constant tidal forces from the cluster's overall gravitational field could act like a constant, gentle tug, loosening the star's grip on its own atmosphere and causing it to shed mass at a much higher rate than a star living in the peaceful isolation of the galactic disk. This enhanced mass loss has a direct and profound effect on the star's evolution. The red giant phase is fundamentally powered by the hydrogen-burning shell around the helium core. The mass of the hydrogen envelope acts as a blanket, controlling the pressure and temperature at the base of the shell. If a star loses this envelope too rapidly and too early, it effectively runs out of fuel for the red giant branch. The star may never reach the brilliant peak luminosity that characterizes a classic red giant. Instead, it could transition prematurely to the next stage, the horizontal branch, appearing as a fainter, hotter star. In the most extreme cases, if mass loss is truly ferocious, a star could have its entire envelope stripped away, exposing its hot, helium-burning core and bypassing the red giant phase almost entirely. This would create a bluer and less luminous star where our models predict a red giant should be, directly accounting for the observed deficit. But there's another, more subtle evolutionary quirk that could be at play. The journey to the red giant branch is not a simple one-way street. For stars of a specific mass range, there is a critical, unstable phase known as the helium flash. This is the moment when the degenerate helium core becomes hot and dense enough to ignite helium fusion in a sudden, explosive burst. In a single star living in isolation, this flash is contained deep within the core and has little effect on the star's outer layers. However, some theorists have proposed that in the unique chemical environment of a globular cluster, where stars from later generations are born with extra helium, this flash could be far more violent. A stronger helium flash might disrupt the star's internal structure, leading to a much more rapid traversal of the red giant phase or, again, a different evolutionary path altogether. The star might quickly shed its envelope and move to the horizontal branch before we have much of a chance to observe it as a classic red giant. This would mean that the chemical pollution that created multiple stellar populations within the cluster is also directly influencing how those stars die, creating a feedback loop where a star's birth composition dictates its final act. The missing red giants are therefore not an error in our stellar models, but a powerful indication that those models must be refined to account for the complex and dynamic realities of stellar life in a crowded metropolis, where gravity and chemistry conspire to rewrite the standard script of stellar death. Yet another layer of mystery is woven into the very emptiness between the stars, where we find something that should not be there at all. For decades, the conventional view of a mature globular cluster was that of a purely stellar environment, a celestial city that had long ago cleaned its streets. The immense collective radiation pressure and stellar winds from thousands of hot, young stars in the cluster's infancy, along with the shockwaves from early supernova explosions, were believed to have acted like a cosmic hurricane, sweeping every last wisp of gas and every mote of dust clear out of the cluster's grasp billions of years ago. The space between the stars should be a pristine, almost perfect vacuum with nothing left to obscure our view. This is why the detection of small but significant amounts of intracluster dust and gas came as such a profound surprise. It's the equivalent of finding fresh sand and seawater in the hallways of a sunken ship that has been on the ocean floor for millennia. It points to an ongoing process, a slow leak or a new source that is actively replenishing what should have been lost forever. The evidence for this material is subtle but unmistakable. It appears in several forms. First, there is the telltale signature of interstellar dust, detected as a faint, patchy dimming of the light from background stars. As starlight passes through these microscopic silicate and carbon grains, it gets preferentially reddened. The blue light is scattered away, making the star appear slightly redder than it actually is. This interstellar reddening is a classic tool for measuring dust, and when mapped across a cluster, it reveals a delicate, wispy structure of dust lanes that should not exist. Second, and even more telling, is the detection of specific emission lines from cold, neutral hydrogen gas. Using incredibly sensitive radio telescopes, astronomers have been able to pick up the faint 21-centimeter wavelength signature of this gas lingering within a handful of clusters. The presence of this cold hydrogen is a direct challenge to the idea that these systems are entirely void of the raw material of star formation, suggesting instead that some form of replenishment is actively at work. So, where is this material coming from? Astronomers have two primary, fascinating explanations, and both reveal the globular cluster as a far more dynamic system than its serene appearance suggests. The first and most intuitive source is the stars themselves. A globular cluster is a community of ancient stars, many of which are in the late, dramatic stages of their lives. Red giant and asymptotic giant branch stars are prolific factories of mass loss. They drive powerful, dusty stellar winds, gently blowing their own outer atmospheres out into space at speeds of tens of kilometers per second. In a single year, a single red giant can shed a mass equivalent to the entire planet Earth. While this material is initially ejected at high speed, the collective gravitational pull of the cluster can act to capture a fraction of it, especially if the ejection velocities are on the lower end. This process represents a slow but steady internal pollution, a form of stellar shedding that continuously seeds the interstellar environment with new gas and dust. Furthermore, other processes like the planetary nebula phase, where a dying star shrugs off a gorgeous shell of glowing gas, contribute their own material to this common reservoir. The cluster is in effect breathing out, very slowly filling its own streets with the exhaust of its aging stellar population. The second potential source is far more exotic and points to the cluster's interaction with the wider galaxy. This is the possibility of external accretion. As a globular cluster orbits the Milky Way, it doesn't travel through a perfect void. It plows through the diffuse, invisible halo of hot gas and the tenuous streams of material that permeate our galaxy's surroundings. While the density of this galactic cirrus is incredibly low, over billions of years the cluster's immense gravity can act as a net, slowly sweeping up and capturing this external material. Imagine a ship sailing through a faint mist. Over a long enough voyage, a detectable amount of water will condense on its decks. In the same way, the cluster's gravitational field can focus and trap this pristine galactic hydrogen, along with any dust grains it might contain, adding it to its internal inventory. This process would be a form of cosmic cannibalism on a microscopic scale, allowing the cluster to steal back a little of the material it lost so long ago. The presence of this material, regardless of its origin, has fascinating implications. For one, it provides a potential fuel source for future stellar generations, though the amounts are likely too small to trigger widespread star formation. More intriguingly, this dust and gas acts as a moderator and a tracer for the cluster's internal dynamics. The dust grains, for instance, are not stable. They are under constant assault from the intense ultraviolet radiation pouring out from the cluster's many hot stars. This radiation can literally blow the dust grains apart through a process called sputtering, or it can push them out of the cluster entirely through radiation pressure. The very fact that we see any dust at all means there must be a constant replenishment source to balance this rapid destruction. The gas, too, faces a hostile environment. If it gets too hot, either from stellar radiation or from shock heating, it will expand and escape the cluster's gravitational pull. The detection of cold, neutral hydrogen suggests that this gas has somehow managed to cool and condense into dense, shielded clumps, likely protected within the shadow of larger objects or in the deeper gravitational wells of the cluster. This ongoing cycle of injection, destruction, and removal turns the intracluster medium into a complex and ever-changing ecosystem, a faint whisper of activity in a system we once thought had entered a quiet and permanent retirement. And now we encounter a stellar phenomenon so extreme it pushes the very definition of a star to its limit. At the far, blistering end of the horizontal branch, in the most dynamically intense globular clusters, lies a small but unmistakable population of stars known as the blue hook stars. The name comes from their dramatic appearance on the Hertzsprung-Russell diagram. While a normal horizontal branch forms a relatively smooth horizontal line of stars in clusters like Omega Centauri and NGC 2808, this line doesn't just end, it makes a sharp vertical turn, hooking upward into a region of even higher temperatures and lower luminosities. These are not just hot stars, they are stellar infernos blazing with surface temperatures that can exceed 35,000 Kelvin, over 6 times hotter than our own Sun. Their existence is a direct challenge to our models of stellar old age, forcing us to consider that the final chapters of a star's life can be punctuated by late-stage cosmic reboots and dramatic, last-minute transformations. The journey to becoming a blue hook star is a tale of stellar survival against the odds, hinging on a critical and unstable event known as the helium flash. For a typical star, this flash occurs at the very tip of the red giant branch. After the star exhausts the hydrogen in its core, the core, now made of inert, degenerate helium, contracts and heats up until it reaches a temperature of around 100 million Kelvin. At this point, helium fusion ignites explosively in a violent but contained thermal pulse. This flash does not destroy the star. Instead, it stabilizes the core, allowing the star to settle onto the calm, steady state of the horizontal branch, where it burns helium in its core for tens of millions of years. But for the progenitors of blue hook stars, this standard script is thrown out the window. The key deviation is an episode of truly extreme mass loss before the helium flash occurs. Imagine a red giant star, bloated and unstable, having its outer hydrogen envelope stripped away at a ferocious rate. This could be driven by the intense stellar winds common in metal-poor stars, or it could be dramatically accelerated by a gravitational encounter with a binary partner or a passing star in the dense cluster core. So much mass is lost that by the time the degenerate helium core is ready to ignite, the star's remaining hydrogen envelope is extraordinarily thin, a mere wisp of its former self. This changes everything. With such a thin envelope, the star is no longer a classic red giant. It has already shrunk and heated up, looking more like a hot horizontal branch star even before the helium flash. Then the delayed helium flash finally happens, but not at the red giant tip. It occurs on what is called the extended horizontal branch, a location the star was never supposed to reach before this critical ignition. This is known as the flash mixing scenario. The violent energy release of the helium flash, now occurring in a star that is already compact and hot, is thought to drive a brief but profound episode of deep mixing. The star's interior is churned violently, bringing the products of the helium flash of freshly forged carbon and oxygen up to the surface, while simultaneously dragging the last remnants of the hydrogen envelope down into the hot interior to be burned. This mixing event is a stellar metamorphosis. It leaves behind a star that is now predominantly helium and carbon on its surface, with its hydrogen supply almost entirely eliminated. Stripped of its hydrogen blanket and powered by a newly stabilized helium-burning core, the star contracts further and heats up dramatically, launching it to the extreme temperatures we observe at the very blue end of the horizontal branch, creating that distinctive hook in the diagram. However, the flash mixing scenario is not the only pathway being explored. A compelling alternative suggests that binary star interactions are the primary architects of these exotic objects. In the crowded core of a globular cluster, the gravitational dance between stars is constant. Imagine a binary system where one star is a red giant and the other is a compact companion like a white dwarf. As the red giant expands, it can transfer its outer hydrogen envelope onto its partner. If this mass transfer is particularly efficient or rapid, it can strip the giant down to a bare helium core long before it has a chance to experience a helium flash in the traditional way. The result is a hot, helium-burning star that appears directly on the extreme horizontal branch, its position dictated by the precise amount of mass that was lost in the stellar interaction. In this narrative, the blue hook star is not the product of an internal convulsion, but the result of a cosmic theft, its appearance sculpted by the gravitational pull of a nearby companion. The presence of blue hook stars also provides a crucial link to the earlier mystery of multiple stellar populations. Their unique surface chemistry, often showing extreme enhancements of helium and heavy elements alongside a severe depletion of hydrogen, is a perfect match for the predicted outcome of the flash mixing model. This suggests they are the direct descendants of the later, helium-enriched generations of stars within the cluster. A star born with extra helium from the very beginning has a different internal structure and a hotter, faster evolution, making it far more susceptible to the extreme mass loss required to set it on the path toward the blue hook. Therefore, these stars are not just random oddities, they are the logical, if extreme, endpoint for a specific lineage of stars within the cluster's complex family tree. Their brilliant, ultraviolet heavy light serves as a beacon, illuminating the final consequences of the chemical pollution and dynamic interactions that have shaped these ancient stellar cities for billions of years, proving that even in its final moments, a star's life can be utterly transformed by the legacy of its birth and the company it has kept. And just when we thought we had mapped the final boundaries of these spherical star cities, the universe presents us with a shape that defies the very definition of a globular cluster. For centuries, the spherical form was the cluster's signature, a perfect symmetry born from gravity's relentless, isotropic pull. Every model of their formation and evolution was built upon this foundational geometry. But then, in a handful of rare and enigmatic systems, astronomers found something that shouldn't be there, a disk. The discovery of flattened, disk-like structures of stars or gas rotating within a handful of globular clusters is as shocking as finding a perfectly square planet. It immediately calls into question our most basic assumptions about how these objects come together and maintain their structure over billions of years, suggesting that the path to a stable, ancient star cluster can be far more varied and dynamic than our tidy spherical models ever allowed. The evidence for these disks is subtle but definitive, revealed through the precise orbital mapping made possible by observatories like Gaia. Instead of stars moving in every possible direction, creating a buzzing, formless swarm, astronomers detected a distinct and coordinated flow. In clusters like NGC 6397, a significant population of stars was found to be orbiting the cluster's center on paths that are all aligned within a single, preferred plane. It's the difference between a swarm of gnats buzzing randomly in the air and a flock of starlings wheeling in a coordinated, fluid mass. This isn't the gentle, overall rotation we've discussed in other clusters. This is a much more structured and flattened configuration, a distinct disk of stars embedded within the larger spherical halo of the cluster. In other cases, the disk signature comes not from stars but from cold gas. Radio telescopes have detected the 21-centimeter signature of neutral hydrogen gas that isn't just sitting passively between the stars. It is organized into a rotating disk, its motion betraying a clear, flattened geometry. This presents a double mystery. How did such a delicate structure form, and how has it managed to survive the relentless gravitational churning that should have randomized and destroyed it over the cluster's immense lifetime? The existence of these disks forces a complete re-evaluation of the cluster formation process. The standard model of a monolithic, spherical collapse from a single, turbulent gas cloud seems insufficient to explain such a coherent, rotating structure. Instead, astronomers are looking to more specific and dramatic origins. One leading theory suggests that these disk clusters are the products of a major merger in their deep past. Imagine two smaller, gas-rich protoclusters, each with its own inherent spin, on a collision course. If they don't just smash together chaotically, but instead engage in a slow, grazing encounter, their angular momentum could combine to form a single, larger object with a pronounced rotational axis and a disk-like structure. The stars and gas from both progenitors would settle into this new, shared plane of rotation, preserving the memory of the collision for billions of years. This scenario transforms these clusters from simple, isolated entities into the complex offspring of a cosmic union, their internal disk a fossil record of a long-ago galactic-scale accident. Another compelling possibility involves the specific conditions of the cluster's birth within its parent galaxy. If a globular cluster formed from a giant molecular cloud that was itself part of the rotating disk of a young galaxy, it would have been born with a tremendous amount of initial angular momentum. As this cloud collapsed under its own gravity, the conservation of that spin would have naturally flattened it, much like a spinning ball of pizza dough flattens into a disk. In this view, the disk cluster is not an anomaly but a pristine relic. It's a cluster that managed to avoid the major dynamical disruptions that would have randomized the orbits of its stars in other systems, preserving its primordial rotation and flattened shape as a direct link to the conditions of the early, disk-dominated universe. Its survival suggests it has lived a relatively quiet life, orbiting far from the galactic center and avoiding close encounters with other massive objects that would have stirred its stars back into a spherical configuration. The survival of these disks is in itself a profound puzzle. In a densely packed stellar environment, the constant gravitational nudges from passing stars, a process known as two-body relaxation, should, over billions of years, steadily erase any such delicate structure, puffing the disk back up into a sphere. The fact that we still see them means that either these clusters are dynamically younger than they appear, having experienced fewer disruptive encounters, or that some active mechanism is continually reinforcing the disk structure. This could be the ongoing influence of the cluster's own gravitational field, which might be subtly shepherding stars into aligned orbits, or perhaps the lingering influence of a central, intermediate mass black hole whose gravity helps maintain the ordered motion. The presence of a disk is therefore not just a static feature. It is a dynamic equilibrium, a delicate balance between the forces of order imprinted at birth and the forces of chaos that constantly work to dissolve it. Each of these disk-bearing clusters is a unique cosmic laboratory, a place where we can test the limits of gravitational dynamics and trace the specific, individual history of a stellar system that chose to remember its spin, defiantly holding onto its unique shape across nearly the entire age of the universe. Now we turn to a process that fundamentally reshapes a globular cluster from within, a slow-motion gravitational sorting that transforms its very structure over billions of years. This is the enigma of mass segregation, and it is the cosmic equivalent of a phenomenon you might see in a child's toy box. If you shake a container full of mixed nuts, the larger, heavier Brazil nuts will consistently rise to the top. Inside a globular cluster, a similar, though gravitationally inverted, process is constantly at work. Here, the heaviest and most massive stars, the stellar equivalent of Brazil nuts, do not rise to the top, but instead they steadily sink toward the very center of the cluster. This isn't driven by shaking, but by the relentless and impersonal exchange of energy as stars endlessly jostle and swing past one another in their intricate orbits. The mechanism is a fundamental process known as two-body relaxation. Every time two stars have a close gravitational encounter, they subtly alter each other's paths and speeds. In this cosmic game of pool, there is a statistical tendency for kinetic energy to be shared throughout the system in a specific way. More massive stars, due to their stronger gravitational pull, tend to lose kinetic energy in these encounters, slowing down just slightly. As they slow, their orbits decay and they migrate inward, journeying toward the dense core. Meanwhile, the lighter, low-mass stars often receive gravitational kicks that boost their speed, effectively heating them up and pushing them onto wider, more energetic orbits that take them further out into the cluster's halo. Over billions of years, this process acts like a gravitational filter, systematically sorting the stellar population by mass, the cluster's downtown core becomes an exclusive district for heavyweight stars, while the suburbs are populated by a lighter, faster-moving stellar populace. This isn't just a theoretical idea, we observe it directly. In spectacular Hubble images of clusters like 47 Tucani, you can see the breathtaking concentration of brilliant, massive stars in the core, while the fainter, redder dwarfs are more diffusely spread throughout the outer regions. However, the mystery, the true enigma, arises when astronomers compare these observations to sophisticated computer simulations of cluster evolution. The models, which encode all our understanding of Newtonian gravity and stellar dynamics, make very specific predictions about how pronounced this mass segregation should be after a given amount of time. They tell us how steep the gradient of stellar masses should be from the core to the outer halo. Yet, when we take the actual measurements, we often find a discrepancy. In some clusters, the mass segregation is far more extreme than the models allow. The core is even more dominated by heavy stars, and the halo is even more depleted of them than it should be. In other clusters, the opposite is true. The segregation is much weaker, with a surprising number of massive stars still lingering in the outer regions, defying their gravitational fate. This is not a minor accounting error. It is a sign that our models of these complex gravitational systems are missing a crucial piece of the puzzle. The universe is showing us that the simple, elegant process of two-body relaxation is being either accelerated or hindered by other, more dramatic forces at play within the stellar city. So, what could be causing this anomalous sorting? For clusters that show enhanced mass segregation, where the heavy stars have sunk even faster than expected, the prime suspect is the presence of a central, intermediate mass black hole. Imagine a gravitational anchor at the very heart of the cluster, a dark, massive object weighing thousands of solar masses. Its immense pull would create a steeper gravitational well, accelerating the orbital decay of nearby massive stars and drawing them into the core much more efficiently. It would act like a drain at the bottom of a sink, pulling the heaviest objects down with a stronger force than gravity from stars alone could provide. Another fascinating possibility involves the initial conditions of the cluster itself. Perhaps some clusters were born with their massive stars already concentrated in the center, a phenomenon known as primordial mass segregation. If the cluster formed from a cloud where the densest central regions collapsed into the most massive stars first, then the sorting we see today isn't just the result of slow dynamical evolution. It was partly imprinted at birth. The cluster would have started its life already segregated, and the billions of years of dynamical evolution have only served to enhance this pre-existing structure. On the other hand, for clusters that show weaker than expected mass segregation, the explanation points towards a more chaotic and violent history. The primary culprit here is likely the dynamical heating of the cluster by binary star systems. In the dense core, binary stars are not just common, they are powerful gravitational engines. When a single star interacts with a tight binary, the complex three-body dance often results in the single star being flung out at high speed, while the binary pair becomes more tightly bound. This process injects a tremendous amount of kinetic energy back into the cluster's core. It's like stirring a pot that is trying to settle. This constant gravitational heating can effectively counteract the slow, sedate process of mass segregation, preventing the massive stars from sinking as quickly as they would in a more tranquil environment. The core is kept puffed up and dynamically active, which allows a greater number of massive stars to remain in the wider halo for much longer. Furthermore, if a cluster has experienced a recent close encounter with the Milky Way or another cluster, the resulting tidal shock could have violently stirred its stellar population, scrambling the partially sorted structure and resetting the segregation clock. The observed level of mass segregation in a globular cluster is therefore not just a simple function of its age. It is a delicate balance between the relentless, ordering force of two-body relaxation and the disruptive, chaotic forces of binary interactions and galactic tides. By measuring precisely how the stars are sorted, we can read the history of these competing influences, turning the cluster's internal structure into a forensic record of the dynamic events that have shaped its long life. Nestled within the ancient stellar populations of globular clusters are cosmic lighthouses whose rhythmic pulsations provide some of the most reliable measurements in all of astronomy, the variable stars. These are not static points of light. They are stars that breathe, expanding and contracting in a regular, predictable cycle, causing their brightness to rise and fall over periods that can range from hours to months. The two most crucial types for understanding clusters are the Lyrae variables and the type Roman II Cepheids. Lyrae stars are the workhorses of cosmic distance measurement within our own galaxy and its halo. They are old, metal-poor stars that have evolved off the main sequence and into a specific, unstable region of the Hertzsprung-Russell diagram where they pulsate. The true power of these stars lies in a beautifully simple relationship known as the period-luminosity relation. It was discovered that the intrinsic brightness or absolute magnitude of an Lyrae star is directly tied to its pulsation period, the time it takes to go from bright to dim and back again. A star with a longer period is inherently more luminous. This means that simply by observing how long its pulsation cycle takes, astronomers can determine precisely how bright the star should be. By then comparing this known intrinsic brightness to how faint the star appears from Earth, they can calculate its distance with remarkable accuracy. It's like knowing the exact wattage of a light bulb. By seeing how dim it looks from far away, you can figure out just how far away it must be. This makes Lyrae stars perfect standard candles for pinning down the distances to the globular clusters they inhabit, which in turn helps us map the three-dimensional structure and vast scale of the Milky Way's halo. Type Roman II Cepheids, which are also found in these old populations, serve a similar role but for longer periods and greater luminosities, acting as a crucial rung on the cosmic distance ladder that connects galactic measurements to distances far beyond. These variable stars do more than just chart space, they also act as exquisite chronometers. The very presence and properties of Lyrae stars in a cluster provide a powerful, independent check on its age. Because these stars represent a specific, short-lived phase in the evolution of low-mass stars, the point at which stars are leaving the horizontal branch to become Lyrae variables is exquisitely sensitive to the cluster's overall age. By modeling stellar evolution and comparing the predicted number and properties of Lyrae variables to what is actually observed, astronomers can cross-verify the ages derived from the main sequence turnoff, creating a robust, multi-method dating system that consistently points to these clusters being among the oldest structures in the universe. However, this clockwork regularity is not always perfect, and the deviations are where the real mystery lies. For over a century, astronomers have been meticulously tracking the pulsation periods of these stars, and in many cases they have detected subtle but persistent changes. The timing of the brightening and dimming is not perfectly constant over decades. The period is either gradually increasing or decreasing. This phenomenon, known as a period change, is a direct window into the real-time evolution of the star itself. In theory, this is expected. As a star ages and its internal structure changes, as it burns through its nuclear fuel and alters its chemical composition, its pulsation properties should naturally shift. A star evolving toward a redder, larger state might see its period lengthen, while one contracting and heating up might experience a shortening period. These evolutionary period changes are predicted by models, and observing them is like watching a stellar clock tick in slow motion, offering a rare glimpse of stellar evolution happening on a human timescale. Yet, the observed period changes often defy these straightforward evolutionary explanations. The changes can be too rapid, too large, or even switch direction in a way that simple models cannot account for. This is the heart of the puzzle. One compelling explanation for these anomalous shifts brings us back to the uniquely crowded environment of the globular cluster, the Blasco effect. This is a secondary modulation, a long-term variation in the amplitude and sometimes the period of the pulsation itself, causing the light curve to look different over cycles that can span tens to hundreds of days. The physical mechanism behind the Blasco effect has been a subject of intense debate for decades, but one leading theory involves the star's own rotation and its complex magnetic field. In a dense cluster, stellar encounters can spin up stars, and this rapid rotation could interact with the star's pulsations and magnetic field in a complex resonance, creating this beating, modulated pattern in its light output. The Blasco effect, therefore, might not be an intrinsic property of the variable star in isolation, but a symptom of its dynamic history within the stellar crowd. An even more dramatic cause of period anomalies points directly to the social dynamics of the cluster, the presence of an unseen binary companion. If an Lyrae star is gravitationally bound to another star, the two will orbit a common center of mass. From our vantage point, the rhythmic pulsation of the variable star will be periodically Doppler shifted, its light waves compressed as it moves toward us and stretched as it moves away. This introduces a regular, repeating delay or advance in the observed timing of its brightness peaks, a phenomenon known as a light travel time effect. By meticulously decoding these timing variations, astronomers can infer the presence of the invisible companion, measure the orbital period, and even estimate its mass. This has revealed that a significant fraction of these seemingly solitary pulsating stars are actually in binary systems, a discovery that profoundly impacts our understanding of both stellar evolution and the dynamical formation of binaries in these dense environments. The gradual period change we observe could then be a combination of the star's intrinsic evolution and the subtle gravitational tugs from its partner, a complex dance that leaves its signature in the starlight. Furthermore, the constant gravitational nudges in a cluster core can directly alter a star's pulsation. A close encounter with another star can tidally perturb the variable star, slightly altering its shape or internal structure and triggering an immediate, discrete jump in its pulsation period. It's as if someone bumped into a grandfather clock, causing its pendulum to swing just a little differently. These stochastic, environment-driven changes overlay the smooth, predictable evolutionary shifts, creating a rich and noisy signal that astronomers must untangle. The study of these variable star anomalies transforms them from simple distance markers into sophisticated diagnostic probes. By analyzing the precise patterns of their period changes, we can uncover the hidden population of binary stars, gauge the frequency of stellar interactions, and even probe the internal structure and rotation of the stars themselves. These cosmic clocks, with their occasional mysterious hiccups, tell a far more detailed story than just the passage of time. They reveal the dynamic and interactive life that persists within these ancient celestial cities. But the story of a globular cluster isn't confined to the sharp, glittering boundary we see in photographs. For every star securely bound within the cluster's gravitational embrace, there are others that have been cast out, sent drifting into the lonely expanse of the galactic halo. These are the extra-tidal stars, and their discovery paints a far more expansive and dynamic portrait of these ancient systems. The traditional view defined a cluster by its tidal radius, the theoretical boundary where the Milky Way's gravitational pull finally overcomes the cluster's own gravity. Beyond this line, no star should be able to remain bound to the cluster. Yet, when astronomers meticulously map the regions just outside this boundary, they find a faint but significant population of stars that share the exact same chemical fingerprint and motion through space as the cluster's core members. These aren't random field stars, they are escapees, recent immigrés from the stellar city, and their existence reveals that clusters are not closed systems, but are constantly and slowly evaporating, shedding their members in a steady stellar wind. The primary engine driving this stellar exodus is the same relentless gravitational dynamics that shape the cluster's interior. Through countless gentle encounters, stars are constantly exchanging energy. Often, this results in a low-mass star receiving a series of gravitational kicks that gradually pump energy into its orbit. Over millions of years, this star's path becomes more and more elongated, carrying it further and further from the safety of the core on each passage. Eventually, on one of these wide, looping orbits, it ventures beyond the tidal boundary. At that moment, the gentle but persistent pull of the Milky Way takes over, and the star is lost, never to return to the cluster. It joins a growing stream of stellar refugees, drifting away on an independent orbit around the galaxy. This isn't a sudden, violent ejection, but a slow, almost gentle process of leakage, a natural and inevitable consequence of a gravitationally relaxed system. The presence of these extra-tidal stars just beyond the cluster's edge is the direct, observable evidence of this ongoing evaporation, a process that will ultimately lead to the cluster's complete dissolution over trillions of years. However, the plot thickens dramatically when we look much further out. In several clusters, deep imaging surveys have detected a sparse, ghostly halo of stars extending astonishingly far beyond the classical tidal radius, in some cases stretching for hundreds of light years. This is not a tight stream of recent escapees. This is a vast, diffuse cloud of stars that seems to still be gravitationally associated with the cluster, albeit very weakly. The existence of this extended stellar halo presents a much greater challenge to explain. One compelling theory is that these are the lingering echoes of the cluster's own birth. When a globular cluster first formed, it may have been embedded within a much larger, low-density envelope of stars, a sort of stellar cocoon. While the dense core quickly tightened into the sphere we see today, this outer envelope was too loosely bound to follow, remaining as a faint, distant memory of the cluster's initial, more expansive form. Another possibility is that this halo is composed of stars that were stripped from the cluster not by internal dynamics, but by external forces. As the cluster orbits the galaxy, it doesn't move smoothly. It experiences gravitational shocks as it plunges through the galactic disk or swings past the central bulge. These shocks can violently strip away vast swaths of stars from the cluster's outer layers in discrete, dramatic events, rather than through slow evaporation. The resulting halo would be a collection of stars ripped away during these past traumatic encounters, now slowly drifting apart but still tracing the cluster's broader gravitational influence. The most spectacular manifestation of this process is the phenomenon of tidal tails. These are not random halos, but colossal, river-like structures of stars that stretch for thousands of light years across the sky, flowing ahead of and behind the cluster in its orbit. They are the ultimate expression of extra-tidal stars, a visible record of the cluster's dissolution written across the galactic halo. The creation of these tails is a direct tug of war between the cluster and the galaxy. As the cluster moves, the Milky Way's tidal forces act to stretch it, pulling stars away from both the leading and trailing sides. These stripped stars don't just fly off randomly, they continue to orbit the galaxy on paths very similar to the parent cluster, forming these long, coherent streams. By studying the length, density, and shape of a tidal tail, astronomers can read the cluster's history like a book. A long, well-populated tail indicates an old cluster that has been losing stars for a very long time. Gaps or kinks in the tail can signal past encounters with dark matter substructure or the gravitational influence of the Milky Way's spiral arms. The Palomar 5 cluster is the classic example. Its spectacular tails, spanning over 20 degrees on the sky, show that it has already lost the vast majority of its stars to this process, and the cluster we see today is just the fading core of a once much larger object. These extra-tidal stars, from the recent escapees to the vast tidal streams, transform our understanding of a globular cluster from an isolated island into an active participant in the galactic ecosystem. They are a primary source of the stars that populate the Milky Way's own halo, contributing to its growth and chemical enrichment. Furthermore, they serve as powerful forensic tools. Because these stars share the cluster's unique chemical composition, they act as tracers, allowing us to map the subtle contours of the galaxy's gravitational field in 3 dimensions. The precise paths of these streams are exquisitely sensitive to the distribution of dark matter in the Milky Way's halo. Any deviation from a smooth, predictable orbit is a potential sign of a close pass with an unseen clump of dark matter or even a past, undiscovered dwarf galaxy. In this way, the faintest stars, those cast out from their ancient homes, are helping us to chart the invisible scaffolding of the entire cosmos, proving that even in their dissipation, globular clusters have a profound story to tell. And now we venture to the stellar graveyards of these ancient clusters, to the silent, fading embers that represent the final state for the vast majority of stars. These are the white dwarfs, the Earth-sized cores of collapsed stars, slowly cooling into oblivion over trillions of years. In a globular cluster, this graveyard is not a uniform collection of tombstones. It is a diverse and revealing population, holding within its faint glow a detailed record of how stars of all kinds meet their end. The study of these white dwarfs has uncovered peculiarities that are directly tied to the extreme social environment they were born into, including some that are bizarrely massive and others that are mysteriously cool, each telling a different story about the frantic final stages of stellar life in a dense star city. A typical white dwarf is the exposed core of a star that was once like our Sun. After a star exhausts its nuclear fuel and puffs off its outer layers as a planetary nebula, all that remains is this incredibly dense object, supported against its own immense gravity by a quantum mechanical effect known as electron degeneracy pressure. There is a critical upper limit to this pressure, known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. If a white dwarf were to exceed this mass, electron degeneracy pressure would fail, and the star would collapse further into an even denser neutron star or black hole. This means that isolated white dwarfs are all, by necessity, below this limit. But in a globular cluster, the rules are different. Here, astronomers have identified a significant population of white dwarfs that are unusually massive, pushing right up against this Chandrasekhar limit. The existence of these heavyweights points directly to a dramatic and violent origin story, one that could only occur in a place where stars are constantly interacting. The primary pathway to creating these supermassive white dwarfs is through stellar collisions and mergers. Imagine 2 lower mass stars, each on its own evolutionary path to becoming a standard white dwarf. In the crowded core of a cluster, a close gravitational encounter could send them on a collision course. When they merge, their cores combine. If the total mass of the merged core is still below the Chandrasekhar limit, the result is a single, more massive white dwarf. This isn't a gentle process. It's a fiery amalgamation that can also reignite nuclear fusion on the surface of the new object, potentially creating a temporary phenomenon known as a luminous red nova. Alternatively, the path to a massive white dwarf can occur in a binary system through a process called mass transfer. If a white dwarf is in a tight orbit with a companion star, it can act as a gravitational vampire, slowly siphoning material from its partner. As this hydrogen-rich gas accumulates on the white dwarf's surface, it can periodically ignite in a thermonuclear explosion we observe as a nova. While a nova blast ejects some material, a significant amount can be retained, gradually increasing the white dwarf's mass over millions of years. This slow and steady accretion can also build up a white dwarf to near the Chandrasekhar limit. The presence of these massive white dwarfs is therefore a direct tracer of the dynamical history of the cluster. A cluster with many such objects is one that has experienced a high rate of stellar collisions and complex binary interactions, its graveyard populated by the products of cosmic violence. On the opposite end of the spectrum, we find white dwarfs that are unusually cool. A white dwarf has no internal energy source. It simply radiates away the residual heat from its earlier life, cooling and dimming over time. In principle, the coolest white dwarfs in a cluster should be the oldest, providing a direct way to date the very first stars that formed. However, the cooling process in a cluster is not as straightforward as it is in isolation. Observations have revealed that in some clusters, the white dwarf cooling sequence, the graceful arc they trace on a color magnitude diagram as they fade, shows a curious kink or pile up. Instead of a smooth, predictable curve, there is a point where an unexpected number of white dwarfs appear to be cooler and redder than they should be for their luminosity, as if their cooling has been somehow delayed or accelerated. This anomaly provides a crucial clue about the internal composition of these stars and the environments that shaped them. The explanation for this strange cooling behavior likely lies in the final, dramatic act of the star's life, the loss of its outer envelope. When a star becomes a red giant, it develops a deep, convective envelope that acts like a boiling pot. The precise point at which this star loses its envelope to become a white dwarf determines the composition of the white dwarf's outer layers. If the envelope is lost very late in the process, the white dwarf will be born with a thick blanket of helium. If it is lost earlier, the white dwarf will have a thinner helium layer or may even have its carbon-oxygen core directly exposed. The rate at which a white dwarf cools is exquisitely sensitive to the composition of this outer blanket. A thin layer of helium or hydrogen allows the internal heat to escape more readily, causing the white dwarf to cool rapidly at first. However, as it cools, the interior material can begin to crystallize, transitioning from a liquid to a solid state. This crystallization releases latent heat, much like water releasing heat when it freezes into ice. This sudden injection of energy can slow down the cooling process dramatically, causing the white dwarf to appear to pause on the cooling sequence, creating the observed pile-up of stars at a specific temperature and luminosity. The presence and shape of this pile-up tells us about the specific distribution of masses and compositions in the white dwarf population, which in turn reflects the mass loss histories of the progenitor stars, a process that may have been influenced by the cluster's dense environment through enhanced stellar winds or binary interactions. Furthermore, the dense environment of a globular cluster can directly alter the fate of these white dwarfs through dynamical encounters. A lone white dwarf in the galactic field will cool peacefully and undisturbed. But in a cluster, a white dwarf can be involved in a gravitational encounter that strips away its thin outer layers of hydrogen or helium. This is like peeling an onion, exposing the hotter, carbon-rich interior to space. Such a bare white dwarf would instantly appear much hotter and bluer than its age would suggest, before resuming its cooling from a different starting point. This can scatter white dwarfs across the cooling sequence, creating outliers that don't fit the standard model. The study of these diverse white dwarf populations, from the massive products of mergers to the strangely cooling relics, transforms these faint embers into one of the most powerful tools at an astronomer's disposal. By reading their collective properties, we can peer back to the very first stars that died in the cluster, using the coolest white dwarfs to establish a firm lower limit on the cluster's age, a date that consistently confirms these objects are among the oldest structures we can observe in the entire universe. And now we delve into one of the most subtle and telling pieces of evidence hidden within the stellar motions of these ancient cities, the discovery of kinematically cold substructures. Imagine a bustling urban square where thousands of people are milling about in every direction, a scene of pure chaos. But within that crowd, you notice a small group of people all walking in lockstep, moving together with a shared purpose and identical speed. That is the essence of a kinematically cold substructure. Within the overall hot, random buzz of stellar velocities in a globular cluster, astronomers have found distinct groups of stars that are moving with remarkably similar speeds and directions. They are stellar squads moving in coordinated motion that stands out starkly against the chaotic background dance. This finding is like discovering a distinct accent or dialect within a large, noisy population. It signals a separate origin, a shared history that sets this group apart from the crowd. The cold in the name refers to their low-velocity dispersion, meaning all the stars in the group have very little random motion relative to each other. They are all moving as a single, coherent stream within the cluster. The survival of this delicate order for billions of years is just as astonishing as its existence, pointing to a formation history far more complex than a single, monolithic collapse. The primary explanation for these coordinated stellar squads is a dramatic story of cosmic assimilation, the idea that the globular cluster did not form all of its stars itself, but instead swallowed up a smaller stellar system long ago. The most likely candidate is a dwarf galaxy. In the early, violent universe, dwarf galaxies were common, and globular clusters with their immense gravity would have been formidable predators. If a small, fragile dwarf galaxy passed too close to a massive globular cluster, the cluster's tidal forces could have ripped it apart, stripping away its stars. However, if this accretion event was a slow, grazing encounter, the dwarf galaxy's core, the most tightly bound part of its stellar population, could have been ingested largely intact. The stars from this devoured core would have entered the cluster with their original, shared motion largely preserved. They would have been born together in the dwarf galaxy, sharing its specific velocity, and that coordinated motion would have acted as a kind of gravitational inertia, allowing them to travel as a group through the cluster for eons before dynamical friction could fully mix them in. The presence of these cold substructures is therefore a fossilized imprint of a long-ago act of galactic cannibalism, a ghostly signature of a smaller system that was consumed and whose stars now roam within a larger host, still remembering their shared ancestral home. But the plot thickens when we consider another possibility, that these cold streams are not the remnants of an external victim, but rather the preserved cores of the cluster's own formation. The standard model of a single, rapid collapse from a giant gas cloud might be an oversimplification. Instead, a massive cluster could have formed from the merger of several smaller, distinct star-forming clumps within a single giant molecular cloud. Imagine several small stellar villages, each forming in its own pocket of the cloud, each with its own slight spin and velocity. As these villages fell together to build the larger cluster city, the stars from each individual clump would have arrived with their own shared kinematic identity. In the tumultuous process of merger, the outer stars from these clumps would have been stripped away and their motions randomized, but the densest cores of these groups might have survived, their stellar populations remaining kinematically cold as they were absorbed into the new, larger structure. This scenario paints a picture of a globular cluster's birth as a hierarchical process, a bottom-up construction from smaller building blocks, with the cold substructures representing the last surviving, unassimilated cores of those original construction units. Detecting these subtle streams is a feat of modern astrometric precision, made possible almost entirely by the Gaia Space Observatory. Gaia's mission is to map the positions, distances, and motions of over 1 billion stars in our galaxy with unprecedented accuracy. For nearby globular clusters, Gaia can measure the tiny, proper motions of individual stars, their actual movement across the sky, with stunning clarity. To find a kinematically cold substructure, astronomers take this vast dataset of stellar motions and use sophisticated statistical algorithms to filter out the general, hot motion of the cluster. They look for statistical overdensities not just in physical space, but in velocity space. It's like listening to a symphony and using a computer to isolate a single violin section playing a harmonious line that is distinct from the rest of the orchestra. When they find a group of stars that are not only close to each other in the cluster, but also share an almost identical velocity vector, they have identified a cold substructure. This is not something visible in a direct image. It is a pattern revealed only through the meticulous, long-term tracking of stellar paths, a hidden architecture written in the language of motion. The implications of these findings are profound, as they directly challenge the long-held view of globular clusters as the simplest stellar populations in the universe. The presence of multiple kinematically distinct groups within a single cluster provides irrefutable evidence that its current form is the product of a complex evolutionary path involving either multiple merger events or a multi-clump formation process. This forces us to see these clusters not as pristine, single-generation fossils, but as composite objects, galactic archaeologists that have preserved the DNA of their own assembly history in the motions of their stars. Furthermore, these cold streams serve as powerful probes of the cluster's gravitational field. Because their stars are moving in a coherent pack, they are exceptionally sensitive to the underlying mass distribution, including the potential presence of a central intermediate mass black hole or concentrations of dark remnants. Any slight deviation in the stream's path or velocity can be used to map the invisible gravitational landscape of the cluster's core. In this way, these quiet, coordinated groups of stars become dynamic tracers, illuminating not only their own past but also the hidden forces that continue to shape the cluster from within, revealing a level of structural complexity we are only just beginning to decipher. But to truly grasp why this event is so pivotal, we need to step inside the heart of an aging star. After billions of years of steadily burning hydrogen in its core, a star like our Sun faces a fuel crisis. The hydrogen is exhausted, leaving behind a core of inert helium ash. With the central fusion engine shut down, the core can no longer support itself against the immense force of gravity, and it begins a violent contraction. This collapse releases a torrent of gravitational energy, which heats the core to staggering temperatures and also ignites a shell of hydrogen fusion just outside of it. The energy pouring from this shell is so tremendous that it forces the star's outer layers to expand to hundreds of times their original size, transforming the star into a brilliant, bloated red giant. Meanwhile, deep within, the helium core continues to contract and heat up. Because it is so densely packed, it enters a state known as electron degeneracy, a bizarre quantum mechanical condition where the pressure is no longer dependent on temperature. The core is now like a ticking bomb, heating up but unable to expand to cool itself down. The temperature soars past 100 million Kelvin, and at this critical point, helium fusion ignites. But in a degenerate core, this ignition is not a gentle turning on of a new engine. It is a runaway thermonuclear explosion. In a matter of seconds, a substantial portion of the core undergoes a violent fusion chain reaction, releasing as much energy as the star has emitted over the previous 100 million years. This is the helium flash, a stellar heart attack of cosmic proportions. Now, in a typical, isolated star, this cataclysm is entirely contained. The incredible burst of energy does manage to lift the core out of its degenerate state, allowing it to expand and settle into a stable, quieter phase of helium burning. The outer layers of the star adjust, and the star moves from the red giant branch to the horizontal branch on the Hertzsprung-Russell diagram. From the outside, the transition can appear relatively smooth. But within a globular cluster, the story can be radically different. The unique conditions of these dense environments, specifically the prevalence of multiple stellar generations and the possibility of dramatic mass loss, can fundamentally alter both the timing and the consequences of this flash, turning it from an internal crisis into a transformative event that reshapes the star's entire future. One of the most dramatic ways a cluster environment intervenes is by forcing the helium flash to occur in an entirely unexpected location. This is the extraordinary path that leads to the creation of the blue hook stars we discussed earlier. Imagine a red giant star in a cluster that is experiencing extreme mass loss. This could be due to its own powerful stellar winds, which are more potent in the metal-poor stars common in clusters, or it could be dramatically accelerated by a gravitational encounter with a binary partner or a passing star. So much of its outer hydrogen envelope is stripped away that the star shrinks and heats up significantly, even before its core is ready to ignite helium. It leaves the red giant branch prematurely and moves onto what's called the extended horizontal branch. It's already a hot, compact star when its degenerate helium core finally reaches the ignition temperature. The resulting helium flash, instead of happening deep within a bloated red giant, now occurs in this much more evolved and exposed star. This is the flash mixing scenario, the violent energy release of the flash erupting in a star that is already compact is thought to trigger a brief but profound episode of deep mixing. The star's interior is churned like a blender, pulling the remaining hydrogen envelope down into the hot interior to be burned and pushing the newly forged carbon and oxygen from the flash up to the surface. This stellar metamorphosis leaves behind a star that is now predominantly helium and carbon on its surface, with its hydrogen supply almost completely eliminated. Stripped of its hydrogen blanket and powered by its new helium-burning core, the star contracts further and heats up dramatically, launching it to the extreme temperatures we observe at the very blue end of the horizontal branch. The helium flash, in this case, isn't a contained event. It's a catalyst for a complete stellar rebirth, creating an object that defies our standard classifications. The chemical makeup of the cluster itself can also dictate the nature of the flash. Stars from later generations within a cluster are born with extra helium in their outer layers, a legacy of the pollution from the first massive stars. This higher initial helium abundance changes the star's internal structure from the very beginning. A helium-rich star has a smaller, denser core for the same total mass. This means it evolves more rapidly and its core will reach the ignition temperature for helium fusion at a different point in its evolution compared to a star with standard composition. The flash itself might be more or less violent, and the star's subsequent journey onto the horizontal branch will be different, often resulting in a hotter, bluer star. This provides a direct link between the multiple population phenomenon and the specific way stars die within the cluster. The helium flash acts as a filter, processing stars from different chemical lineages in slightly different ways, and the resulting population of horizontal branch stars is a direct map of those ancestral differences. Furthermore, the incredible density of stars in a cluster core introduces the possibility of external triggers. While the helium flash is an inevitable evolutionary phase, a close gravitational encounter could potentially perturb a star on the verge of the flash, subtly altering the core conditions. While it's unlikely that an encounter could directly cause the flash, the tidal forces from a passing star could influence the rate of mass loss from the red giant's envelope in its final moments. If this encounter strips away just a little more mass right before ignition, it could be the difference between a star experiencing a standard flash and one that undergoes the dramatic flash mixing that creates a blue hook star. In this social environment, the most personal and violent moment in a star's life can be influenced by the gravitational nudges of its neighbors, a testament to the fact that in a globular cluster, no star truly evolves in isolation. The helium flash, therefore, is far more than a simple nuclear physics milestone. It is a sensitive probe, a dramatic event whose outcomes are exquisitely tuned by the star's birth composition, its mass loss history, and the dynamic social pressures of the ancient stellar city it calls home. Yet another profound mystery is written in the faint light of the cluster's most ancient stars, a puzzle that takes us back to the universe's first few minutes and involves an element so simple it seems almost out of place in this cosmic drama. This is the story of the Spite Plateau, a discovery that simultaneously confirms and confounds our understanding of the Big Bang. In the late 1970s, astronomers Monique and Francois Spite made a remarkable observation. When they measured the amount of lithium in the atmospheres of the oldest, most metal-poor stars in the galactic halo stars that are the cousins of those in globular clusters, they found something unexpected. Despite these stars having vastly different temperatures, gravities, and overall metal contents, their lithium abundance was virtually identical. When plotted on a graph, the data points formed a flat, unwavering line, a plateau. This consistency was stunning. Lithium is the third lightest element, and in the turbulent interiors of stars, it is easily destroyed at temperatures above 2.5 million Kelvin. The fact that these otherwise dissimilar ancient stars all showed the same lithium levels strongly suggested they were preserving a relic from their birth. This pristine lithium, the Spites argued, was primordial, a fossil from the very first nuclear reactions that occurred when the universe was only a few minutes old. The Spite Plateau thus became a cornerstone of modern cosmology, a direct observational anchor for the theory of Big Bang nucleosynthesis, the process that forged the first atomic nuclei. This primordial lithium acts as a cosmic dipstick, allowing us to measure the conditions of the infant universe. The physics of Big Bang nucleosynthesis is exquisitely precise. Based on the measured density of ordinary matter in the cosmos, our models calculate exactly how much of each light element should have been cooked up in that initial fiery crucible. The predictions for hydrogen and helium-deuterium match the observations spectacularly well, but for lithium-7 there is a glaring and persistent problem. The amount of lithium we see on the Spite Plateau in these ancient stars is consistently about 3 times lower than what the Big Bang models predict. This is the lithium problem in its purest form. We have a robust, successful theory that gets almost everything right, and a set of pristine, ancient stellar fossils that should be showing us the unaltered chemical makeup of the early cosmos, yet the numbers simply do not add up. It's as if we had a perfect historical record stating a certain king had 3 chests of gold, but when we open the royal vault, we only find 1. The question is, was our historical record wrong, or did something happen to the other 2 chests after they were minted? This discrepancy forces scientists to explore 2 profound possibilities, each with monumental implications. The first is that our understanding of nuclear physics in the first 3 minutes is incomplete. Perhaps there are unknown nuclear reaction rates or particles involved in the early universe that could have suppressed the production of lithium-7. Some theorists have proposed the existence of exotic particles, like certain types of dark matter, that could have interacted with the primordial soup, altering the delicate balance of reactions that built the first nuclei. If this is true, then the missing lithium is not an error, but a clue pointing toward new physics beyond the standard model, a hidden ingredient in the recipe for the cosmos itself. The second, and equally compelling, possibility is that our stellar laboratories are not as pristine as we think. Perhaps these ancient stars, despite their age and simple composition, have been silently destroying their lithium over the billions of years of their lives. This would mean the Spite Plateau does not show the true primordial value, but a value that has been universally depleted by a specific, shared process. The most likely culprit is a slow, subtle mixing of the stellar material. Stars are not perfectly still. They can have gentle internal currents that circulate material from the surface down into hotter interior regions. Even a very slow circulation over billions of years could transport surface lithium down to a layer hot enough to destroy it, effectively burning away a portion of their primordial inheritance. The remarkable uniformity of the Spite Plateau would then be explained because all these old, low-mass stars share a similar internal structure and would experience this depletion in the same way, all converging on the same lower lithium level regardless of their initial starting point. The environment of a globular cluster adds a fascinating layer of complexity to this detective story. Could the dense, dynamic life within a cluster influence this lithium depletion? It's a distinct possibility. The same gravitational encounters that spin up stars to create blue stragglers could also stir a star's interior, potentially enhancing the mixing process and driving lithium down to its doom more efficiently than in an isolated star. A star that has lived a quiet life in the cluster's outskirts might retain a slightly different lithium abundance than a star of identical age and composition that has resided in the chaotic core, constantly buffeted by gravitational interactions. This turns the measurement of lithium in cluster stars into a potential new diagnostic tool, not just for cosmology but for stellar dynamics. By mapping subtle variations in the spite plateau from star to star within a cluster, we might be able to trace the dynamic history of individual stars, reading their personal stories of gravitational encounters written in the delicate balance of this fragile element. The spite plateau, therefore, is far more than a simple number on a graph. It is a delicate interface between the largest scales of cosmology and the most intimate details of stellar evolution. A puzzle whose solution requires us to understand everything from the universe's first moments to the quiet, internal workings of its oldest shining sentinels. Far from being invulnerable fortresses, these ancient stellar cities face a recurring and devastating threat on their long journeys around the galaxy, a destructive force that can tear them apart from the outside in. This is the phenomenon of tidal shock, and it represents one of the most violent and rapid mechanisms for altering, or even completely destroying, a globular cluster. To understand this, we need to picture a cluster's orbit, which isn't a simple, serene circle around the Milky Way center. Many clusters follow highly elliptical paths that plunge them right through the dense, thin plane of our galaxy's disk and then swing them perilously close to the crowded central bulge before soaring back out into the galactic halo. It's during these close encounters that the cluster experiences a gravitational ambush. A tidal shock isn't a single, sharp pull. It's a dramatic difference in the gravitational force acting on the near side of the cluster versus its far side. As the cluster passes through the galactic disk, the stars on the side closest to the disk feel a much stronger pull from the concentrated mass there than the stars on the opposite side. This difference in force doesn't just stretch the cluster, it acts like a powerful, sudden jerk, imparting a burst of energy to every single star in the system. Imagine holding a snowball by the top and bottom and then suddenly yanking your hands apart. The snowball doesn't just elongate, it flies apart. In a globular cluster, this gravitational yank doesn't necessarily pulverize individual stars, but it violently shakes the entire system, injecting so much random kinetic energy into the stellar orbits that vast numbers of stars are given the extra velocity they need to escape the cluster's gravitational grasp forever. The aftermath of such a shock is a rapid and dramatic mass loss, a form of stellar evaporation accelerated to an extreme degree. Unlike the slow, internal process of two-body relaxation that gradually heats up low-mass stars, a tidal shock is an external, brutal event that affects stars of all masses throughout the cluster. The stars that are most vulnerable are those already on loosely bound orbits in the cluster's outer halo. The shock doesn't gently nudge them, it kicks them hard. In a single, close passage, a cluster can lose several percent of its total mass almost instantaneously in cosmic terms. But the damage isn't just about the stars that are immediately ejected. The shock fundamentally alters the cluster's internal energy balance. The entire system is heated up, making it puffier and less centrally concentrated. This makes it even more susceptible to the next tidal shock it encounters on its subsequent orbit. This creates a vicious, runaway cycle of destruction. With each passage, the cluster becomes less massive and more diffuse, which in turn makes it even easier for the next tidal shock to strip away more stars. A cluster that might have survived for trillions of years through slow evaporation can be completely dismantled in just a few billion years if its orbit subjects it to regular, punishing encounters with the galactic disk or bulge. We can actually see the ghosts of this process in the sky today. The most famous example is the cluster known as Palomar 5. It's a wispy, ethereal object, a pale shadow of a once great globular cluster. What makes Palomar 5 so spectacular is not the cluster itself, but its incredible tidal tails. These are two vast, river-like streams of stars stretching across over 20 degrees of the sky, containing far more stellar mass than the cluster's dim core. These tails are the direct result of tidal shocking. As Palomar 5 orbits the galaxy, its repeated passages through the galactic disk have systematically stripped its stars away, pulling them out in these long, leading and trailing streams. The cluster we see today is just the dying core, a temporary holding cell for stars that will soon join the spectacular tails. Palomar 5 is a cluster in its final death throes, and its magnificent debris streams serve as a stark monument to the destructive power of the galactic tide. It shows us that destruction can be beautiful, and that even in its dissolution, a cluster can create some of the most striking and scientifically valuable structures in the galaxy. The destructive power of a shock depends heavily on the cluster's internal structure and its specific orbital path. A dense, centrally concentrated cluster with a strong gravitational core can withstand a tidal shock much better than a loose, diffuse one. It's the difference between a tightly packed sandcastle and a pile of loose sand when a wave hits. One might lose a few grains while the other is washed away entirely. Similarly, a cluster on a circular orbit that keeps it safely in the galactic halo may never experience a significant shock, allowing it to age gracefully through slow evaporation. In contrast, a cluster on a highly eccentric, plunging orbit that regularly dives through the galactic disk is living on borrowed time. The specific angle at which it crosses the disk also matters. A direct, perpendicular punch is far more damaging than a shallow, grazing encounter. By studying the shapes, densities, and orbits of different globular clusters, astronomers can effectively read their pasts and predict their futures, classifying them as either long-term survivors or cosmic dead men walking, destined to be shredded by the relentless gravitational machinery of the Milky Way. This division leads us to a discovery that serves as a powerful echo of our own galaxy's most violent growing pains, a fundamental split in the very identity of the globular cluster population itself. It's a concept known as the bimodality in metallicity, and it reveals that the story of these clusters is not a single, continuous narrative, but rather a tale of two distinct eras, two separate bursts of cosmic construction that bookend a period of dramatic change. For a long time, when astronomers measured the metal content of globular clusters orbiting large galaxies like the Milky Way and Andromeda, they expected to find a smooth, continuous distribution. They anticipated a gradient, with some clusters being extremely metal poor, others moderately so, and a few with slightly higher metal content, reflecting a gradual enrichment of the galaxy's gas over time. But the data revealed something far more striking. The clusters didn't form a smooth continuum, they clustered into two distinct, separate camps. It's as if you sorted a large group of people by height and found that everyone was either very tall or very short, with almost no one of average height in between. This is a bimodal distribution, and in the case of globular clusters, the two groups are defined by their iron content, which astronomers use as a shorthand for overall metallicity. On one side, we have the true ancients. These are the metal-poor clusters with iron abundances less than about 1% of the Sun's level. They are the pristine relics composed almost entirely of hydrogen and helium, the raw materials of the Big Bang. On the other side, we find the metal-rich clusters. Now, rich is a relative term here. These clusters are still vastly more metal-poor than the Sun, but they possess iron abundances that are typically 5 to 10 times higher than their metal-poor cousins. This clear division is not a random statistical fluke. It is a profound clue, a fossil record pointing directly to two major, separate epochs of globular cluster formation in the galaxy's history. The metal-poor population represents the first great wave of construction. These clusters formed when the universe was in its wild youth, perhaps only 1 or 2 billion years old. At this time, the cosmos was a much smaller, denser place, and the gas that filled it was largely unpolluted by the products of stellar nucleosynthesis. The first galaxies were assembling, and within them, the conditions were perfect for the rapid, monolithic collapse of giant gas clouds into these incredibly dense, massive star clusters. This first wave created the foundational population of globulars, the true cosmic pioneers that have witnessed nearly the entire history of the universe. But then, something dramatic happened. The formation of new globular clusters seems to have largely stopped for a significant period. The universe expanded. The pristine gas was used up or blown out of galaxies by the fierce feedback from those first supernova and quasars, and the frantic pace of cluster formation slowed to a crawl. The second wave, which created the metal-rich population, was triggered by a specific and violent event: major galaxy mergers. Imagine the early Milky Way, not as the majestic spiral we see today, but as a smaller, gas-rich protogalaxy. Another galaxy of similar size, also having already formed its own population of metal-poor clusters, is on a collision course. When these two systems finally smash together, it is not a gentle process. It is a cosmic cataclysm of unbelievable proportions. The orderly motions of stars and gas are thrown into chaos, and immense shockwaves compress the interstellar gas to incredible densities. This merger event provides the precise conditions, the intense pressure, and the plentiful, now chemically enriched, gas necessary to trigger a new, furious burst of globular cluster formation. The gas from which these new clusters form is no longer pristine. It has been seeded with heavier elements forged in the lives and deaths of the stars from both colliding galaxies. Therefore, this second generation of clusters is born with a higher metallicity from the very beginning. They are the children of violence, their slightly richer chemical composition, a direct inheritance from the galactic wreckage from which they were born. This bimodal split is not just a story about the clusters themselves, it's a story about the galaxy that hosts them. The metal-poor clusters are like the original settlers of a continent, having arrived first and staked their claim in the vast, empty halo. They orbit the galactic center on all sorts of random, eccentric paths, a testament to their ancient and chaotic origins. The metal-rich clusters, in contrast, are the second wave. They formed later within the tumultuous, gas-rich disks of the merging galaxies. As the merger settled down and the new, larger galaxy formed a distinctive bulge, these metal-rich clusters were left orbiting closer to the galactic center, their motions more aligned with the overall rotation of the galaxy's bulge and thick disk. This spatial and kinematic difference is the final piece of evidence that locks in the two-epoch theory. We don't just see two different chemical families, we see them occupying two different parts of the galaxy and moving in two different ways, a clear signature of their separate birthplaces and times. This grand dichotomy forces us to see globular clusters not just as individual wonders, but as tracers of the most monumental events in a galaxy's life. By simply counting the ratio of metal-poor to metal-rich clusters in a galaxy, astronomers can effectively gauge its past violence, reading the history of its growth and assimilation written in the ancient light of these stellar fossils. But perhaps the most detailed chemical evidence for this complex history is written in the subtle, star-to-star variations of the lightest elements beyond hydrogen and helium. When astronomers take the spectrum of a star, they are reading its chemical identity card, and for stars within the same globular cluster, these identity cards reveal a strange and specific pattern of fraud. They show wild variations in the abundances of carbon, nitrogen, and oxygen elements that astronomers collectively call the light elements. From one star to the next, even when those stars are neighbors in the same cluster and have the exact same amount of heavier elements like iron. This is a profound chemical clue. The amount of iron in a star is like its family name, telling you which large galactic generation it belongs to. but the amounts of carbon, nitrogen, and oxygen are like personal signatures, revealing the specific and often dramatic life stories of its direct ancestors. These variations cannot possibly be explained by the Big Bang, which produced only trace amounts of these elements, nor can they be explained by the general, slow enrichment of the galaxy over time, because the iron content, which tracks that general enrichment, remains constant. The only possible explanation is a local, internal source of pollution. The cluster must have contaminated itself, and the specific pattern of this pollution points directly to the nuclear furnaces burning inside its own most massive stars. To understand this, we need to step into the heart of a first-generation star. These pioneers were not like our Sun. They were massive, hot, and fast-living. Deep in their cores, where temperatures soar to tens of millions of degrees, a specific chain of nuclear reactions known as the C0 cycle was the dominant engine for converting hydrogen into helium. The C0 cycle, which stands for carbon, nitrogen, oxygen, uses these heavier elements as nuclear catalysts. A carbon-12 nucleus captures protons, turning first into nitrogen-13, which decays to stable nitrogen-14. This nitrogen-14 can then capture another proton to become oxygen-15, which decays back to carbon-12, completing the cycle. The key point is that in a perfect closed system, the catalysts are recycled and their total amounts don't change. But a massive star's interior is not a perfect closed system. It's a layered, turbulent place where different processes occur in different shells. In the hot hydrogen-burning shell where the C0 cycle runs, the reaction chain doesn't reach perfect equilibrium. Nitrogen-14, being a particularly stable isotope, tends to accumulate. It acts like a bottleneck in the cycle, so the gas that is processed through the C0 cycle emerges enriched in nitrogen. Meanwhile, the original carbon and oxygen that were used to start the cycle are depleted as they get tied up in the process of creating more nitrogen. But the story doesn't end there. At even higher temperatures, in a shell surrounding the core where helium is burning, another set of nuclear reactions takes over. Here, helium nuclei are fused onto existing heavier elements. When a carbon nucleus captures a helium nucleus, it becomes oxygen. But under the specific conditions of high temperature and density found in these massive stars, other reactions can occur. For instance, neon atoms can capture protons to become sodium, and magnesium can capture protons to become aluminum. This high-temperature hydrogen and helium burning creates a very specific chemical output, a gas that is enriched in helium, nitrogen, sodium, and aluminum, while being simultaneously depleted in carbon and oxygen. This is the crucial nucleosynthesis fingerprint. It's a bizarre, imbalanced recipe that could only be cooked up in the intense, layered interiors of massive stars. The next step in the mystery is getting this processed material out of the star and into the cluster's shared reservoir of gas. This is where stellar death and stellar winds come into play. The most massive of these first-generation stars ended their lives in core collapse supernova, which would have blasted their newly forged heavy elements far and wide. However, for the specific pattern of light element variation, supernova may not be the primary delivery mechanism. For the intermediate mass stars, those several times more massive than our Sun, the primary way they shed their enriched layers is through powerful, steady stellar winds during their red giant phase. As these stars evolve, they blow off their outer atmospheres into space. These winds are essentially the star gently exhaling its nuclearly processed interior, carrying this chemically peculiar gas, now rich in nitrogen and sodium, and poor in carbon and oxygen, and releasing it into the interstellar environment of the entire globular cluster. This ejected gas, bearing the unmistakable fingerprint of high-temperature proton capture, then mixes with whatever pristine hydrogen and helium still remains from the cluster's initial formation. This creates a new, second reservoir of raw material that is chemically distinct from the first. When gravity triggers a second wave of star formation, This new generation of stars condenses from this already polluted gas cloud. They are therefore born with this strange chemical signature already imprinted in their DNA. They don't have to create these elements themselves, they inherit them. This is why we see stars that are chronologically ancient but chemically look like they've been contaminated. One star from the first generation will show a pristine pattern with higher carbon and oxygen. Its neighbor from the second generation will show the polluted pattern, enhanced nitrogen and sodium, and depleted carbon and oxygen. The variations are not random, they follow a clear, anti-correlated pattern. Where nitrogen is high, carbon is low. Where sodium is high, oxygen is low. This is the definitive forensic evidence of internal pollution, a chemical cycle of life and death that operated entirely within the confines of the cluster itself, transforming it from a simple collection of stars into a complex stellar ecosystem with its own distinct chemical evolution. Now, as we zoom out from the intricate lives of individual clusters to their broader galactic context, we stumble upon a profound cosmological puzzle that threatens to rewrite the story of how the smallest galaxies are born. This is the problem of the missing globular clusters, and it strikes at a fundamental prediction of our most successful model of the universe. The logic seemed unassailable. We know that globular clusters are incredibly ancient, forming at the same time as their host galaxies. We also know from overwhelming evidence that galaxies are built within vast, invisible cocoons of dark matter. These dark matter halos provide the gravitational scaffolding that pulls in gas and guides the formation of stars. The more massive the dark matter halo, the larger and more luminous the galaxy it can host, and crucially, the more massive globular cluster system it should be able to form and hold onto. For large galaxies like our Milky Way, this relationship holds beautifully. We have a massive dark matter halo, and we host a rich system of over 150 globular clusters. The theory seemed to scale down perfectly. It predicted that even the tiniest dwarf galaxies, the faintest smudges of light in the cosmos, should each possess their own small retinue of these ancient star clusters, perhaps 2, 3, or even 5 of them, orbiting as miniature cosmic consorts. But when astronomers went looking, they found a glaring void. In countless dwarf galaxies, particularly the small, diffuse spheroidal dwarfs that orbit the Milky Way and Andromeda, the globular clusters are simply not there. The galaxies exist, their stars are present, but the expected ancient clusters are missing. It's like arriving at a grand, historic city and finding the main cathedral, the central castle, and the oldest monuments have all vanished without a trace, leaving only the residential neighborhoods behind. This isn't just a minor statistical undershoot, it's a systematic failure of prediction that leaves cosmologists scratching their heads. The most stark examples are galaxies like the Draco dwarf and the Ursa Minor dwarf. Based on their stellar mass and their inferred dark matter halos, they should each host a handful of globular clusters, yet they have none, zero. The silence of their empty halos is deafening, posing a direct challenge to our understanding of how structure forms in the universe. So, where did all the clusters go? Scientists are investigating several compelling and sometimes dramatic possibilities. The leading theory points an accusatory finger at our own galaxy and its larger siblings. This is a story of cosmic cannibalism on a grand scale. In the hierarchical model of galaxy formation, large galaxies like the Milky Way grow by consuming smaller ones. As a dwarf galaxy swings close to the giant, the immense tidal forces begin to rip it apart. This process is brutally selective. The most vulnerable parts of the dwarf galaxy are the loosely bound stars in its outer halo and, critically, its globular clusters. These clusters orbiting in the galaxy's periphery are the first to be stripped away. They are gravitationally plucked from their original host and adopted by the larger galaxy, becoming part of its own extended cluster family. In this scenario, the missing clusters aren't missing at all. we're simply looking in the wrong place. The globular clusters we see orbiting the Milky Way today are not all native to it. A significant fraction of them are the stolen property of devoured dwarf galaxies. The Fornax dwarf spheroidal galaxy provides a fascinating counterexample that supports this idea. It is one of the only dwarf galaxies near the Milky Way that still holds onto its own cluster system, 5 of them. Crucially, Fornax is on a much wider, more distant orbit than galaxies like Draco and Ursa Minor, placing it far from the destructive tidal grip of the Milky Way. It seems that to keep your globular clusters, you need to keep your distance from galactic giants. However, tidal stripping might not be the whole story. A more radical possibility is that the problem lies not with the clusters being lost, but with them never having formed in the first place. This theory challenges the initial conditions of the early universe. Perhaps the very first generation of star formation worked differently in these small dark matter halos. In the largest halos, the immense pressure and density could have easily triggered the monolithic collapse that forms a massive globular cluster. But in a smaller halo, the gas may have been more susceptible to feedback. The first massive stars to form would have unleashed torrents of ultraviolet radiation and powerful supernova shocks. In a large halo with its deep gravitational well, this feedback could be contained, perhaps even triggering further cluster formation. But in a shallow dwarf galaxy potential, this same energy might have been utterly devastating. It could have blown all the remaining gas clear out of the halo in a single, swift blow, permanently shutting down star formation and leaving no chance for a second wave that could have built a globular cluster. The dwarf galaxy would be stillborn, left with a small, faint population of stars but lacking the dense, glittering centerpieces that should have been its crowning glory. The absence of clusters in this view is a permanent scar from a traumatic birth, a testament to the violent and unforgiving nature of the early cosmos. A third and deeply intriguing possibility involves the dark matter halos themselves. Our predictions for how many clusters a dwarf should have are based on the assumption that their dark matter halos are dense and centrally concentrated. But what if they aren't? Recent observations and simulations suggest that some dwarf galaxies might inhabit halos that are much more fluffy and extended than we thought. A less concentrated halo would have a weaker gravitational pull at its center, making it much harder to trigger the rapid, efficient collapse of gas required to form a massive, bound cluster. It might only be capable of forming loose, unbound stellar associations that quickly dissolve, leaving no permanent cluster behind. This idea connects to the core cusp problem in cosmology, where the observed distribution of dark matter in dwarf galaxies seems less peaked than simulations predict. The missing globular clusters could be another manifestation of this deeper mystery, hinting that the nature of dark matter itself, or its interaction with normal matter, might be more complex than our standard models allow. Ultimately, the silent emptiness surrounding these dwarf galaxies forces us to reconsider the entire ecosystem of galaxy formation. It reveals that the survival of these ancient stellar cities is a fragile thing, dependent not just on the conditions of their birth, but on a lifetime of avoiding the gravitational predators that lurk in the cosmic deep. Moving from the steady rhythms of Lyrae stars, we encounter a class of variable stars that operate on a timescale more befitting of geological epochs than stellar pulsations. These are the ultra-long period variables, and their discovery within globular clusters has introduced a slow, mysterious heartbeat into these ancient systems. Imagine a star that takes not hours or days, but entire years, even decades, to complete a single cycle of brightening and dimming. While most variable stars are like metronomes ticking with reliable regularity, these stars are like grand, slow-moving pendulums, their cycles so protracted that a single human career of observation might only capture a handful of their pulses. This incredible slowness is the core of the mystery. What kind of stellar process could possibly drive such a leisurely, drawn-out oscillation? The very existence of these stars challenges our models of stellar instability, forcing us to consider that the final chapters of stellar life might involve changes so gradual we have only just begun to notice them. The nature of these stars is a subject of intense debate, precisely because their long periods don't fit neatly into the established categories of variable stars. One leading hypothesis suggests we are witnessing the final, deep breaths of stars at the very end of the asymptotic giant branch phase. This is the last hurrah for a sun-like star before it sheds its outer layers to become a white dwarf. At this stage, the star is a bloated, unstable behemoth, its interior a complex layering of fusion shells. The ultra-long period could be driven by a slow, resonant thermal pulse within the star. In this model, the star's helium-burning shell undergoes a cycle of ignition and quenching. When it ignites, it produces a burst of energy that causes the star to expand and cool slightly, which in turn shuts off the shell. The star then slowly contracts until the conditions are right for the shell to ignite again, starting the cycle over. This process, playing out in the vast, distended envelope of a supergiant star, could easily take several years to complete, producing the observed slow, rhythmic change in brightness. It would be a sign of a star in its final, deeply unstable throes, a slow-motion prelude to its transformation into a planetary nebula. However, there is another, more exotic possibility that connects these stars directly to the unique environment of a globular cluster. This theory posits that the ultra-long period variables are not pulsating due to an internal instability, but are instead engaged in a slow, cosmic dance with a binary companion. Imagine a system where a bright, evolved giant star is locked in a wide, leisurely orbit with a smaller, dimmer partner. If our line of sight is nearly edge onto this orbit, the giant star will be periodically eclipsed by its companion. Given the immense size of the evolved giant and the correspondingly large orbital separation required to accommodate it, a single orbit could indeed take many years. The dimming we observe would then be a simple eclipse, a celestial occultation on a grand timescale. The challenge with this model is that the dimming events in many of these stars are not perfectly sharp and symmetric like a typical eclipse. They can be more gradual and irregular, suggesting that more than just a simple geometric blocking is at work. Perhaps the companion is close enough to distort the giant star through tidal forces, causing its shape to change slowly over the orbit and thereby altering its brightness in a complex way. Or maybe the companion is pulling material from the giant, creating a circumstellar disk of dust that periodically obscures our view, creating a slow, dusty dimming rather than a clean eclipse. The dense environment of a globular cluster makes this binary explanation particularly compelling. We know that binary star systems are common in clusters, and dynamical interactions can create a wide variety of orbital configurations. A binary system with an ultra-long period would be highly vulnerable to gravitational perturbations from passing stars. A close encounter could easily disrupt such a wide, weakly bound orbit, which means that any ultra-long period binary that survives must be either very lucky or must have formed in a particularly quiet part of the cluster. Alternatively, the binary might have been hardened through interactions, and the long period we see is actually a transient phase in a much longer dynamical evolution. The very survival of these systems, if they are indeed binaries, tells us something about the dynamical history of their host cluster. A cluster with many such systems likely has a comma core where wide binaries can persist for long periods. Distinguishing between the pulsating star and binary star hypotheses is a monumental task that requires patience spanning decades. Astronomers are building up light curves, graphs of brightness over time, that now cover many years, slowly piecing together the complete story of a single cycle. They are looking for telltale signatures in the light. For instance, if the star is a pulsator, its color should change in a specific way as it expands and cools, then contracts and heats up. If it is a binary system, the spectrum of its light might reveal a Doppler shift as it moves around a common center of mass, or there might be subtle chemical signatures of mass transfer between the two stars. Each new data point, each new year of observation, brings us closer to understanding the true nature of these slow celestial giants. They remind us that the universe operates on timescales far beyond our own, and that some of its most profound mysteries reveal themselves not in a flash, but in the patient, relentless passage of time. Gravity, the architect of the cosmos, often works in ways that feel counterintuitive, and nowhere is this more evident than in the slow, cosmic waltz that draws the most massive globular clusters toward their eventual demise. This process is known as dynamical friction, and it acts as a kind of gravitational brake, a relentless drag that saps the energy of massive objects as they move through a sea of lighter particles. Imagine a giant, heavy pebble being swung through a dense cloud of fine sand. The pebble will constantly be bumping into sand grains, transferring a tiny bit of its momentum to each one with every microscopic collision. While any single grain barely affects the pebble's path, the collective effect of trillions of these tiny interactions creates a persistent, cumulative drag, steadily slowing the pebble down. In the vastness of a galaxy, the roles are played on an unimaginable scale. The heavy pebble is a massive globular cluster weighing in at perhaps 1 million solar masses. The cloud of sand is the galaxy's halo, composed of billions of individual stars as well as vast amounts of dark matter. As the cluster speeds along its orbit, its immense gravitational pull doesn't just attract nearby stars, it actually creates a slight, dense wake of stars behind it, like the gravitational equivalent of the bow wave behind a speedboat. This wake, being denser than the surrounding stellar field, exerts a gravitational tug back on the cluster itself. This isn't a push from the front, but a pull from behind, and it acts directly against the cluster's direction of motion. The result is a continuous, gentle braking force, dynamical friction, that relentlessly robs the cluster of its orbital energy and angular momentum. The consequences of this energy loss are both predictable and profound. Just as a satellite in low Earth orbit, if it slows down, will begin to spiral inward toward the planet, a globular cluster experiencing dynamical friction will see its orbit slowly decay. It doesn't plunge directly toward the center. Instead, its path becomes a tightening spiral, a slow-motion descent into the galactic core that can take billions of years to complete. The rate of this decay is exquisitely sensitive to the cluster's mass. A puny, low-mass cluster will barely feel this effect, its orbit remaining stable for timescales longer than the current age of the universe. But for the true heavyweights, the most massive and brilliant clusters, dynamical friction is a death sentence. Their immense gravity creates a stronger wake and a more powerful braking force, accelerating their inward journey. This creates a fascinating natural selection process within the galactic halo. Over cosmic time, the galaxy acts as a gravitational filter, systematically stripping away its most magnificent stellar cities from the outer regions and delivering them to the bustling downtown of the galactic center, leaving behind a halo populated predominantly by smaller, lighter clusters. So, what is the ultimate fate of a cluster on this inexorable inward spiral? The journey ends in destruction, but a destruction that feeds the growth of the galaxy itself. As the cluster gets closer and closer to the galactic center, the tidal forces it experiences become unimaginably strong. The difference in the galaxy's gravitational pull on the near side of the cluster versus its far side stretches and distorts the cluster violently. First, its outermost stars are stripped away, forming long, dissolving streams that merge with the general stellar population of the galaxy's bulge. Then, as it penetrates deeper, the tidal forces become so overwhelming that the entire cluster is ripped apart. Its stars are scattered, their unique, shared motion dissolved into the random orbits of the billions of other stars that make up the central bulge of the galaxy. The cluster as a distinct entity ceases to exist. It has been shredded, its identity erased by the very galaxy that gave it birth. This process of destruction is not a mere cosmic cleanup operation. It is a fundamental mechanism of galaxy growth and evolution. The relentless delivery of massive, metal-rich globular clusters to the galactic center provides a steady supply of stars to build up and puff out the central bulge. Think of it as a form of galactic cannibalism, where the galaxy consumes its own largest satellite systems to fuel its own central structure. This could explain why the central bulges of some galaxies are so rich in old stars. They are the accumulated wreckage of countless globular clusters that spiraled in and were torn apart over billions of years. Furthermore, this process may play a critical role in feeding the supermassive black hole that lurks at the very heart of most galaxies. While a whole cluster is unlikely to be swallowed intact, the process of tidal disruption would liberate a torrent of individual stars. Some of these stars would be flung out on new, chaotic orbits, while others could be sent on trajectories that bring them dangerously close to the black hole, where they would be tidally shredded themselves, providing a feast of gas that could temporarily light up the black hole as an active galactic nucleus. The inward spiral of a single, massive globular cluster is therefore a small but significant chapter in the life story of a galaxy, a demonstration of how the universe recycles its grandest structures, using their dissolution to build something even larger and more enduring. Now we venture into the domain of the most fleeting and energetic signals in the cosmos, a mystery that has tantalized astronomers for years and may have a surprising home in the ancient hearts of globular clusters. Fast radio bursts are exactly what their name implies, bursts of radio waves that last for just milliseconds, but in that fleeting instant, they can release more energy than our sun puts out over several days. These signals appear as sudden, brilliant spikes on a radio telescope's data readout, often from random directions in the sky, and then vanish without a trace as quickly as they came. For a long time, their origins were completely unknown, sparking theories that ranged from the collisions of exotic stars to, yes, even the possibility of advanced alien civilizations. But as we've detected more of them, a pattern has begun to emerge, revealing that at least some of these cosmic firecrackers are repeating, and a handful of these repeaters have been traced back to environments that look remarkably familiar, the dense, ancient stellar cities of globular clusters. This connection is still speculative, but it's a compelling lead in one of astronomy's greatest detective stories, and it points directly to the incredible population of neutron stars these clusters hoard. To understand why a globular cluster is such a promising factory for these bursts, we need to look at the likely culprits, magnetars. A magnetar is a specific type of neutron star, the ultra-dense remnant of a supernova, but it's a neutron star pushed to an even more extreme limit. Imagine the magnetic field of a typical neutron star, which is already trillions of times stronger than Earth's. Now amplify that by a factor of 1,000. That's a magnetar. Its magnetic field is so unimaginably intense that it can literally twist the star's solid, iron-like crust. This creates immense stress, and when the crust finally snaps in a starquake, it releases a cataclysmic amount of energy in a fraction of a second, potentially blasting out a focused beam of radio waves that we detect as a fast radio burst. It's the cosmic equivalent of the snap of a gigantic magnetic rubber band. Now consider the social dynamics inside a globular cluster. We already know these places are neutron star factories with hundreds or even thousands of these dense remnants, including the rapidly spinning millisecond pulsars. The same dynamical processes that create those pulsars, collisions, binary interactions, and stellar mergers are also perfect mechanisms for creating magnetars. A close encounter between two neutron stars could amplify a magnetic field to magnetar strength, or the merger of a neutron star with another star could create the precise conditions needed for this magnetic monster to be born. The dense core of a globular cluster provides the perfect crucible for forging these extreme objects, making it a natural place to go looking for the sources of these mysterious radio flashes. The evidence, while still circumstantial, is growing stronger. The first major breakthrough came when a repeating fast radio burst was pinpointed to a location within a faint, distant galaxy. While not a globular cluster itself, the environment shared key characteristics. More recently, a repeating burst was localized to a region within a nearby galaxy that is remarkably similar to a globular cluster, a dense old stellar population. This is the tantalizing clue. It suggests that the unique conditions found in these clusters, specifically their high density of neutron stars and the frequent gravitational interactions that can rejuvenate them, might be the key ingredient for producing at least some of these signals. In the chaotic core of a cluster, a magnetar might not lead a quiet life. It could be periodically jostled by passing stars or have its orbit perturbed in a binary system, triggering repeated starquakes and sending out multiple fast radio bursts over time. This would explain the repeaters and why they seem to be associated with these long-lived, stable stellar environments. Of course, the magnetar starquake model is not the only game in town. The sheer density of binary systems in a globular cluster opens up other fascinating possibilities. One leading alternative theory involves a special kind of binary pair, a neutron star and a companion star with a very eccentric or oval-shaped orbit. As they swing close to each other on their elongated path, the neutron star's immense gravity could violently strip material from its partner. This sudden infall of matter onto the neutron star's magnetic poles could create a shockwave so powerful it generates a brilliant, one-off burst of radio emission. Another, even more dramatic scenario involves the final in-spiral and collision of two neutron stars. As these ultra-dense objects spiral closer together, they could emit a last, powerful radio scream just before they merge and form a black hole, a cataclysmic event that would also be a primary source of gravitational waves and the heavy elements like gold and platinum. The fact that globular clusters are predicted to be hotbeds for such neutron star mergers makes them a double contender for producing these enigmatic signals. This speculative link does more than just offer a potential solution to one cosmic mystery. It fundamentally changes how we view these ancient star clusters. We are used to seeing them as serene, static collections of old stars, but the fast radio burst connection reveals them as places of ongoing, violent, and millisecond-scale drama. They are not just fossil beds, they are active arenas where the most extreme physics in the universe can play out, broadcasting their existence through flashes of radio light that travel across cosmic distances. This transforms globular clusters into natural laboratories for studying some of the most energetic and poorly understood phenomena in astrophysics. By continuing to monitor these ancient stellar metropolises with radio telescopes, we are not just looking into the distant past, we are watching for the brief, brilliant flashes that illuminate their dynamic, hidden present, connecting the oldest structures in the galaxy to one of the most modern and exciting puzzles in all of astronomy. But perhaps the single most powerful tool for unraveling the life story of a globular cluster is the one that appears at first glance to be the simplest, the Hertzsprung-Russell diagram, or as it's more specifically known for clusters, the color magnitude diagram. For over a century, this graph has been the foundational map of stellar astronomy, plotting a star's color against its intrinsic brightness. For a simple, single-aged population like a globular cluster was once thought to be, this diagram should look clean and predictable. A well-defined main sequence band where stars spend most of their lives, a distinct turn-off point marking the cluster's age, and an orderly giant branch where stars go after exhausting their core hydrogen. It's a stellar family portrait, with every star posing according to its mass and evolutionary stage. But when we began to plot these diagrams with the incredible precision of modern telescopes like Hubble, the simple, elegant picture shattered. We didn't find a single clean track. We found splits, gaps, twists, and multiple sequences, as if the stellar family had several distinct lineages all vying for space on the same chart. These are not mere cosmetic flaws. They are profound puzzles written in starlight, each anomaly a direct clue to a deeper complexity in the cluster's history and the very physics of stars. One of the most startling revelations was the splitting of the main sequence itself. In several massive clusters, most famously Omega Centauri and NGC 2808, astronomers found that the main sequence, that clean, diagonal line of hydrogen-burning stars, was not a single line at all, but two or more distinct parallel strands. Imagine a two-lane highway suddenly splitting into separate, parallel roads, each carrying a different type of vehicle. This main sequence split is a direct and undeniable signpost of multiple stellar generations with different chemical recipes. The stars on the bluer, hotter main sequence strand are the first generation, born from pristine gas. The stars on the redder, slightly fainter strand are a later generation, born from gas that was polluted with extra helium from the first wave of massive stars. Why does extra helium make a star redder and fainter? It all comes down to the star's internal engine. A star with more helium in its initial mix is more opaque to its own radiation. This means energy has a harder time escaping from the core, so the star has to puff up slightly to achieve equilibrium, making it larger, cooler at the surface, and therefore redder and fainter than a star of the same mass but with less helium. This seemingly minor shift on a graph is therefore a monumental discovery. It's the clearest possible evidence that the cluster hosted not one, but at least two distinct epochs of star formation from chemically different raw materials. Then there is the mystery of the red giant branch, a phase that should be a relatively straightforward ascent to grandeur. Instead, in many clusters, we see this branch split into two distinct paths. As stars leave the main sequence and begin their expansion into red giants, they don't all follow the same route. One group climbs a red giant branch that is slightly bluer, while another group diverges onto a parallel branch that is noticeably redder. This bifurcation is another chemical fingerprint, and it points directly to differences in the abundance of elements like carbon, nitrogen, and oxygen. The stars on the redder branch are typically those from the later, polluted generations. They have a higher abundance of nitrogen, which, in the outer layers of a star, acts as a powerful opacifier. Just as a helium-rich star is more opaque, a nitrogen-rich atmosphere also traps heat more effectively. This forces the star to swell to a larger size and cooler temperature to release its energy, pushing it onto the redder branch. The split red giant branch is therefore a cosmic sorting mechanism, using the star's surface chemistry to separate the primordial population from the polluted one, right before our eyes on a simple graph. But the anomalies don't stop there. Even the horizontal branch, that final stable resting place for helium-burning stars, is riddled with strange gaps and sequences. In some clusters, there are conspicuous empty regions along the horizontal branch zones where no stars are found. These are not random voids, they are instability strips where stellar physics becomes inherently unstable. The most famous of these is the Lyrae gap, where stars pulsate with a regular rhythm. But other gaps exist, and their locations are exquisitely sensitive to the star's internal structure, particularly the mass of its remaining hydrogen envelope. A gap in one part of the horizontal branch tells us that stars with a very specific envelope mass are unstable and quickly evolve through that region, leaving it empty. In other clusters, the horizontal branch isn't a line at all, but a broad, fuzzy band or even a second, nearly vertical sequence. This extreme spread in temperature at the same evolutionary stage is the direct result of the wide range of mass loss experienced by the stars when they were red giants. A star that lost a lot of mass will have a very thin hydrogen envelope and become a hot blue horizontal branch star. a star that held onto most of its envelope will be a cooler, redder horizontal branch star. The incredible diversity of the horizontal branch in a single cluster is a stark record of the diversity of individual stellar life stories, a testament to how factors like rotation, binarity, and dynamical encounters can alter a star's final appearance. Perhaps the most dramatic puzzle of all is the phenomenon of the extended main sequence turnoff, which we touched on earlier. Instead of a sharp corner where stars leave the main sequence, we see a broad, smeared-out region that can even appear to be split. This blurring of the cosmic clock was initially interpreted as a simple age spread, evidence that star formation in the cluster persisted for a few 100 million years. But a compelling alternative explanation has gained significant traction, one that involves the spin of the stars themselves. In the dense core of a globular cluster, stars can be spun up to incredible velocities through gravitational encounters. A rapidly rotating star is fundamentally different inside. The centrifugal force changes its shape and, crucially, induces internal mixing. This churning of stellar material brings fresh hydrogen fuel down into the core and carries helium ash out, effectively giving the star a larger fuel tank and prolonging its life on the main sequence. Therefore, a rapidly rotating star will have a delayed evolution, turning off the main sequence at a fainter, redder point than a non-rotating star of the same mass and age. When we observe the cluster, we see both the normal stars and the spun-up stars, and their combined turn-off points create a broadened, extended region. In some cases, if there are two distinct populations with very different rotation rates, it can even create a clear split in the turn-off. This means the color magnitude diagram is not just a record of age and chemistry, but also a fossil record of the dynamical interactions that have spun stars up over billions of years. Each of these diagrammatic puzzles, the split main sequences, the bifurcated red giant branches, the gappy horizontal branches, and the smeared turnoffs converges on a single, transformative conclusion. A globular cluster is not a simple stellar population. It is a complex stellar ecosystem. The Hertzsprung-Russell diagram, once a tool for classifying simple stars, has become a sophisticated diagnostic instrument. By carefully mapping these anomalies, astronomers can now reconstruct a cluster's entire history, the number of its stellar generations, the specific chemical elements that polluted its gas, the range of mass loss its stars experienced, and even the frequency of dynamical encounters in its core. What looks like a scatter plot of points is, in reality, a detailed autobiography of the cluster, written in the language of color and magnitude, waiting for us to learn how to read it. This brings us to a technique that turns the entire galactic halo into a crime scene, and the globular clusters into the prime witnesses. We're talking about galactic archaeology, a field of science that doesn't just look at what our galaxy is now, but actively digs into its past to uncover the violent, dramatic events that built it. And the key fossils in this investigation are the globular clusters. Think of them not as passive ornaments, but as celestial genealogical records. Each cluster carries two vital pieces of evidence: its chemical composition, which is like its DNA, and its orbital motion, which is like its family name and address. By analyzing these two things for all the clusters in the Milky Way's halo, we can effectively rewind the cosmic clock and piece together a story of galactic cannibalism and growth that occurred over billions of years. The chemical composition is the first clue. As we've discovered, clusters from different formation eras have distinct metallicities. The very metal-poor clusters are the true ancients, the indigenous population of the Milky Way, forming from the pristine gas of the early universe. The slightly more metal-rich clusters represent later arrivals, formed in other, smaller galaxies that were independent entities long before they were consumed. When the Milky Way devours a dwarf galaxy, it doesn't just swallow its stars, it acquires all of that galaxy's globular clusters as well. These captured clusters retain their own unique chemical signature, a fingerprint that is often distinctly different from the native Milky Way population. So when we find a group of clusters orbiting our galaxy that all share a very similar and peculiar chemical pattern, one that matches the stars in a known dwarf galaxy, it's like finding a group of people with the same rare surname in a new city. It strongly suggests they all immigrated from the same place. But the chemical evidence alone isn't enough. We need to confirm their origin by looking at their motions. This is where the incredible precision of the Gaia Space Observatory has revolutionized the field. Gaia has given us a dynamic map of the sky, showing not just where the clusters are, but precisely how they are moving, and this is where the story gets truly spectacular. Astronomers have discovered that many of the Milky Way's globular clusters do not move on random, independent orbits. Instead, they travel in vast, coherent groups. These are now known as satellite galaxy streams, and they are the ghostly remains of devoured dwarf galaxies. The most famous of these is the Gaia sausage, or Gaia Enceladus, a colossal structure that is not made of stars you can see, but is defined by the shared, highly eccentric orbits of dozens of globular clusters and millions of individual stars. The story this tells is one of the most significant events in our galaxy's history. Billions of years ago, a large dwarf galaxy, now named Gaia Enceladus, collided with the nascent Milky Way in a nearly head-on collision. The impact was catastrophic for the smaller galaxy, completely tearing it apart. Its stars and its globular clusters were not destroyed, but were strewn across the Milky Way's halo. Over time, gravity has shepherded these orphan stars and clusters into this vast, sausage-shaped structure in motion space. When we identify a globular cluster that is part of this stream, we know with near certainty that it was not born here. It is a refugee, a captured trophy from one of the Milky Way's most massive ancient mergers. This process allows us to do more than just identify past mergers. It lets us reconstruct the properties of the long-dead galaxy itself. By studying all the clusters that belong to a single stream, like the Helmi stream or the Sequoia event, we can estimate the original mass of the dwarf galaxy they came from. We can determine its chemical evolution by comparing the metallicities of its captured clusters. We can even piece together its orbital history right up to the moment of its dissolution. Each stream is like a separate chapter in a history book, detailing the assimilation of a different galactic building block. The sheer number of these streams tells us that the peaceful-looking Milky Way halo is actually a galactic graveyard, filled with the remnants of dozens of smaller galaxies that it has consumed over the eons. The globular clusters are the enduring headstones in this graveyard, each one marking the final resting place of a galaxy that no longer exists. This archaeological record is constantly being refined. As Gaia and other surveys provide ever more precise data, astronomers are identifying finer and finer substructures, uncovering smaller merger events, and even the possible traces of the very first protogalaxies that coalesced to form the Milky Way's core. This work transforms our understanding of galaxy formation from a theoretical model into a detailed, observational history. We are no longer just assuming that galaxies grow by merging. We are holding the evidence in our hands, written in the light and motion of these ancient star clusters. They are the ultimate time capsules, preserving not only the conditions of the early universe, but also the specific, violent events that sculpted our cosmic home into the majestic spiral we see today. And here we encounter a cosmic accounting error so fundamental it forces us to question the very nature of what makes up these clusters. This is the puzzle of the mass-to-light ratio anomaly, and it begins with two very different ways of weighing a globular cluster. The first method is beautifully straightforward. We simply count the light by measuring the total brightness of a cluster and knowing the average mass of the types of stars that contribute to that light. Astronomers can calculate a luminous mass. It's a bit like estimating the weight of a distant forest by its overall greenness, assuming a certain mass for each tree. This gives us a baseline, the mass we can directly see shining in the form of stars. The second method is more clever, and it relies on the laws of gravity. By meticulously tracking the speeds of individual stars as they orbit within the cluster, specifically how their velocities change from the crowded core to the diffuse outer halo, scientists can work backwards to calculate the total gravitational force required to hold them in those orbits. This dynamical mass is the true weight of the entire system, the sum of everything that exerts a gravitational pull. In a perfectly simple universe, these two numbers should match. The mass inferred from the light should perfectly account for the mass inferred from the stellar motions, but in many globular clusters they don't. The dynamical mass, the one measured by gravity, is often significantly larger than the luminous mass. It's as if you weighed a sealed, transparent box by looking at it, and then weighed it again by shaking it and listening to the contents rattle, and the second weight was mysteriously, consistently heavier. There's something inside that has weight but gives off no light, and its identity is one of the most nuanced detective stories in modern astrophysics. The immediate and most thrilling suspicion, of course, falls upon dark matter. After all, this is the same technique we use to discover the missing mass in galaxies. The rotational speeds of stars around a galactic center are far too high to be explained by the gravity of the visible stars alone, compelling us to infer the presence of a massive, invisible dark matter halo. So, when we see the same kind of mass discrepancy in a globular cluster, the natural conclusion would be that these ancient structures are also embedded within their own small halos of dark matter. This would be a monumental discovery, potentially linking the formation of the smallest star clusters directly to the vast cosmic web of dark matter. However, the evidence points in a different, more complex direction. For the vast majority of well-studied clusters, the mass-to-light ratio discrepancy is not nearly as extreme as it is in galaxies. While the dynamical mass is often 10 to 50% higher than the luminous mass, it is not orders of magnitude larger as we see in dwarf galaxies. This subtle but crucial difference suggests that the unseen mass is not a dominant, enveloping halo of exotic particles, but something else entirely, something intrinsically linked to the cluster's own stellar population. So, if it's not a vast halo of dark matter, what is causing this gravitational surplus? The leading suspects are the dark remnants of dead stars, and they form a kind of invisible underworld within the cluster. Over billions of years, the most massive stars in a cluster have lived out their fiery lives and died. Many have left behind stellar mass black holes, neutron stars, and white dwarfs. These objects are the gravitational ghosts of the cluster. A stellar mass black hole, for instance, can contain the mass of several suns compressed into a volume smaller than a city, emitting no light whatsoever unless it is actively feeding. A neutron star is similarly dense and dark. Even white dwarfs, while they initially glow from residual heat, eventually cool and fade to near invisibility. The key point is that these remnants still possess their full mass and therefore their full gravitational pull. They contribute nothing to the cluster's overall brightness, but they contribute significantly to its weight. When we calculate the luminous mass, we are primarily counting the bright, living stars, but the dynamical mass faithfully records the gravitational tug of every single object, including this vast population of dark stellar corpses. This means the mass-to-light ratio is not a static number, it's an evolving fossil record. A young cluster where few stars have died should have a mass-to-light ratio close to 1. An ancient cluster like those in the Milky Way, which has had ample time for generations of stars to perish, should have a higher ratio precisely because it has accumulated a significant inventory of these invisible dead stars. The observed anomalies are, in this view, not anomalies at all, but the expected signature of a mature stellar population. However, the plot thickens when we consider the distribution of this dark mass. It's not just what the unseen mass is, but where it is that creates the dynamic signature we observe. Through a process called mass segregation, which we've discussed, the heaviest objects in a cluster, including both bright, massive stars and these dark remnants, sink towards the core over time. This means the center of the cluster becomes a concentrated repository of invisible mass. The effect of this on the stellar motions is profound. Stars whipping around the core feel the combined gravity of the visible stars they fly past and the intense, concentrated pull from this central reservoir of black holes and neutron stars. This can cause their velocities to be higher in the core than a model based on luminous mass alone would predict. The mass-to-light ratio, therefore, isn't constant throughout the cluster. It can be much higher in the dense core than in the outer halo, a direct result of this gravitational sorting. In some clusters, there's compelling evidence that this sinking of heavy objects has led to the formation of a central, intermediate mass black hole, a single, massive dark anchor that profoundly influences the orbits of nearby stars and contributes significantly to the dynamical mass without adding a single photon to the luminous mass budget. But there is another, more subtle force at work that can mimic the gravitational signature of unseen mass, and that is the cluster's own dynamic history. A globular cluster is not a system in perfect equilibrium. It has been shaped by billions of years of gravitational interactions, both internally and with the Milky Way. Stars on elongated or radial orbits behave differently than stars on circular orbits. If a significant fraction of a cluster's stars are on these radial paths, all swooping in and out of the core in a coordinated way, it can alter the overall velocity distribution in a manner that, when we apply our standard models, makes it appear as if there is more mass present than we can see. This is a case of the cluster's complex orbital architecture fooling our simple weighing scales. Furthermore, if a cluster has recently experienced a close encounter with the galaxy, a tidal shock it can have ejected a large number of its low-mass, faint stars. This would leave behind a population that is, on average, more massive, thereby increasing the mass-to-light ratio without requiring any dark remnants at all. The cluster would simply be top-heavy, its light dimmed relative to its mass because its faintest members have been stripped away. Untangling these various effects, the presence of dark remnants, mass segregation, orbital anisotropies, and tidal stripping, is the great challenge of interpreting the mass-to-light ratio. It's not a single mystery with a single answer, but a complex diagnostic that reveals the intricate balance between what a cluster is made of and how it has lived its life. Each anomaly is a unique clue pointing to the specific dynamical age, remnant population, and past trauma of the stellar city in question. And this leads us to a discovery that connects the largest scales of the cosmos to the tiniest points of ancient light, a correlation so fundamental it might be the master key to understanding how galaxies are built. It's the observed relationship between the number of globular clusters a galaxy possesses and the mass of its invisible dark matter halo. At first glance, this seems like an absurd connection. How could these relatively small, dense star clusters, which themselves appear to contain little to no dark matter, have anything to do with the immense, invisible gravitational scaffolding of an entire galaxy? Yet the data is overwhelming and clear. If you take a galaxy from the smallest, faintest dwarf to the largest, brightest elliptical, and you count its globular clusters, that number is a remarkably reliable indicator of the total mass of the dark matter halo that surrounds it. A galaxy with a handful of clusters has a relatively small dark matter halo. A galaxy like the Milky Way, with over 150 clusters, sits within a halo of about 1.5 trillion solar masses. And the true behemoths, giant elliptical galaxies at the hearts of galaxy clusters, can have thousands of globular clusters, each one tracing the presence of a dark matter halo that is hundreds of times more massive than our own. This isn't just a loose trend, it's a tight mathematical relationship. It's as if the universe left barcodes on its galaxies, where the number of glittering, ancient star clusters directly reveals the weight of the invisible giant in which they are embedded. The profound implication of this correlation is that the formation of globular clusters and the assembly of dark matter halos are not separate processes. They are deeply intertwined chapters of the same cosmic story. This connection likely was forged in the universe's fiery infancy. The prevailing theory is that both the densest dark matter halos and the most massive globular clusters formed from the same initial seeds, the rarest, most pronounced peaks in the density fluctuations of the early universe. Imagine the cosmos just after the Big Bang, filled with a nearly uniform soup of dark matter and gas. Tiny quantum fluctuations were stretched by the universe's rapid expansion, creating a cosmic web of slight overdensities and underdensities. At the intersections of this web, where the dark matter was most densely concentrated, gravity worked its magic most efficiently. These regions had the deepest gravitational potential wells, acting as powerful traps for the primordial hydrogen and helium gas. It was within these specific, high-density environments that conditions were just right for the rapid, monolithic collapse that gives birth to a globular cluster. The immense pressures and shock waves in these collapsing pockets of gas could trigger a starburst so intense and efficient that it formed a massive, tightly bound cluster of stars in a single, swift event. In this picture, a globular cluster is not a random ornament that later attached itself to a galaxy. It is a core component, a fundamental building block that formed concurrently with the very foundation of the galaxy's dark matter structure. The number of these initial density peaks in a region would naturally dictate both the final mass of the assembled dark matter halo and the number of globular clusters it could produce. A region with many high peaks would coalesce into a massive halo filled with many clusters, while a region with only a few peaks would become a smaller halo with only a few clusters. The correlation we see today is therefore a fossilized imprint of the initial conditions of the universe, a direct link between the largest structures and some of the smallest, oldest stellar systems. This relationship transforms globular clusters into powerful cosmological tools. For astronomers, weighing a distant galaxy's dark matter halo is an incredibly difficult task. It requires painstaking measurements of stellar velocities or the subtle distortions of gravitational lensing, but counting its globular clusters, that is often far more straightforward. With a powerful telescope like Hubble, astronomers can simply take an image of a distant galaxy, count the points of light that are its globular clusters, and then use the established relation to get a remarkably accurate estimate of the galaxy's total dark matter mass. This turns these ancient star clusters into a kind of universal scale, a standard weight we can use to measure galaxies across the cosmos. This is especially valuable for studying the mysterious ultra-diffuse galaxies, faint, wispy galaxies that are as large as the Milky Way but contain only 1% of its stars. When astronomers counted the globular clusters in several of these ghostly galaxies, they were stunned to find numbers suggesting they reside within incredibly massive dark matter halos, far larger than their feeble starlight would suggest. This discovery helped solve the puzzle of how such fragile-looking structures could hold themselves together, revealing that they are not weak at all, but are in fact dominated by invisible dark matter, with the globular clusters acting as the telltale signposts of that hidden mass. Yet this elegant picture is not without its own puzzles. The relationship, while strong, is not perfectly linear, and the scatter in the data holds its own important clues. Some galaxies have slightly more clusters than their dark matter mass would predict, while others have slightly fewer. These deviations are not errors, they are the scars of a galaxy's individual life story. A galaxy that has been a voracious cannibal consuming many smaller satellite galaxies will have stolen their globular clusters along with their stars. This galaxy would end up with a richer cluster system than a galaxy of similar mass that had a quieter, more isolated history. We see this in our own Milky Way, a significant fraction of its globular clusters are now believed to have been stolen from devoured dwarf galaxies like Gaia Enceladus. On the other hand, a galaxy that has experienced intense tidal stripping from a nearby massive neighbor might have lost many of its outer globular clusters, leaving it with a poorer system than its dark matter halo would otherwise suggest. The precise way a galaxy's cluster population fits onto the universal relation therefore tells a story about its past interactions, its mergers and acquisitions, and its near misses. The globular clusters are not just passive tracers of mass, they are dynamic tracers of history. Their total number gives us the weight of the galaxy, but their specific distribution, motions, and chemistries tell us how that galaxy achieved its current form, painting a detailed portrait of growth and evolution across billions of years. Deep within the placid appearance of an ancient globular cluster, some of its most senior residents are experiencing internal convulsions of a truly dramatic scale. These are the stars on the asymptotic giant branch, or AGB, and they are in the final, fiery throes of their long lives. Having already passed through the red giant phase, these stars are now powered by a complex and inherently unstable engine, two separate fusion shells burning one on top of the other. Deep inside, a shell of helium fuses into carbon and oxygen. Surrounding that, like a nested celestial onion layer, a second shell fuses hydrogen into helium. This delicate double shell structure is a ticking time bomb, and its periodic detonations, known as thermal pulses, create some of the most profound and observable changes in the entire life of a star. The process begins with the helium shell. It burns in a quiet, steady state for tens of thousands of years, producing helium ash which rains down onto the core below. This steady accumulation increases the density and temperature at the base of the helium shell until it reaches a critical flash point. At this moment, the helium ignites explosively in a runaway thermonuclear reaction, a thermal pulse. This isn't a gentle flicker, it's a violent burst of energy that releases as much power in a few months as our sun will emit over several millennia. The immediate effect of this internal blast is a colossal breathing motion of the entire star. The sudden energy release from the helium pulse forces the overlying hydrogen-burning shell to extinguish temporarily and causes the star's outer layers to expand dramatically. The star swells to its absolute maximum size, becoming a truly super-sized giant. But this expansion comes at a cost. As the star puffs up, its outer layers cool, and this cooling triggers a powerful and catastrophic episode of mass loss. The star drives a super wind, ejecting vast quantities of its own atmosphere out into space at speeds of up to tens of kilometers per second. After a year or so, the thermal pulse subsides. The helium shell returns to a quiet burn, and the star begins to contract. As it shrinks, it heats up, which reignites the dormant hydrogen-burning shell. The star then settles back into its steady state, but it is forever changed. It is now slightly smaller, hotter, and it has just ejected a significant fraction of its mass into the surrounding cluster environment. This entire cycle, the quiet buildup, the violent pulse, the massive expansion, and the super wind repeats itself every 10,000 to 100,000 years. With each pulse, the star loses more of its outer envelope, a process that is far more efficient and dramatic than the gentle mass loss of a normal red giant. These thermal pulses are not just an internal affair. They are the primary chemical factories for a specific class of elements within the cluster. The intense, neutron-rich environment during the pulse is a cosmic forge for a process called the slow neutron capture process, or the S process. During the pulse, neutrons are slowly added to the nuclei of existing seed elements like iron. These seed nuclei absorb the neutrons and, through subsequent radioactive decays, are transformed into heavier elements all the way up the periodic table. This is how the star produces a significant portion of the universe's strontium, yttrium, zirconium, barium, and even lead, Before a thermal pulse, the outer atmosphere of the star might be rich in these S-process elements, but they are trapped deep within. The convulsive expansion and the powerful superwind that follows a pulse act as a delivery mechanism. They literally dredge these newly forged heavy elements up from the star's interior and blast them out into space. The ejected material is a highly enriched chemical soup carrying the specific isotopic signature of the S process. This polluted gas then mixes with the intracluster medium, becoming part of the raw material from which future generations of stars or planets might one day form. The presence of these specific S-process elements in the spectra of later generation stars within a cluster is a direct forensic signature of this violent process having occurred in their long-dead AGB star ancestors. The frequency and intensity of these thermal pulses are not uniform across all stars, and this is where the unique environment of a globular cluster adds another layer of intrigue. A star's initial mass and, crucially, its chemical composition heavily influence its AGB evolution. In a cluster with multiple stellar populations, a star from a later generation, born with extra helium and other elements, will have a different internal structure than a first-generation star. This can lead to more frequent or more intense thermal pulses, altering the rate and chemical mix of the material it pollutes back into the cluster. Furthermore, the dense core of a globular cluster introduces the possibility of dynamical interactions that could perturb an AGB star. A close gravitational encounter with a binary companion or a passing star could, in theory, tidally squeeze the star at just the wrong moment, potentially triggering a thermal pulse prematurely or altering the efficiency of the dredge-up process that brings the heavy elements to the surface. While this is a challenging effect to observe directly, it suggests that the social life of the cluster could be subtly influencing the very nuclear processes occurring deep within its most evolved stellar members, turning their final, unstable breaths into a complex dialogue between internal physics and external dynamics. We now arrive at a theoretical puzzle so profound it challenges our very understanding of how gravity operates in the most extreme environments. It's known as the final parsec problem, and while it was originally conceived for the supermassive black holes at the centers of merging galaxies, this same gravitational conundrum applies with startling relevance to the dense hearts of the most massive globular clusters. Imagine two stellar mass black holes, or perhaps even intermediate mass black holes, that have been brought together through the relentless dynamical friction we discussed earlier. They sink to the very center of the cluster, finding one another in the chaotic dance and becoming gravitationally bound. They form a binary system, a pair of invisible cosmic predators now locked in a mutual orbit. According to Einstein's theory of general relativity, such a binary should lose energy by emitting gravitational waves, those ripples in space-time. As they lose energy, their orbit shrinks, they spiral closer together, and their orbital speed increases in a runaway process that culminates in a final, violent merger. This is the primary source of the gravitational wave signals we detect with observatories like LIGO and Virgo. The mathematics is clear and beautiful for a binary that has been brought to a sufficiently close separation. But there's a catch, a cosmic traffic jam that occurs at the very end of this journey. The problem is in the name itself, the final parsec. A parsec is a unit of distance, about 3.26 light-years. As the black hole binary spirals inward, the efficiency of gravitational wave emission is exquisitely sensitive to the distance between them. When they are far apart, the emission is incredibly weak. It's only when they get extremely close separations of less than about 0.01 parsecs that the gravitational wave radiation becomes powerful enough to rapidly drain their orbital energy and force a final merger within the age of the universe. The great challenge is getting them across that last parsec of separation. It's the gravitational equivalent of trying to push two powerful magnets together when they are just a little too far apart to snap together on their own. You need an external force to bridge the final gap. So, what causes this stalling? The issue lies in a fundamental shift in the gravitational dynamics at play. In the early stages of the inspiral, the black holes are surrounded by a dense sea of other object stars, white dwarfs, neutron stars. As the binary swings around, its gravitational pull acts like a slingshot, flinging these background stars out of the core at high velocities. This process, known as dynamical friction, is very effective at first. The binary transfers its orbital energy to the surrounding stars, causing it to harden and its orbit to shrink. But here's the catch: this process is a victim of its own success. The binary effectively cleans its own house. It ejects all the stars that are on orbits that can interact with it strongly. Once the surrounding region is depleted of stars, once the binary has created a gravitational vacuum around itself, there's nothing left to fling away. With no more stars to absorb the binary's orbital energy, the inspiral through dynamical friction grinds to a near halt, leaving the black holes stranded in a stable, wide orbit, perpetually separated by that critical final parsec, unable to get close enough for gravitational waves to take over and finish the job in a timely manner. They become a stalled binary engine trapped in a cosmic standoff. This is where the unique, super-dense environment of a globular cluster core becomes absolutely critical. A galaxy's core is vast, and replenishing the stars around a stalled binary is a slow and difficult process, but a globular cluster is a different beast entirely. Its core is so incredibly dense and dynamically active that it offers not one, but several potential solutions to this final parsec problem. The first and most powerful solution is the constant resupply of fuel. In a cluster core, stars are packed so tightly that their orbits are constantly being perturbed. The binary black hole doesn't just sit in an empty cavity. That cavity is constantly being refilled by new stars that wander in from the outer regions of the cluster due to their own random motions and gravitational interactions. This provides a steady stream of new objects for the binary to interact with and eject, allowing the hardening process to continue far longer than it would in a more placid galactic core. The cluster, in essence, is a self-stirring system that never lets the gravitational well around the binary run dry. Another fascinating solution involves the complex gravitational dance of three-body interactions. It's not just single stars that can interact with the binary. In the bustling core, another black hole or a dense neutron star can venture too close. When a third massive object enters the scene, the resulting three-body interaction is a chaotic gravitational ballet. The most likely outcome is that the lightest of the three objects gets gravitationally slingshot out of the core at an enormous velocity, becoming a hypervelocity star or stellar remnant. In the process, the original binary receives a gravitational kick and its orbit hardens, shrinking that final separation just a little bit more. These repeated, violent encounters can act like a series of hammer blows, relentlessly driving the binary members closer together until they finally cross the threshold where gravitational wave emission becomes dominant. This makes a globular cluster core a far more efficient factory for black hole mergers than the center of a galaxy, precisely because of this relentless dynamic churning. Perhaps the most elegant solution of all, however, involves the black holes themselves finding new partners. In a cluster core rich with black holes, a stalled binary might not be a permanent marriage. A close encounter with a third black hole can lead to a cosmic partner swap. The three-body interaction can result in one of the original binary members being ejected, replaced by the incoming black hole. This new binary will often be formed with a tighter, more eccentric orbit, bypassing the stalling point of the previous pair entirely. This process, known as binary exchange, can create binaries that are born already within the gravitational wave-dominated regime, ready to merge almost immediately. The very chaos of the cluster core, therefore, doesn't just hinder the process. It actively creates pathways to circumvent the final parsec problem altogether. ensuring that these dark gravitational engines can ultimately complete their cosmic dance and send their ripples through the fabric of spacetime. This resolution of the final parsec problem within globular clusters doesn't just tidy up a theoretical loose end. It fundamentally reshapes our expectations for the entire field of gravitational wave astronomy. If these dense stellar environments are as efficient at forging and merging black hole binaries as the dynamics suggest, then they should be contributing a dominant, steady background hum of cosmic collisions to the universe. This leads to a very specific and testable prediction for observatories like LIGO, Virgo, and CAGRA. The models suggest that globular clusters could be responsible for a significant fraction, perhaps even the majority, of the binary black hole mergers we detect. The mergers from clusters are predicted to have certain distinguishing features because they are formed dynamically through chaotic encounters rather than from isolated binary stars evolving together. The black holes involved can have a wider range of masses, and crucially, their spins are expected to be randomly oriented relative to their orbital plane. This is a key fingerprint. When LIGO analyzes a gravitational wave signal, it can extract information about the spins of the merging black holes. A detection where the spins are clearly misaligned or tilted is a strong candidate for a dynamical origin, a merger that was likely orchestrated in a dense environment like a globular cluster rather than a quiet, isolated binary system. Furthermore, the very mass distribution of the black holes we see merging could bear the cluster's signature. The relentless process of dynamical hardening and binary exchange might favor the survival and merger of more massive black holes, potentially explaining why we see so many black holes in the so-called upper mass gap, with masses significantly higher than what standard stellar evolution models might predict. However, this is where the plot twists into a fascinating puzzle. When we compare these robust theoretical predictions to the actual catalog of gravitational wave events detected so far, the story becomes more nuanced. While LIGO has indeed observed mergers with properties consistent with a dynamical origin, the overall numbers are not quite as high as some of the most optimistic globular cluster models forecasted. This discrepancy, this quieter-than-expected cosmic merger rate from clusters, is itself a profound piece of data. It forces us to re-examine our assumptions about life inside these ancient cities. One possibility is that our models have overestimated the retention efficiency of black holes. After a black hole is formed in a supernova, the explosion can give it a natal kick, a recoil velocity that can propel it out of the cluster entirely if the kick is strong enough. If most black holes are born with such high kicks, they would be ejected before they ever had a chance to sink to the core, find a partner, and merge. The clusters would be largely void of the very objects needed to power this gravitational wave engine, turning them from roaring factories into much quieter workshops. The actual merger rate would then be a delicate balance between the efficiency of black hole formation and the violence of their birth kicks. Another compelling explanation involves the ultimate fate of the black holes themselves. Perhaps the dynamical processes inside clusters are so efficient that they actually clear themselves out. A dominant binary black hole in the core, through its slingshot interactions, could eject not only stars but also other black holes that venture too close. This self-ejection mechanism could systematically purge the cluster of its entire population of stellar mass black holes over a few billion years, leaving behind a core dominated by lighter objects like neutron stars and white dwarfs. In this scenario, globular clusters were incredibly active gravitational wave factories in the distant past, but have since grown quiet in their old age, having expelled their most massive and dynamic residents. We would be observing them in a quiescent phase of their life cycle, a conclusion that would dramatically alter our view of their long-term evolution and their role in shaping the gravitational wave sky. The current non-detections and the precise statistics of the events we are seeing are therefore a powerful diagnostic tool. Every new gravitational wave event added to the catalog is another data point that helps us constrain the physics of globular clusters. By carefully measuring the masses, spins, and merger rates, we are effectively conducting a census of black hole populations in environments we cannot directly see into. A higher than expected rate of mergers with random spins would suggest that clusters are indeed teeming with black holes and are efficiently solving the final parsec problem. A lower rate or a preference for aligned spins would point toward a different dominant formation channel, perhaps from isolated binary stars in the galactic field. This interplay between gravitational wave astronomy and stellar dynamics is a breathtaking example of how one field of science can illuminate another. The silent ripples in spacetime are not just signals, they are messages from the heart of these ancient stellar metropolises, telling us about the lives and deaths of their most secretive inhabitants and challenging us to decode the complex social rules that govern life in the densest neighborhoods of the cosmos. The intricate dance to overcome the final parsec relies on the chaotic environment of the cluster core itself, with one of the most elegant solutions involving the timely arrival of a third black hole. Imagine the stalled binary locked in its wide orbit when a third massive interloper drifts into their gravitational sphere of influence. The resulting three-body interaction is a gravitational free-for-all, a chaotic ballet where the three black holes exchange energy in a wildly unpredictable way. The most probable outcome of this cosmic scuffle is that the lightest of the three is unceremoniously ejected from the system, flung out of the cluster core at a significant fraction of the speed of light, becoming a hypervelocity black hole destined to wander the galactic halo. This ejection is the key. The energy required to launch one black hole away is stolen from the orbital energy of the remaining pair. This loss of energy causes the surviving binary to harden dramatically. Its orbit shrinks and often becomes more elliptical, catapulting it over the final parsec hurdle and into the regime where gravitational wave emission can efficiently take over and drive the merger within a cosmologically short time. This process, known as gravitational scattering, effectively uses the sacrifice of one black hole to seal the fate of the other two. It's a brutal but effective form of dynamical matchmaking, where the social chaos of the cluster core provides a constant stream of potential partners and catalysts to ensure these dark unions can be consummated. Beyond these dramatic black hole interactions, a more subtle and continuous process may also be at work, involving the gentle but persistent influence of the countless stars that still populate the core. Even after the binary has cleared its immediate vicinity, the cluster is a dynamic entity. Stars on random orbits are constantly diffusing in from the outer regions, refilling the lost cone, the region of orbital space that allows for close encounters with the central binary. While not as violently efficient as a three-black hole encounter, this steady trickle of stellar interactions provides a persistent, low-level hardening force. Each time a star is gravitationally slung away by the binary, it carries off a tiny amount of the binary's orbital energy. Over millions of years, this cumulative effect, this death by 1,000 gravitational cuts, can slowly but surely nudge the binary across the final parsec divide. The efficiency of this process depends entirely on the cluster's ability to keep this stellar reservoir replenished, which is why the very densest clusters, with their immense gravitational pull and rapid relaxation times, are the most likely candidates for hosting this slow evolutionary in-spiral. A more exotic and still speculative solution involves the potential presence of gas within the cluster. While globular clusters are famously devoid of the vast gas clouds seen in galaxies, it's not impossible that small amounts of material could be present. This gas could originate from the powerful winds of asymptotic giant branch stars or from the tidal disruption of stars that pass too close to one of the black holes. If a circumbinary disk of gas were to form around the stalled pair, it would introduce a completely new physical mechanism, gaseous friction. As the black holes orbit within this disk, they would create spiral density waves similar to the gaps planets carve in protoplanetary disks. The gravitational interaction between the black holes and these waves would transfer angular momentum from the binary to the gas, causing the black holes to spiral inward toward each other. This process could be incredibly efficient, potentially solving the final parsec problem on a much shorter timescale than stellar dynamical processes alone. While the evidence for significant gas reservoirs in clusters is currently scant, future ultra-sensitive radio telescopes might just be able to detect the faint whisper of such a disk, providing a crucial clue to this alternative merger pathway. Our ability to distinguish between these scenarios and finally solve the mystery of the final parsec rests entirely on the next generation of observational tools. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the next decade, will be a game-changer. While ground-based observatories like LIGO are tuned to the high-frequency waves from stellar mass black hole mergers, LISA will operate in a lower frequency band, making it exquisitely sensitive to the earlier, in-spiral phases of massive binary systems. For a stalled binary at the center of a globular cluster, LISA could detect the persistent, nearly constant hum of their gravitational waves years, even decades before they finally merge. This would provide an unprecedented census of these stalled systems, telling us directly how common they are and precisely how far apart the partners are separated. By monitoring their orbits over time, we could even measure the minute orbital decay caused by those slow, stellar scattering events, providing direct observational proof of one of the proposed hardening mechanisms. Simultaneously, a new era of extremely large telescopes is dawning. The Giant Magellan Telescope and the 30-meter telescope, with their colossal light-gathering power and phenomenal resolution, will be able to peer into the very hearts of nearby globular clusters like never before. They will measure the precise motions of thousands of individual stars in a cluster's core with astrometric precision down to micro-arcseconds. The subtle gravitational wiggles in the paths of these stars as they are tugged by the invisible hands of a central black hole binary will be laid bare. By mapping this intricate dance, we can weigh the binary, determine its separation, and even infer the eccentricity of its orbit, all of which are direct tests of the different hardening models. A widely separated circular binary would point toward a stalled state, while a tight, eccentric pair would be the smoking gun for recent dynamical hardening, likely through a three-body interaction. These telescopes will turn the core of a globular cluster from a blur of light into a detailed gravitational map, revealing the architecture of its dark heart. Furthermore, the relentless survey power of missions like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope will provide a statistical revolution. By observing hundreds of globular clusters throughout the local group and beyond, we will move from studying individual cases to understanding the population as a whole. We will be able to correlate the presence of central black hole binaries with global cluster properties like mass, density, and age. Do only the most massive, dense clusters show evidence of these binaries? Does the binary fraction drop in very old clusters, suggesting they have already ejected their black hole populations? These large-scale demographic studies will provide the crucial context to determine which solutions to the final parsec problem are most common in the universe, separating rare curiosities from fundamental evolutionary pathways. The convergence of gravitational wave astronomy, high-resolution imaging, and large-scale surveys promises to transform this theoretical puzzle into an observational science, finally revealing the ultimate fate of the darkest and most massive residents of these ancient stellar cities. As we've journeyed through these 50 strange discoveries, it's clear that globular clusters are not the simple stellar fossils we once thought. They are dynamic, complex, and often baffling systems that continue to challenge and refine our understanding of astrophysics, stellar evolution, and the history of the cosmos itself. We began with stars that appear older than the universe and ended with gravitational wave factories hidden in their cores. we've encountered stellar vampires, phantom dark matter, and chemical fingerprints of cosmic cannibalism. Each revelation peels back a layer, revealing not just answers, but deeper, more profound questions. These ancient cities of stars have become the ultimate cosmic laboratories, places where the fundamental rules of physics are stress-tested under conditions of unimaginable density and timescales that dwarf human history. They force us to acknowledge that our models are not perfect, that our understanding is a work in progress, and that the universe is far more creative and chaotic than we ever dared to imagine. The very existence of blue stragglers tells us that stars can be rebooted. The absence of dark matter tells us that galaxy formation has multiple pathways, and the presence of planets around pulsars screams of resilience and rebirth in the most hostile of environments. This isn't just a collection of trivia, it's a paradigm shift. We can no longer look at that faint, fuzzy patch of light in the night sky as a mere celestial ornament. It is a living, breathing, and evolving ecosystem, a silent witness to nearly 14 billion years of cosmic history that is only now beginning to whisper its secrets. So, which of these mysteries resonates most deeply with you? Is it the philosophical headache of stars that defy the age of the cosmos? The violent social drama that creates stars living on borrowed time? Or perhaps the profound implication that these clusters, devoid of dark matter, might be the key to finally identifying its true nature? Let us know in the comments below which discovery bent your mind the most. If this journey into the cosmic unknown has sparked your curiosity, be sure to subscribe for more deep dives into the universe's greatest puzzles. The cosmos is vast, strange, and endlessly fascinating, and there are